Within Six Sigma, one of the most commonly used tools in order to test to see if a change has made a difference in your process is hypothesis testing. A hypothesis test is a statistical analysis where you're checking if a result is statistically significant as you predicted it. So you're using data from your process to test a claim about a population parameter. You conduct hypothesis tests because you want to have data-driven decisions, so you want to be able to provide evidence to support an opinion. And typically that opinion is that you've seen a change within your process. But now you want to use data to support that there actually has been a change. You're going to use statistical significance to quantify or show whether or not that change is significant. You're using sample data, and you're drawing inferences about the population based on that sample data. For example, you could use hypothesis testing within your Six Sigma projects to determine whether a process improvement effort has actually reduced the proportion of defective items. Or you could use hypothesis testing to investigate a claim that a new accounting software package has reduced the processing costs. Another example where you could use hypothesis testing is to validate whether the loan processing time at a bank has decreased since the introduction of an online application process. Within Six Sigma, you started with the define phase, where you determined what the issues are within your process. You set up problem goals and the business case for taking on a Six Sigma project. And then within the measure phase, you started to identify what are some of those key variables or factors that are impacting your process. And then within the analyze phase, you want to look closer at those factors to determine if they have an impact on the mean of your output or in the variation of your output. Hypothesis testing typically comes into play in the improve phase of DMAIC, as you implement improvements or changes, and then go back to analyze to determine if you got the intended results. There are several different types of hypothesis tests. The first type of test is a one-sample hypothesis test, where you're looking at the means. For example, if you want to examine the difference between the mean of your process and the industry standard. Based on your distribution, you want to know if there is a statistically significant difference between the mean of your process and that industry standard. You can also do a two-sample hypothesis test for the mean, where you're comparing the mean of one process to the mean of another process. And then there are several more advanced statistical analyses for hypothesis testing, such as the paired t-test, the test for proportions, the test for variances, and Anova, which is an analysis of variances. The test for variances and Anova are used when you're trying to reduce the variation within your process, and to see if there's been a difference between the variation of your process once you've made a change to the process. In hypothesis testing, one of the first things that you set up are your hypotheses. This is what you're trying to prove or disprove, and you can have null hypothesis or an alternative hypothesis. Your null hypothesis is what you're saying and expresses the status quo. If you think about the null hypothesis, it assumes that any observed differences are due to chance or random variation. Typically, with a null hypothesis, which is your h sub 0 or h naught, you're setting it up as two values are equal to each other. One is less than or equal to another value, or one is greater than or equal to another value. It assumes that any observations are the result of chance or random variation. With your alternative hypothesis, it's expressed as h sub a. This is what you're trying to test, or what you're trying to prove. With the alternative hypothesis, you're assuming that the observed differences are real, and it's not due to chance or random variation. So this is typically where you change something in your process, and you're trying to see if now there has been a difference in the mean of your output. Your alternative hypothesis needs to be mutually exclusive from your null hypothesis. In other words, you want to make sure that as you are testing this, the values have to fall in one category or the other. With your alternative hypothesis, you're testing for the opposite of a null hypothesis. So you will be testing that the two values are not equal, that it's greater than or less than. With your hypothesis test, there are two primary goals. First, you want to be able to see if there is a difference between two values. So the output for the outcome of your hypothesis test could be that you reject your null hypothesis in favor of your alternative hypothesis, and this is essentially saying that your result is statistically significant. The second goal would be that you fail to reject your null hypothesis And when you fail to reject your null hypothesis, you're stating that there is insufficient evidence to claim your null hypothesis is invalid. You're stating that there is insufficient evidence to claim your null hypothesis is invalid, or that the alternative hypothesis is true. For example, in a hospital, you could set up a null hypothesis that any difference in processing time, based on improvements from a Six Sigma process, are due to random variation and chance, and essentially your improvement efforts have not made a difference. So your null hypothesis would be to state that there is no change based on the process improvement efforts. Your alternative hypothesis would be to show that the process has actually improved based on your Six Sigma efforts. If you know that the average wait time at the outpatient clinic at this hospital is 10 minutes, then you would set up your null hypothesis as being equal to 10. Then your alternative hypothesis would be that it's not equal to 10. It's important to note that you're testing to see if there's been a change. And that's why you will set up your null and alternative hypotheses as equal to or not equal to, because the change could have been to reduce or increase your wait time for your patients. It's also important to note how you present the results, which may not sound natural to you. You state your results in the terms of the null hypothesis. For example, you would state either "we reject the null hypothesis" or "we fail to reject the null hypothesis." As a Six Sigma professional, it's important to understand the difference between statistical and practical significance in hypothesis testing. When you think about practical significance, you really need to understand the rationale for the decisions. Depending on your organization, a small value might be very meaningful to a business. For example, if you think about the healthcare or air safety where human health and safety or a catastrophic loss could be involved, then a small change might be very significant. So it's important to understand the test limitations and how those relate back to the rationale for the decisions. In addition, you need to understand what your business goals are, because there might be a seemingly large difference that might not mean much to some organizations, but it might be very important to your organization. So you need to consider the business goals and how these changes relate back to what you're trying to achieve for your organization. When you're first testing for practical significance, there are several key questions that you need to ask. First, you need to understand, will there be any appreciable gain or change? Because when you're thinking about practical significance, it relates back to the organization itself and how it's going to impact the organization based on that change. In addition, with hypothesis testing, you're using a sample to make inferences about a larger population. Depending on your results, you need to go back and look at what was your sample size. Was it sufficient? If you had a smaller sample size, and you're trying to infer about your population, then you might have to take that into account and rethink what your results were giving you, because sometimes it could be too expensive to have a large sample size. You also need to think about how easy change is to implement. From a practical standpoint, thinking about the level of significance, you need to see what that impact is and what it will have on the business and how expensive and easy it is to implement. In addition, since you're using samples to make the inference about your population, you need to understand if the differences in the samples have real meaning. Also, in terms of your sample size, was it a representative sample? Another key question is, you need to know if there's a strong financial case for change. Just because something is statistically significant, that doesn't mean that making that change is going to be cost-effective and make business sense for your organization. And then, by knowing that there is a change, you also need to think about how a potentially small value may have a significant improvement to your process, or vice versa. Now, when you establish your practical significance, there's three key areas that you need to consider. The first is you need to consider your confidence interval, and this goes back to your business case. What do you really need to have in terms of your confidence interval to have a specific level of confidence within your process improvement efforts? It's important as a Six Sigma professional that you present a complete picture of the test results and let the business managers decide based on the organization and the business requirements. This allows management to consider the organization and the process knowledge to make an educated decision on what's best for the organization. You also need to choose the sample size carefully. A small sample size means that there is a possibility that a large difference won't be detected and deemed statistically significant. Or you could choose a larger sample size, where you might find a very small difference, but it could be interpreted as statistically significant, even if it's not practical. So it's important you think about the strength of significance, and this is your p-value that's going to be compared with your alpha value, and the actual difference between what you are comparing. With hypothesis testing, you're using a sample to infer information and data about your population, and so it's important to understand sample estimates of population parameters. There are several data characteristics used within your hypothesis testing: the mean, standard deviation, and variance. Population parameters are presented by Greek letters. For mean, it's mu, for standard deviation, it's sigma, and for variance, it's sigma squared. For sample statistics, mean is represented by x bar, standard deviation is represented by s, and variance is represented by s squared. It's useful to understand the differences between these values, because they're used to find a single value to estimate that population parameter. So let's explore an example using point estimates of your sample to infer information about your population. Let's suppose that you're conducting a survey of 2,000 people from across the country on whether or not they are for or against universal health care. Based on the 2,000 people who were surveyed, you had 1,100 of those 2,000 that are for universal health care. The population parameter in this case is all of the people within the country, but the sample that you're using is 2,000 people, because that's what you surveyed. The point estimate then is the proportion of people who are for universal health care. In this example then, the statistic that you reached for the sample of the population is that 55% of all people in the country are for universal health care. And so that gives you a point estimate that 55% of the population is in favor of universal health care. Now, it's important to understand there are some weaknesses if you use point estimates. It's highly unlikely that your point estimates that you are using are exactly the same as the true population parameters, because you're using that information from your sample data to infer about the entire population. That's why it's important that you have a range or interval over some set of your values that you're using. You need to use information so that you're able to estimate where the true population mean and standard deviation are most likely to fall. This is where intervals, and particularly the confidence intervals, are very useful, because they provide a better measure. For example, if you're looking at testing the confidence intervals, that gives you information on the variability of the sample statistics, and whether two samples originate from the same population, or whether a target falls within the natural variation of a process. So let's say you're trying to figure out the likely values for the population parameter and you want a 95% confidence level. You're able to determine that your confidence intervals, based on the mean and your variation from your sample statistics, provide you with a confidence interval from 9.1 to 9.3 centimeters, and that would contain the actual population mean 95% of the time. Here's another example of how you could determine whether a target value falls within the natural variation of a process. Let's say you have a pharmaceutical company that has a new drug they want to test, and the goal of the drug is to treat high cholesterol. You want to be able to determine whether the drug improves cholesterol levels to the healthy target of 200 milligrams, and so your target for this value is 200 milligrams. Based on the sample data that you're collecting, you can set a confidence level at 95%, such that 95% of your value should fall within a specific range. Then your confidence interval calculates that values between 195 and 210 would contain 95% of the values. You'll use that information to check whether the target value falls within your confidence interval. If it doesn't, then the sample is from a population with a mean that's different from the target value. And if the target value does fall within the confidence interval, then you know that the sample is from a population with a mean that's the same as the target value. In this case, your target value is 200, which is within your confidence interval. So you can conclude at the 95% confidence level that the drug is decreasing cholesterol levels to between 195 and 210. In hypothesis testing, you're taking information from a data set, a sample, and you're making inferences about your population. What you're trying to do is make a decision based on this information, and hopefully that decision matches up with the true state of nature, what is actually occurring. So ideally with hypothesis testing, you're getting accurate enough information that you can draw a correct decision. So if you know a hypothesis is false, you want to reject the null hypothesis and come to that decision. In addition, if your null hypothesis is true, you want to come to the correct decision by failing to reject the null hypothesis. Unfortunately, that's not always the case, and you have different error types. In this topic, we'll explore type 1 errors, or alpha risks, and type 2 errors, also called beta risk. Type 1 errors, alpha risks, occur when the true state of nature is that your null hypothesis is true, but you reject your null hypothesis. It's like a false alarm. This is the risk that you're willing to take in rejecting the null hypothesis when it's actually true. Sometimes it's also called the producer's risk, because this is the risk of thinking that a product is defective when it's actually good, so you throw the product away. Thus, it's a risk that a producer takes. The common value for alpha is 0.05, which means you have a 5% possibility of committing a type 1 error. Now, it's important to understand the difference between your significance level and your confidence level. When you're plotting your values to understand where the significance level reaches, you have a critical value, and it's above this point where you have a threshold that delineates the regions of acceptance and rejection for that test statistic. Your region of acceptance is a region where the set of values of the test statistic for which you fail to reject the null hypothesis fall in this range. And then within your rejection region, these are the set of values of the test statistic for which the null hypothesis is rejected. Depending on where your test statistic falls, it's either within the rejection region or the acceptance region. And this is all based on your alpha value, which is your significance level, which again is typically 0.05. Your confidence level that you're looking for is 1 minus your alpha value, and so in the case of it being 0.05, you're looking for a 95% confidence. Let's go through a quick example of loan processing time and how it applies. And for this company, the director of the Consumer Loans Department at the retail bank claims that the average auto loan processing time is now 8.9 days. And the process improvement team thinks that the processing time has changed over the past few months, because they've been working to automate the processing. So the Six Sigma team wants to test the hypothesis with 95% confidence that the current processing time is now less than the claim. The team collects 20 samples on the processing time, and they set up the data to test the hypothesis. So the processing time is now less than the claimed 8.9 days. For this hypothesis test, the team would use a one-tailed test to test the mean, because you're looking to see if the value is now less than. And in this case, the alpha value is 0.5, so you have a 5% chance that the conclusion to reject the null hypothesis is wrong, and that your confidence level is equal to 1 minus alpha, which is a 95% confidence level that the population mean will fall within that confidence interval. In addition to the type 1 error in the alpha and alpha risk, you also have a type 2 error, which is also known as beta risk. The most commonly used beta risk value is 0.10. Beta risk is similar to the risk of failing to find a defective piece during a quality check or quality control inspection after a product is produced. Another example is the risk of not finding a defect and shipping your defective product off to your customer. This is why it's commonly referred to as the consumer's risk. It's important to understand that beta and alpha are inversely proportional. By reducing your alpha, it increases your beta, and vice versa. In addition, when you look at the power of the test is the test probability to correctly reject the null hypothesis, and the power of your test is determined by 1 minus beta. A key concept in hypothesis testing is power. When you talk about the power of the hypothesis test, this is the test probability of correctly rejecting the null hypothesis. What that means is you're coming out with a correct decision where the true state of nature is that your null hypothesis is false, and your decision is to reject the null hypothesis. In order to calculate the power of your test, the power is calculated as 1 minus beta. This is important because the concept of power helps you to increase the chances of correctly rejecting the null hypothesis, and what you're trying to do is improve the likelihood of finding a significant effect when one exists. There are 4 factors that affect the power of a test: sample size, population differences, variability, and alpha level. First, it's important to understand that as sample size increases, so does the power of your test. So when you can increase your sample size, then you are more likely to get the correct result. And sample size is the most important factor when you're talking about the power of a test. The next factor is population differences. You want to understand what the difference is between your two populations. When there is a bigger difference between your two populations, then the power of your test increases. Because there are bigger differences, it's much easier to tell there's a difference between those two populations. However, when there's little difference between your two populations, the power of your test decreases, since you're reducing the probability that you're going to be able to detect the differences within your test, because there's overlap between these two populations. The third factor is variability, which is a measure of the dispersion of your values. When you have less variability within your samples, then you have more power. And when you have more variability within your dataset, you have less power. So these two factors are inversely proportional. Finally, the fourth factor that affects the power of a test is the alpha level. When you're setting up your hypothesis test, the alpha level is something that, as you're running the test, that you can set. If you had two distributions that are identical, then the distributions are the same. But by simply changing the alpha value from 0.05 to 0.01, you can significantly change the result of your hypothesis test. You can change from the do not reject or fail to reject the null hypothesis, to rejecting the null hypothesis, simply by changing the alpha value. The most common value is 0.01, but decreasing or increasing your alpha value again can change the overall result of the test when you're comparing your p-value against that value. And so essentially, the higher the alpha value means the higher the power. Sample size is one of the most important factors or considerations when you're talking about power of a test. And it's important as a Six Sigma professional when you're going through and performing your hypothesis test that you're looking at your sample size, since it is the most important factor, and it's something that can be easily controlled. As your sample size increases, the power of your test also increases. But it's also important that when you're looking and conducting your hypothesis test, that you look at calculating the right sample, and it's something that should be considered very carefully. If you decide on too many samples, then you could be wasting time, resources, or money. But on the other hand, if you collect too few samples, then you could actually have inaccurate results. So you want to be able to find that balance between having too many and too little, and get the right amount. And you can determine the right amount by calculating what your sample size should be. As part of this calculation, you need to look at your margin of error. E is your margin of error, and it's calculated using the critical value. And that value is multiplied by the standard deviation and your sample size. What you're trying to do is minimize your margin of error. You can use this equation then to solve for n and rearrange the equation, so that you can calculate how many samples that you should have. As you go through this calculation, it's important to note that your n value should always be rounded up, because you're looking for a certain level of confidence. So, for example, even if you get a sample size that's 233.1, you would always want to round that up to 234, and that guarantees that you have your level of confidence. So let's explore an example of how you would calculate the sample size. Let's suppose that you are conducting a study for a local cable TV provider, and you want to understand how much time a family is spending watching TV. To do this, you want to calculate your sample size. So you're going to solve to determine what the sample size should be to make sure that you're getting the right representation. As you go through the calculation, you determine that you want to have a confidence level of 95%. And also, based on your experience, you understand and you determine as a team that your margin of error is going to be within 2 hours per week. Also, there was a survey that was conducted recently, and you're able to use that information to get your standard deviation, or a sigma value from your historical data of 22 hours per week. And finally, you want to find your z-value, and in this case, you're using a two-tailed distribution table. So you're looking at a z of alpha over 2, or a 95% level of confidence, and that value from your table is 1.96. So using this information, you can go through and you can solve for n. And you know your z-value for alpha over 2 is 1.96. Your standard deviation is 22, and your allowable error is 2. As you go through and you calculate that, your n value is 464.8336. Now, it's important that you always round up, So you would round this value up to 465. What that means then, if you collect the data from 465 families, we'll be 95% confident that the sample mean will fall within 2 hours of the true population of TV viewing. Hypothesis testing is comprised of 5 steps. Establish your hypothesis, determine your test considerations, calculate your test statistic, calculate your critical value or your p-value, depending on which method you use, and interpret your results. In this topic, we'll walk through each of them. In the first step, you're determining what your null hypothesis and your alternative hypothesis should be. Your null hypothesis is that the parameters of interest are equal and there is no change or no difference. The alternative hypothesis would be the opposite of this, and so your alternative hypothesis would be that the population parameters of interest are not equal and the difference is real. Next, you need to make sure that you're developing your test consideration, and for this there's 4 key test considerations. You need to make sure that you are selecting the appropriate test statistic based on what you're trying to test. And then you need to make sure that you're identifying the appropriate alpha value, based on the level of confidence you want in your results. You also need to determine the sample size, and conduct sampling to make sure that you get a representative sample of your data. And then you also need to make sure that you're doing the assumption checks. The next step in the process is to calculate your test statistic, which is what you're going to use when you determine your critical or p-values at your next step, and you're going to use this for comparison. There are several different types of test statistics. The ones here shown are z-statistic and your t-statistic, which are the most commonly used test statistics. It's important to make sure you know what type of test you are using, and when you talk about your z-statistic, you need to make sure that your values or samples are greater than 30. And your t-test is typically used when your sample size is less than 30. The fourth step in the process then is to determine what method you're going to use. You could use either the critical value method or the p-value method. If you determine that you're going to use the critical value method, then you would use a table, where you know the degrees of freedom. And then you're looking for what your alpha value is to determine that critical value. Once you have determined the method that you're going to use, then you can interpret the results. For example, if you use the critical value method, you're going to look at your test statistic that you just calculated, and you're going to see how it falls. If it falls in the rejection region based on what your critical value is, then you're going to reject your null hypothesis. However, if it does not fall within the rejection region, if it's outside of your rejection region, then you fail to reject your null hypothesis. So your critical value method is a comparison between where your test statistic falls and if it falls within a critical value, which is your rejection region. If you use the p-value method, then you're going to determine how your p-value relates to your alpha value. For example, if your p-value is less than your alpha value, that means the test is significant, so you reject your null hypothesis. However, if your p-value is greater than alpha, then you fail to reject your null hypothesis. As you set up your hypothesis test, it's important to make sure that you're running the right test, and you're choosing the appropriate type of hypothesis test. You need to understand if you have a one-tailed test or a two-tailed test. With a one-tailed test, you could have a one-tailed test to the right, and with this, what you're testing for is to see whether or not your values are different from each other. For this example, your null hypothesis would be that your mu, your mean, is less than or equal to some other value, and therefore your alternative hypothesis would be that your mu is actually greater than your mu sub 0. And what you're looking for is where does your test statistic fall. Based on your calculation, if you're doing a t-test or z-test, you plot your test statistic to see if it falls into your reject region, or it falls within your acceptance region. And in this example, your test statistic falls into your rejection region, or in other words, your test statistic is greater than the critical value. And so, since it's inside a rejection area, you reject your null hypothesis. Now, you could also have a one-tailed test to the left, and when you're looking at these values, you're trying to see if something has either reduced or it's increased. In this case, you would set up your null hypothesis such that your mu is greater than or equal to a hypothesis value. In this case, it's actually greater than your critical value, and it falls within your acceptance region. Because of this, you fail to reject the null hypothesis. The next type of test you could have is a two-tailed test. Typically, when you're setting up a two-tailed test, you're looking to see if there's a change. So your null hypothesis would be that the means of your two values are equal to each other. And then your alternative hypothesis would be that the means are not equal. Since your values could not be equal, that means it could fall above or below that value. So this is why you would do a two-tailed test, because the values could fall in either rejection region. In this case, your test statistic falls within the acceptance region, and therefore you would fail to reject the null hypothesis. Once you've determined the test statistic and your alpha value, the next step you need to do in hypothesis testing is to decide which method you're going to use to compare your desired confidence level to the test results that you're going to apply. This is either going to be the critical value method or the p-value method. For the critical value method, you're comparing your test statistic to your critical value, and then you're looking to see how your test statistic compares to that critical value. This is determined based off of your alpha value. The critical value is really what divides the curve area into your rejection region and your acceptance region. If your test statistic falls in the rejection region, then you're going to reject your null hypothesis. However, if your test statistic falls within your acceptance region, then you're going to fail to reject your null hypothesis. A critical value method gives you a graphical representation of how the process falls. The same method would apply with a two-tailed test. The difference would be that you have rejection regions on both sides, both ends of your distribution. The next step would be to use a z-distribution table to find the critical value for a given alpha value if you're using a two-tailed test. And just because it's a two-tailed test, you need to make sure that you're not forgetting to add in a plus and a minus sign. For example, with a value of 1.96, you have a value of 0.4750. When you set up a critical value for z of minus 196 and plus 196, you're going to have your comparison based on these two critical values, which would be plus and minus. This is used to signify the critical regions on both the left and right-hand sides of your curve. Now, the p-value method is typically the most commonly used method within hypothesis testing. You'll see it frequently in statistical software such as Minitab, and it gives the test results in the p-value format. When you do this, you're comparing your alpha valued or alpha range with your p-value. And if your p-value is greater than or equal to alpha, then you fail to reject your null hypothesis. Conversely, when you compare your alpha value to your p-value, if your alpha value is less than or equal to alpha, then you reject your null hypothesis. And a simple way to remember that is if p is high, null will fly. If p is low, null will go. Within hypothesis testing, one of the most commonly used types of test is test for means. When testing for means, you can have one sample or two samples tests, and depending on the types of tests, there are various statistics that we'll use or test statistics that we'll use for those. When you're performing a test for means, when you have a one sample test, if you have a known population variance or your sample size is greater than or equal to 30, then you're going to use your z-test. If your population variance is unknown or your sample size is less than 30, then you use the t-test. For your two-sample test, if your population variance is known or if your sample size is greater than or equal to 30, then you're using your z-test still. However, with your two samples, if your population variance is unknown or your sample size is less than 30, you'll have a situation where either your variance is assumed to be equal or unequal, and so you'll use the pooled t-test and non-pooled t-test. And it's important to note here that when you're setting up for your test for means, if your variance is unknown or your sample size is less than 30, then you're going to use a t-test. If your variance is known and your sample size is greater than or equal to 30, then you can use the z-test. And most commonly, what you run into is selecting your test based on your sample size. Let's use an example of your one sample test for means at a retail bank process, in which the Consumer Loans Department claims that the average auto loan processing time is 8.9 days. But as a Six Sigma team, you believe otherwise. So you want to test the hypothesis that the auto loan processing time has changed, since the application process has now been automated. You're going to set up your null hypothesis that the mean is equal to 8.9 days. And then your alternative hypothesis will be the opposite. It will be that the mean is not equal to 8.9 days. Then the next step in the process will be to go through and perform your test considerations. And to do that, you would go through and look at what you are changing within your processing time within your loan application. Because you're not specifying the direction of change or the processing time, the change could be greater than or equal. You're going to use a two-tailed test. You create a sampling plan, so you're going to go through and collect 20 samples. You can calculate your degrees of freedom as 19, because it's the equivalent of n-1, and you can have 20 samples, so your degrees of freedom is 19. Your population standard deviation is an unknown, but you're going to assume that the data is numerical, that it's randomly selected, and that it's normally distributed. You can determine that you're going to test your hypothesis with 95% confidence, which means your alpha value will be 0.05, since you're looking for a 95% confidence. The next step in this process, then, is to calculate your test statistic. Since you're using 20 samples, and your number of samples is less than 30, you're going to calculate your t-statistic. You know the mean from your 20 samples, and that's been calculated from the data table, and that value is 8.54. So you can plug that value in for your x-bar, and using that same information, you can calculate your sample standard deviation and find that the value is 2.96, and your number of samples is 20, so you can replace your value for n with 20. And then your mu sub 0 is 8.9, because you're testing to see if the value is equal to 8.9. And then by solving for t, you get a test statistic of minus 0.54. And so now you can compare your test statistic value, your negative 0.54, to the critical value for 19 degrees of freedom and a significance value of 0.025, which is your alpha over 2. Using the table, you can find your degrees of freedom of 19 and your alpha over 2 value of 0.025. Since it's a two-tailed test, you're taking half of the 0.05, and that gives you your critical value of 2.093. Now, if you would have used the table, you could also have manually found the p-value. If you had done that, the test statistic value of minus 0.54 corresponds to a p-value that's close to 0.6, because your value of 0.3 is the one side of the test. So 2 times 0.3 gives you a value of 0.60. Since a test statistic of minus 0.54 is within the acceptance range, and it does not fall within your reject range, then you fail to reject your null hypothesis. The result would have been the same with the p-value method, because the 0.60 is higher than 0.05. Now the procedure is essentially the same when you have a sample size over 30, but instead you would solve for your z-test statistic. So in this example, you would have a seed producer that claims that the average weight of a packet of seeds is 1.5 grams. And you think that the new machine may not be calibrated correctly, and the average weight of seeds has changed. And so from that you can set up your hypothesis, where the mean weight is equal to 1.50 for your null hypothesis. Then your alternative hypothesis would be that the mean weight is not equal to 1.50. You can solve and find out that the mean value for your 75 samples is 1.48 grams. The population standard deviation is 0.2. Since your claimed mean is 1.5 grams, when you input the value for the test statistic, you get a value of minus 0.869. You can use the z-table to then find your critical value. Now the value for alpha was previously set at 0.10, which is a 90% confidence level. And then the corresponding critical value is 1.645. So you can use that information to compare your test statistic to your critical values. Since your test statistic of 0.869 is within the acceptance region, and it does not fall within your reject region, then you fail to reject your null hypothesis. In other words, the claim of the average weight of a packet of seeds is 1.5 grams, and it's held valid with 90% confidence. A two-sample test for means is very useful in comparing the means of two samples. It's commonly used when you're comparing two different products or two different processes that are producing the same product, to see if there's a difference in the means or the outputs, or for comparing two different suppliers. When you do the two-sample test for mean, the difference is whether or not you're looking at pooled or non-pooled statistical tests. There are several assumptions that you need to make about your samples. They must be independent, random, follow a normal distribution, and have either equal or unequal variances. With your two-sample test, the differences depend on whether or not the population variance is known or unknown. If the population variance is known or the sample size is greater than or equal to 30, then you would use the z-test. If the population variance is unknown and the sample size is less than 30, then we'll use the pooled t-test. And this is used when your variances are assumed to be equal. So now, let's explore how you would set up the hypothesis test for a two-sample test for the mean using an automotive manufacturing example. So let's suppose you're working for this auto manufacturing company and you're analyzing the root causes for excessive variation in the quality of the manufacturer's seatbelt. Based on the initial analysis, you determine that the problem lies with the seatbelt's braking strength. So you're going to set up a hypothesis test to focus on the braking strength and to see if there's a difference between the means of two samples in the braking strength. For the seatbelts, you have two different suppliers, and so you want to determine if there's any differences in the strength of the seatbelts based on these two suppliers. You're going to initially test this and set up your hypothesis test. You're measuring to see if the first supplier's seatbelts are stronger than the second's. So to do that, you set up your null hypothesis, where the mean of A is equal to the mean of B, and the mean of A would be your supplier A, and the mean of B would be supplier B. And then your alternative hypothesis would be that the mean of A is greater than the mean of B. As you set this up, you need to set up different test parameters, and as a Six Sigma team, you need to decide that you want to set your alpha value at 0.10 because of how you have your null hypothesis, and more importantly, your alternative hypothesis test setup. You're performing a one-tailed test to the right, because your alternative hypothesis is stated such that the mean of A is greater than the mean of B. And for each supplier, you have data. You have 15 data points from supplier A and supplier B. Because of this, you can determine that your degrees of freedom equals the 15 from both samples, which is 30 minus 2, because you lose a degree of freedom for each supplier, and so your degrees of freedom is 28. So then you can take this information and you can calculate your test statistic. You have the two suppliers, supplier A and supplier B, and you've got the number of samples. In this case, it's 15 samples from each supplier. You can calculate the mean for both suppliers and the standard deviation for both suppliers. And since you're looking at the mean for the two samples, you would go through and you would use the two-sample t-test for pool values, because you can take into account if there's differences in the number of sample sizes, differences in the means, and also differences in the standard deviations. Your pooled two-sample t-test then takes into account the differences between your number of samples and your standard deviation. So by using this information from both suppliers, you're able to calculate that your pooled standard deviation is 2.399. Then using that information, you can calculate your t-test. With your t-test, you're pulling the averages for each sample, and you're using your pooled standard deviation and your denominator plus the differences, in case you have a different number of samples for each one. And so your t-value, when you plug in the numbers, becomes 5.06. The next step in the process is to find your critical value using your t-distribution table. When you do this, you know your degrees of freedom is 28, because you have 15 samples from each of your suppliers and you're subtracting 2, because you had two different suppliers. And so you find your degrees of freedom of 28. And then you set your significance value of 0.10, and so that gives you your critical value of 1.313. And so now you can go through n users' values to determine the results of your hypothesis test. And in this case, your test statistic value is 5.06 based on your calculations, and your critical value is 1.313, which came from your distribution table. Since your test statistic value of 5.06 is more than your critical value of 1.313, you reject the null hypothesis, because your test statistic is within your rejection region. By depicting this graphically, you're able to determine that you should reject the null hypothesis. In other words, what that means for your results is that a 0.10 significance level. Your data indicates that the seatbelt supplied by supplier A can sustain a higher braking force than a seatbelt supplied by supplier B. And so your null hypothesis is rejected, and your alternative hypothesis holds, which stated that the mean of A is greater than the mean of B. In this topic, we'll explore the two-sample t-test for means with non-pooled data. So let's consider that you're comparing the average call time between the day shift and the night shift at an inbound call center for an electronics manufacturer. You suspect that the average call time difference between the two shifts is different, so you're going to call these Shift 1 and Shift 2, and you're assuming that they're equal. So you set up your hypothesis such that your null hypothesis is that the mean of Shift 1 is equal to the mean of Shift 2. And your alternative hypothesis would be that the mean of Shift 1 is not equal to the mean of Shift 2. As you set this up, you have several considerations that you need to determine as a Six Sigma team. Now for these two shifts, your population variance for each shift is unknown, but you're assuming that it is unequal. With your considerations, you would have set up your alpha value of 0.05. You would have a two-tailed test, because your alternative hypothesis is that they are not equal. Therefore, you'd use an alpha value over 2, and your alpha value would be 0.025. For your first shift, you have 16 data points, and for your second shift, you have 12 data points. The next step in the process would be to calculate your degrees of freedom. And in this case, because you're using non-pooled data, calculating the degrees of freedom is significantly more complicated. You'd want to compare the differences between the two shifts, like the number of samples per shift and the standard deviation per shift. Your degrees of freedom would be calculated by adding the standard deviation from Shift 1 plus the standard deviation from Shift 2 and squaring that summation, and dividing that by the variance from Shift 1 divided by the number of samples from Shift 1 minus 1. That would then be added to the variance from Shift 2, divided by the number of samples from Shift 2 minus 1. Using the values from the table, you could pull these values in and calculate your degrees of freedom equal to 25.9. The next step in the process would be to calculate your test statistic. Since your sample size for each is less than 30, you're using your t-statistic. Your t-statistic is calculated by subtracting the average of Shift 2 from the average of Shift 1, and dividing that value by the square root of the variance from Shift 1 divided by the number of samples from Shift 1, plus the variance from Shift 2 divided by the number of samples from Shift 2. And using the values from your table, you would pull those numbers in, and your test statistic value would be minus 1.36. Next, you find the critical value and compare that to your p-value. With your degrees of freedom, you take your value of 25.9. And when you're talking about the degrees of freedom, you would want to use the most conservative value. So you would round that down to a value of 25. And when you look at your distribution tables, then you would find your degrees of freedom for 25. And your significance level, since it's two-tailed and it's alpha over 2, you're looking at alpha value equal to 0.025. And that gives you your critical value of 2.06. The next step in the process is to compare your p-value of 0.19 to your alpha value of 0.05. Graphically, you could take a look at how your test statistic matches up to your acceptance and your rejection region. Since your test statistic value of minus 1.36 falls within your acceptance region and does not fall within your rejection region, then you fail to reject the null hypothesis. Now, it's important to note that for your p-value, the data indicates that the difference in the average call duration on the first shift and the second shift then are not statistically significant. You're comparing your value of 0.19, which is greater than 0.05. So regardless of the method that you use, you end up with the same conclusion. At an alpha value of 0.05, your data indicates that the average call durations of the first shift and the second shift are statistically similar. And there's only minor differences that appear in the samples, and these can be caused by natural variation. but they're not statistically significant. Hypothesis testing is used within Six Sigma mainly in the analyze phase. It's used at this point in the domain methodology in order to test to see if there's been differences within your means or variances. You're also trying to determine if there's been changes in your processes, if that's made a difference in your overall outcome. Hypothesis testing can be used to answer questions about your processes. For example, from a service perspective, you could use it to figure out if one courier company delivers more consistently than another company. Or you could examine two molding machines to see if they're producing the same proportion of defective items. In addition, you could also look at if the proportion of people over 50 who purchase a particular journal has changed over time. So essentially, you can use hypothesis testing to determine if there's a difference in terms of whether values have changed, or if they're equal to the same value over time, and to test if variances or proportions have changed over time. There are 5 key steps in hypothesis testing. First, you set up your null hypothesis and your alternative hypothesis, and these values should be mutually exclusive, meaning that there should not be any overlap between how you set these up. The second is to figure out your test considerations. In your test considerations, you're determining what the alpha value is and what the degrees of freedom value is for your calculations. The next step is to determine your test statistic. And your test statistic is calculated based on the type of hypothesis test that you're using. In the fourth step, you compare your critical value to your p-value. And finally, in the fifth step, based on the comparison findings, you interpret the results. There are several different types of hypothesis tests that you should be aware of. They include the paired comparison t-test, test for variances, the test for proportions, analysis of variance, the f-test, and the chi-square test. Each of these has a slightly different aspect that you're trying to test. For example, with your paired comparison t-test, you're comparing two different samples. But within these samples, one sample from one grouping has a natural partner within the other sample. In addition, you could look at the differences within your variances to see if you're reducing your variation, or if your variation has changed. You could also look at the difference within proportions if you're looking at defect rates, and so forth. In this topic, we'll explore paired comparison t-tests. In a paired comparison t-test, you're looking at data that's been paired through the same set of subjects. So the datasets are really connected to each other, and they're not independent, they're dependent, because there's a corresponding dataset for each data. So let's examine a few examples to understand what that really means. You could use a paired comparison t-test when you're evaluating before and after effects, assuming that these are coming from the same subjects. You could also compare gas mileages for the same model of car, because you're comparing the same model. You could also use a paired comparison t-test when you're looking at quarterly test results for different classes, but you're looking at it for the same teacher, and so that would give you your connection between the datasets. And finally, another example would be if you're looking at the same task that's being performed manually and automatically, because you're looking at the same task. It's important to note that the paired comparison t-test is very similar to the two-sample t-test for means. The big difference, though, is that the data is paired rather than being independent. For example, if you have a group of patients that get a new medication to reduce their blood pressure, the same sets of patients are tested before and after. Now, the two datasets would be dependent because they're connected through the same patients, and therefore you would use the paired t-test. However, you could also look at this from a two-sample t-test. For example, if you have a group of patients with a new medication that's compared with another group of patients that does not take the new meds. In this case, the two samples are independent, and they're not paired because you have one group that takes the medication and one group that does not take the medication. And in this case, you would use a two-sample t-test because they're independent and not paired. Paired comparison t-tests have several key characteristics. First, this type of test works really well when you're doing a before and after comparison, because you're looking at that from the perspective of the same person, or the same machine, and things like that. The paired comparison tests also work very well when your data is organized in pairs. It's important to note that when you're looking at your data in terms of pairs, there would be that dependent aspect of it as well, that linkage or that connection that these values, these data points, would be connected. And because you're looking at paired data sets, the data sets should be the same size. Essentially, what you're doing then is you're testing the differences between the pairs. You could use the paired comparison test when you're looking at the number of defects produced before and after installing a new machine. And in this example, you would have the before and after, and that same aspect is the same machine. You could also use the paired comparison test when you're comparing the responses of an interview from before and after a change is made. Or you can measure the number of complaints received before and after a training program has been implemented. In this topic, we'll explore how you conduct a paired comparison t-test. So let's say you have 10 high schools that you're comparing within a school district. They launched an early intervention program to tackle the issue of increased dropout rates, and they monitor the effect of that program over 2 academic years. You want to compare the dropout rate before the intervention and the dropout rate after the intervention. And with your hypothesis test, what you want to do is test to see if the program helped in bringing the dropout rates down for these schools. And so looking at those values, one of the first steps of the process is to calculate the differences between the before and after. The next step in the process is to set up the 2 hypotheses and the various test parameters. Since you're looking to see if there's a difference, you're going to set up your null hypothesis that the 2 population means are equal. And by saying that the 2 population means are equal, you're also saying that the difference in the means is equal to 0. Therefore, your alternative hypothesis would be the opposite, that the mean difference between these values, the before and after, is not equal to 0. For this example, the schools could be set up with an alpha value of 0.05. For your test considerations, this would be a two-tailed test, because the differences could be that it increased or reduced the dropout rates. And since it's a two-tailed test, you're using alpha over 2, or 0.025 for each tail. And your degrees of freedom would be set at 9, because it's n minus 1, and you had 10 high schools that you're using. And using this information, you would have a critical value of plus or minus 2.26. Now, using the data table and the differences column, you can calculate your test statistic. And in this case, you're calculating your test statistic, or T calculation. It's important to note that as a Six Sigma professional, you need to know what the paired comparison t-test is. But this is more for demonstration purposes, because calculating the test statistic using this formula is outside of the Greenbelt training. But it's recommended that students would use an online calculator or statistical software such as Minitab to actually do this calculation. So with this calculation, you would end up with a test statistic of 2.5. Using that test statistic, you would compare it to your critical value. And by using the critical value method, you would compare your test statistic value of 2.5, which is greater than your critical value of 2.26. You can also look at this graphically, where you compare your test statistic of 2.5, and it falls within your rejection region. And so, based on the critical value method, you would reject your null hypothesis. You could also use the p-value method and compare your p-value of 0.0339, which is less than 0.05. And therefore, based on the p-value, you would also reject the null hypothesis that there's no differences between the before and after student dropout rates. In other words, there's sufficient evidence to support the alternative hypothesis of difference. So you can conclude, based on this analysis, that the intervention has actually reduced the dropout rate at the schools. This is just one example, but it's a great way to show you how useful a paired comparison t-test can be when working on your Six Sigma initiatives. As a Six Sigma professional, it's important to understand the elements of performing different hypothesis testing methods and calculations, including the paired comparison t-test. The reality, though, is that for the sake of your time, you'll most likely use a software to perform your calculations and produce your results. One very common statistical software for Six Sigma is Minitab. In this topic, we'll examine a typical Minitab output of a paired comparison t-test to show how you can use the results and perform a more detailed analysis. We'll use an example in which you've got 10 high schools that you're comparing within a school district. They launched an early intervention program to tackle the issue of increased dropout rates, and they monitor the effect of that program over 2 academic years. You want to compare the dropout rate before the intervention and the dropout rate after the intervention. You're testing to see if the program helped in bringing the dropout rates down from these schools. Within Minitab, there is a plot called the Individual Value Plot of Differences. And within this plot is a graph that you can examine the individual values in each sample, and you can use it to assess your sample distributions. Your null hypothesis from a dropout rate study at the schools was that there was no difference between when the intervention was implemented. When you look at your null hypothesis, you can see that most of the data points fall to the right of your null hypothesis, which is to the right side of 0. And a positive difference indicates that the school dropout rate has decreased, because you're comparing the after to the before. In addition, within Minitab, you can do a paired t-test results table. And within this table, you're looking to see if your p-value is less than your alpha value. And in this case, your alpha value was equal to 0.05, and your p-value is 0.034. By doing this comparison, you would reject the null hypothesis, and you would conclude that there is sufficient evidence to support the alternative hypothesis, that there is a difference. It's also important to note with this table that the mean is an estimate of the population. In this case, before the dropout rate was 6.10, and after the dropout rate was 5.7. So based on your p-value comparison to your alpha value, you can say that your dropout rate has gone down from 6.1 to 5.7. Another point you can examine is your 95% confidence interval for the mean difference. And within your confidence interval, you're saying that 95% of your values are going to fall between that 0.037 and 0.745. Your value of 0, saying there's no difference, doesn't fall within that range, so that's another indication that you can reject the null hypothesis. Paired comparison t-tests are useful in seeing if once an improvement has been implemented, if it's made a difference in your output. In this topic, we'll explore hypothesis tests for variance. Testing for variance is important because within Six Sigma, what you're trying to do is have on-target performance. This is where your tests for means come into play, to see if your mean and your target values are similar. In your test for variances, when you're making changes to your process, you want to see if you're able to reduce your variation within your process, where you have a narrower distribution. You're focusing on standard deviation and variance, sigma and sigma squared. There's 2 different types of tests that you can consider, the one-sample test and the two-sample test. With the one-sample test, you compare the variance in a single population with a specified value. But if you want to determine which of 2 samples exhibits the largest variation or variance, then you could use a two-sample test for variance. This is where the population samples would come from 2 different processes, or from the same process at 2 different times. For example, if you had a before and after improvement initiative, then you would use your two-sample test for variance. Tests for one-sample variance use the chi-square distribution. In chi-square distribution, it's not normally distributed, it's skewed to the right. And one way to remember that is that the skew of the tail is off to the right of the distribution. Let's say a tire manufacturer is developing a new type of tire. The goal is to provide a more consistent overall wear rate. So your engineers might want to determine if the variation of wear in the new batch of tires is smaller than the variation in the current tire that's being produced. So let's determine your hypotheses and test considerations. You would start by setting up your null and alternative hypothesis. The process has been running for some time, and you have a variance of 6.25, and this would be for a critical dimension within your part. In order to improve the throughput of your operation, an engineer increased the speed of the drive motor. And for your new process, you went ahead and collected 33 samples that were randomly selected. Then you calculated the variance from these samples, and you found that the new variance, your new sigma squared, is equal to 6.76. And since you want to compare your new variance to your historical value of 6.25, you would choose the one-sample test for variance, and set up your null hypothesis that the variance is less than or equal to 6.25, and your alternative hypothesis is that your variance is greater than 6.25. For your confidence level as a team, you would set it at 95%, and so your alpha value would be 0.05. And for your degrees of freedom, since you have 33 samples, you subtract 1, and your degrees of freedom is 32. Now, it's important that you also have several test considerations and assumptions with this. One of your assumptions is that your data must be continuous, independent, randomly sampled, and normally distributed. Now, let's calculate the test statistic. And again, since you're using a one-sample test, you're going to use the chi-square test statistic. Since your chi-square test statistic uses your sample variance as squared and your sigma sub-zero squared, which is your specified variance that you're testing against. Take these values and plug the information into your formula, where 6.76 is the value of the new variance that you're comparing with your historical variance of 6.25. You had 33 samples, and that gives you a chi-square test statistic of 34.61. Now that you have that value, you would interpret your results by comparing the value that you find in the chi-square table to your test statistic value. Using the chi-square table, you would find your degrees of freedom at 32, and your alpha value is 0.05. So you would compare your value of 34.61, and since it's not greater than the critical value of 46.194, you fail to reject the null hypothesis. You can conclude with 95% confidence that your data does not support the conclusion that the variance for the process has increased over the 6.25. Alternatively, you can also use your p-value. And doing your calculation here, your p-value would be 0.344, and you would compare that to your alpha value of 0.05. And in this case, your p-value is greater than your alpha value. So because of that, you would also fail to reject your null hypothesis. In this topic, we'll learn about using the two-sample test for variance. When you're using the two-sample test for variance, you're pulling information from two samples. These could be two samples from different populations, if you're trying to see if there is a difference in the variance between those two samples. Or this could be that we've got the same process, and you want to do a before and after comparison. In the two-sample test for variances, you're going to use the F distribution. Using the two-sample test for variance, your first step would be to set up your hypothesis, your null and your alternative hypothesis. So let's explore how this would apply with an example. Suppose you're part of a Six Sigma team in a paper factory, and you're trying to compare the output of two machines. And both machines were built to extract water from pulp. So if you want to see if there's a difference between the variation or variance from both samples, you would set up your null hypothesis such that the variance for machine 1 is less than or equal to the variance for machine 2. And that your alternative hypothesis would be that the variance for machine 1 is greater than the variance for machine 2. You want to know this with a 95% confidence level. Therefore, your alpha would be 0.05. You would set this up as a one-tail test. You want to see the difference if it's to the right, if the tail of the distribution is to the right. Next, you would use your degrees of freedom. In this example, you would pull 25 samples from both pieces of equipment. So the degrees of freedom for each piece of equipment would be 25 minus 1, or 24. Your degrees of freedom for both machines would be 24. Our assumptions would be that the data is continuous, independent, randomly sampled, and normally distributed. The next step in the process would then be to calculate your test statistic. Since you're using the F distribution, your calculation would be where your numerator would be the larger of the sample variances, divided by the smaller of the sample variances. So in this case, you have 6.7 divided by 2.5, and that gives you your test statistic of 2.68. Now you can use that information then to interpret the results. The first step in that would be to find your critical value using your F distribution, and based on your degrees of freedom, since there's 25 samples each, your degrees of freedom would be 24 for machine 1 and machine 2. That gives you a critical value of 2.0050. Since a test statistic of 2.68 is greater than your critical value of 2.0050, you would reject the null hypothesis. You could also compare your p-value to your alpha value. And in this instance, your p-value is really low compared to the significance level, and therefore you would have the same conclusion. So in this case, you would reject the null hypothesis. Using that information, you could state that the variability of machine 1 is greater than the variability of machine 2. Because you're not always dealing with continuous data, it's important as a Six Sigma professional to understand hypothesis testing when you're dealing with proportions. You're using the hypothesis test for proportions when you're testing ratios within a sample. There are several key assumptions when you're using tests for proportions. First, the data should be binary. This should be yes-no, pass-fail type information, and this is commonly what's used when you're talking about defect rates. You also need to assume that your samples are random. Your trials for this test are independent, and then proportions of interest are constant over time, that they're not changing over time. So when you look at the hypothesis test for proportion, there's two different types of hypothesis test for proportions. The first is a one-sample test for proportions. This type is useful if you're looking at your defect rate within your organization, and you want to see if your proportion from defects from one manufacturing line is on par with the rest of the organization. The second type is the two-sample test for proportions, and this is where you're comparing proportions from two different populations. For example, you could compare machine 1 against machine 2 to see if the defect rates are the same. Now, because you're dealing with proportions, it's important to make sure that you have the right sample size, that you have sufficient enough sample size to ensure that you're able to perform accurate calculations. The equation, when you're calculating your sample sizes, you're looking at the minimum of different factors, and you want to make sure it's greater than or equal to 5. So n in your calculation is your sample size that you're solving for. Then, based on what you're testing, you're going to fill in the value of p sub 0 to determine the appropriate sample size. And p sub 0 comes from essentially your pass rate. If you know that over time your defect rate is 10%, you could set up your p sub 0 value of 0.1. If you fill in your p sub 0 value of equal to 0.1, then your n value, your number of samples, should be at least 50. If your p sub 0 value is 0.01, then that means your number of samples should be at least 500. In this topic, we'll explore how to calculate and perform a one-sample proportion test. So let's walk through this with an example. Let's say you're examining loan processing time, and the director of a consumer loans department claims that over 75% of the applications for loans are processed within the accepted time frame of 9 business days. However, the process improvement team within the bank thinks that this value is actually much less than the 75%. So to test this hypothesis with a 95% confidence, the team goes through and records sample and collects information on 25 different applications. The team looks at the data, and they test the assumption that the data is normally distributed, random, independent, and has constant variance. And because these assumptions are met, they can move forward. Now, the next step in the process is to also make sure that they have sufficient information. So when you look at the sample size, since you have 25 samples that we've collected, and you're testing the hypothesis of 0.75 or 75% of the application received within that time, then that gives you a value of n times p sub 0 of 18.75. Then you use the n times 1 minus p sub 0, which gives you 25 times 0.25 and a value of 6.25. You could compare that to the minimum value of 5, and since 6.25 is greater than or equal to 5, you've met the condition with your sample size. Now the team is ready to move forward with the hypothesis test, and you set up the hypotheses, where the null hypothesis is that the p-value is greater than or equal to the claimed value of 75%, or 0.75. And the alternative hypothesis is that the actual p-value is less than the assumed value of 0.75. Based on this setup, this is a one-tailed test. Since you're performing a one-sample test, the equation that we'll use is your z-test statistic. You use your p prime value, which is a sample proportion, and you subtract p sub 0, which is your hypothesized proportion, 0.75. Then your sample size is 25. So using that information, you would plug it into your test statistic calculation, and you would get a test statistic of negative 1.27. Now that you have that information, you can interpret your results. When you use the z-table, since you're using an alpha value of 0.05, your critical value is 1.645. So you can compare your test statistic of negative 1.27, and it's less than the critical value, which means it does not fall in the rejection region, and therefore the test fails to reject the null hypothesis. You can also look at it in terms of the p-value. So when you take your test statistic value of negative 1.27, and when you compare that value to your z-value of negative 1.645, then you further validating your test, and you can state that you fail to reject your null hypothesis. In this topic, we'll examine the two-sample test for proportions. This type of test is used when you're comparing two different populations to see if there's a difference within those proportions. Let's explore how to perform this calculation using an example. So let's suppose that you're a part of a Six Sigma team analyzing the call durations of the night and day shifts at an inbound international call center. You have information from the day shift and the night shift that you're trying to compare. The goal is then to determine whether there's a significant difference between the proportion of escalated calls in the two shifts. And for an escalated call, that means that it's something that the operator has not been able to handle, that it's been escalated up to the next level or next tier. To perform this task, the team's going to take 400 samples from the day shift and 300 samples from the night shift. Of these samples from the day shift, 25 were escalated, and 42 were escalated in the night shift. The team needs to understand if you can infer from the samples that, on a whole, the escalations for both shifts are different. So you're going to set up your hypothesis, such that your null hypothesis is that the two proportions are equal, and your alternative hypothesis is that the two proportions are not equal. Given this information, you would have a two-tailed test. So now, let's take a look at how that would work. You would use the z calculation, which is equal to, in your numerator, p1 prime minus p2 prime, over p sub p prime times 1 minus p sub p prime. You then take the square root of that value, and it's multiplied by the square root of 1 over n sub 1 plus 1 over n sub 2. The prime sub p value is equal to x1 plus x2 over n1 plus n2. So then, using this information, you could interpret your results. The alpha value is 0.05, and the p-value is 0.00056. And since your p-value is less than your alpha value, you're able to compare these two values. And you're going to reject your null hypothesis, because your p-value is less than your alpha value. What that means then is that the proportion of your escalated cases in the day shift is significantly different from those in the night shift. So practically speaking, there's something other than just random or mere chance happening in this difference. So the Six Sigma team needs to go back and look at what is the difference between the day shift and the night shift. In this topic, we'll explore analysis of variance, or Anova. Anova allows you to test the differences between two or more means. Your null hypothesis mean, as you perform an Anova, is that all of your means are equal. For example, if you're examining an attribute of a material that's supplied by 4 different suppliers, and you want to see if there's a difference between the means amongst these 4 different suppliers. Then, if there's a difference, you can determine which one has the best mean. You can also use Anova to test, for example, different levels of temperature. You could have 3 different levels of temperature, and you want to see which one affects the moisture content of a product most significantly. In Anova, there are several key concepts you should keep in mind. First are the 3 attributes of Anova. They are factor, levels, and response. Factors are the different aspects, so if you think back to your product where you had 4 different suppliers, you could have your factor that would be your supplier. Levels would be your different suppliers. In this case, you have 3 suppliers, supplier A, B, and C. Your response is, what is that customer characteristic that's important that you're trying to improve? And in this case, it could be density, and you could be looking at the mean from each of those 3 suppliers in terms of density. Another important concept in Anova is the type of Anova to use. You can have one-way ANOVA and two-way ANOVA. When you talk about a one-way ANOVA, you're looking at really one factor. For example, you could look at variation amongst different treatment means, and you could look at the variation within treatments, or the experimental error. With two-way ANOVA, you could look at two factors. For example, you could have factor A and then factor B, and you could be testing your experimental error. Another ANOVA concept to keep in mind is where the variation is. You can have variation within group or between group. You can get useful information about where the differences are coming from. For example, if you have 5 different machines that you're determining where the variation is within your process, you could look at your output of uptime, and then for each machine, for example, with machine 1, you could look at that variation in your uptime. That would be within group variation. Perhaps machine 2 has a longer spar, so it has the most variation. Alternatively, you could also look at between group variation in your process by plotting the average and examining the difference between each of those 5 machines. One other key ANOVA concept is that you use your F statistic. The F statistic is a ratio of the between group variation and the within group variation. In between group variation, you're looking at the sum of factor-related variance, and when you look at the within group variation, you're looking at the sum of the error-related variance. In this topic, we'll go through an example of conducting a one-way ANOVA test. So let's consider a large insurance company that's looking at their automobile insurance claims. These claims are processed at 5 centers internationally. You want to determine what the impact has been of a process improvement project that was initiated to determine the average processing time. You want to know if it's the same for all 5 centers, or if there's differences between those 5 centers. You would start by setting up your hypotheses. Your null hypothesis would be that the means of all 5 centers are the same, and your alternative hypothesis would be that the means are not all equal, that at least one is different. You want to know this with the 95% confidence, and therefore your alpha value would be 0.05. And since you're looking to see if your means are equal or not equal, then you're looking at both tails of the distribution. So it's a two-tailed distribution. And then with this, we'll also need to look at the degrees of freedom. Now, with a one-way test for ANOVA, you also have several assumptions. You're assuming that the samples are random, independent, normally distributed, and have constant variance across all of the factors. So now that we've set up your hypothesis test, let's go through and calculate the test statistic. It's important to note that as a greenbelt, you would need to be familiar with the table and the key terms, but you would typically not have to actually perform any of these calculations that are in the table. You would typically be using statistical software such as Minitab. Within this table, you're looking at your sources of variation, which are between treatments and within treatments. As a part of your calculations, you would be looking at your sum of squares and your degrees of freedom. Then you're identifying your mean square and using this information to calculate your F-test statistic. Now, in order to understand some of these calculations, you need to understand some of the basic variables. When you talk about the number of readings, since you have 5 different centers and you're collecting 7 pieces of information, your capital N is your number of readings. Your lowercase n is your number of readings per level. You're getting 7 samples, or 7 observations per center, and K is your number of levels of treatments, and you have 5 centers. When you examine your between treatments, your degrees of freedom is K minus 1, and since you have 5 centers, it's 5 minus 1, which equals 4. Within treatment, you're taking your number of readings minus your number of levels, and so your degrees of freedom is 30. Using this information, you find your critical value. For your critical value, you're going to use your F distribution table. And your first degrees of freedom that you looked at was 4, since you have 5 centers and you lose 1 degree of freedom. Then you calculate your second degree of freedom. That comes from your within treatment, and that has a value of 30. Using that information then, you get your critical value of 2.6896. Now, you can use that information to interpret your findings. So you're going to compare your F statistic to your critical value. In this case, your F statistic is less than your critical value. You're going to fail to reject your null hypothesis. And you could also use the same thing for looking at your p-value, and by comparing your p-value to your alpha value. Since your p-value is greater than your alpha value, you also fail to reject your null hypothesis. What this means is, you could state that since the null hypothesis is retained, you could infer that the average processing times at the 5 centers are equal to each other. In other words, there's no statistically significant difference between the average processing time at those 5 centers, and any difference that you're seeing is due to chance. In this topic, we'll explore the chi-square test. The chi-square test has other uses beyond just using it for one sample test for variance. You can also use the chi-square test to determine whether variables of one categorical variable are related to levels of another categorical variable. So, for example, if you're looking at sales within an organization, you could look at the sales of 3 different products, and you could look to see if there's a difference between the region and where they're being sold. You could also use this information in terms of whether or not there's a specific customer complaint that's related to a specific region, or if there's a type of defect or error that occurs more frequently on a particular shift within a particular department, or even within different operators. And so this is where the chi-square test is very useful. Now, with the chi-square test, there are several assumptions. First, you're assuming that data is randomly selected. And with each population, you need to have a sample size that's greater than or equal to n times 10. The test is not useful for continuous data, so you need to make sure that your variables are discrete or categorical. Finally, you need to ensure that your frequency count for each cell of a table is greater than or equal to 5. Now, with the chi-square hypothesis test, you have 2 possible hypotheses. The first one is that the null hypothesis states that there is no relationship between the variables of interest and the population. Your alternative hypothesis would state that the variables are related and they are dependent on each other. You measure this relationship in terms of the chi-square test statistic. So if your chi-square test statistic is equal to 0, then that means that the observed and the expected frequencies agree exactly and they're independent. If the chi-square test statistic is greater than 0, then that means they do not agree exactly. The larger the value of your chi-square test statistic, then the greater the discrepancy between your observed and your expected frequency. This type of discrepancy indicates some effect or dependency between those variables. In this topic, we'll go through conducting a chi-square hypothesis test. In a chi-square hypothesis test, it's very useful to set up your information in a tables-type format. So let's say you're part of the team within a pharmaceutical company, and you want to determine whether the distribution of side effects of medication varies amongst patient types. So you would have information about your various side effects, and then you would want to compare that against your various types of patients. Within this table, we've captured what type of information that we've observed. You can get values of the expected frequencies. Let's examine a below-average weight patient and whether or not they're expected to experience fatigue. So in this table, if you look at what we've observed based on your data, you had 20 patients that were below average weight that experienced fatigue. You can now explore what you would expect to see. To do that, the first thing that we'll determine is the probability of each effect. We then calculate what your expected values would be for fatigue patients below the average weight. You could take that total probability for fatigue, which is 0.21, and you could multiply that by the number of patients in the below average weight category, which was 113, and that gives you an expected frequency of 23.7. Now, as you set up your hypothesis test, you would need your key test considerations. So you would start by setting up your null and your alternative hypothesis. Your null hypothesis would be that the side effects are not dependent on the type of patient. And your alternative hypothesis, then, would be that your side effects are dependent upon the type of patient. Since you're dealing with medical information and medical practices, you want to have a high level of confidence. So in this example, we're going to say that you're looking for a 99% confidence level, which would change your alpha value then to 0.01. For this test, you're looking for a one-tailed test. Then your degrees of freedom is calculated slightly differently. you would look at your rows minus 1 and multiply that value times your columns minus 1. Since you had 4 rows and 3 columns, your degrees of freedom is 6. The next step in the process is to calculate your test statistic. And if you think back to the patients with fatigue in the below average weight calculation, you had what you observed, which was a value of 20, versus what you expected, which is a value of 23.7. So your chi-square test would be calculated by looking at the summation of the observed minus the expected value squared, divided by the expected value. So, going back to your patients with fatigue that are below average weight, this would be 20, minus 23.7 squared, and then divided by 23.7. And that gives you a chi-square statistic of 0.58. Now, you would do that same calculation for all of the different types of side effects and the different types of patients, and your total chi-square value would then be 1.76. Once you have that information, you can interpret the results. On your chi-square table, you find your degrees of freedom, which was 6, and then you find your alpha value, which was 0.01, and that gives you a critical value of 16.812. In this case, your rejection region is to the right of this number, because the test statistic value is greater than 0. Your test statistic value was 1.76, which you're comparing to your critical value. And since your test statistic value is greater than 0 and is in the rejection region to the right of the critical value, you're going to fail to reject your null hypothesis. And what you're saying then is that the side effects and the patient types are independent. Another way that you could say this, that based on the results of this test, you could say with 99% confidence that there's no relationship between the side effect type and the patient weight category. Design of experiments, or DOE, is a way to make systematic, intentional changes to input variables to measure the impact it has on output variables, the dependent variables. It's very useful within Six Sigma because you typically have multiple factors identified that could potentially impact your output. DOE is used to reduce the number of input variables and determine which ones really have the most impact on your process. Then, by using that reduced set of variables, you can optimize your process and determine what those key settings should be to get that desired output. DOE is typically used in the analyze and into the improve phases of the DMAIC methodology. In the analyze phase, you start to identify some key factors. At this point, you may have multiple factors that you believe impact the output of your process. You can take that information into your improve phase, and this is where you can use the design of experiments. You can determine what factors you need to focus on and how much. You can use this information to improve your process and analyze those key input variables to determine which are important and what settings you need to have those at. Based on that, you can generate solution ideas using the best combination of input variable settings to optimize a response. And once you have those, then you can test, implement, and validate your process improvements. There are 3 types of experiments included in the DOE methodology. The first type is a screening experiment. Typically, when you get to this stage in your Six Sigma project, you have multiple input variables. Screening experiments, then, are used to determine which of those input variables or factors really affect your output or response. And so, the goal of the screening experiment is to reduce your number of factors and take it down to those key factors that really make a difference. Ideally, you want to get down to your probable factors of a maximum of 2 or 3 that are strongly related to the response. That helps to make sure that your design of experiments is manageable and more cost-effective. The next type of experiment is your optimization experiment. And with your optimization experiment, you're trying to optimize your factors that are left to make sure that you're getting that output, that desired output. And so, you're going to adjust those different factor levels that were identified during the screening tests. The third type of experiment is a robustness experiment, sometimes called confirmation experiments. This experiment is used to ensure that your redesign process is robust, or in other words, make sure that it's stable, and that you're going to be able to sustain those gains and you have the correct output that you're searching for. We've just examined the 3 types of experiments, so now let's explore the 3 types of experimental designs. The first type of experiment design is the OFAT, which stands for one factor at a time. And this is used when you've got one factor. In this example, the material weight is your factor, and you're running at two levels, a high factor level and a low factor level. And in this case, since it's one factor at a time, you're using a full factorial design. So you have 4 different runs and you're using every possible setting. The next type of design is full factorial. And with your full factorial, you're using all of your settings for all of your variables. In this example, you have 3 factors: material weight, material density, and temperature. Since you have 3 factors and each of these factors run at 2 different levels, then you have a total possible number of runs of 8 different runs. And so, you're running all 3 factors at 2 levels at every single possible combination. The third type of experimental design is the fractional factorial. With the fractional factorial, you're using a reduced set, so you're essentially taking that full factorial and cutting it in half. You're still using those 3 factors of material weight, material density, and temperature, and each of those is still at 2 levels. But now you're going to do 4 runs. That helps to make sure that you're still able to change the response of all of your factors by changing their levels. But you're doing it with a reduced number of runs, and you're not using all factor level combinations. DOE offers multiple benefits. First, because you're able to test multiple factors at once, it's very efficient and cost-effective versus testing each individual factor one at a time. This allows you to test many factors and evaluate those simultaneously. By evaluating factors simultaneously, you can understand and quantify the interactions that might be occurring between various factors, and how these impact the response. You'll also be able to distinguish the importance of these factors against each other. DOE is also very useful because you're able to analyze a large amount of data and construct prediction models based on this data by using multiple factors that are being evaluated simultaneously. There are several elements within design of experiments that you should be familiar with. Since you're working on process improvement in Six Sigma, of course you have the process elements, your key input variables, or your X's, that are input into some processes, and you're trying to measure the effect on your response or output variable. This is where design of experiments comes in, because you're looking at your factors, your X's, and your response, your Y value. So let's explore this with an example about processing loans. With your response variable, your Y is your loan processing speed, and you have a process in operation that you're trying to improve. Within design of experiments, you're able to control the effects on the output by changing the different levels of your input variables, your factors. Some of these factors, it's important to note, cannot be controlled by the experimenter, and they might have an effect on the responses. If the effect is significant, then these uncontrolled factors should be measured and used in the data analysis. It's also important to note that the factors can be discrete, categorical, or continuous variable data points. Besides factors, levels are another element of DOE. So let's go through the loan processing example in a little bit more detail. You can take your different factors, which are your experience of loan processing staff, mode of application, amount of loan, and number of applicants, and you can set this up as 2-factor levels. And for each of these factors, you can set the factors appropriately, and your symbols for those are your low setting and your high setting. As you set up your levels, you need to make sure that these different values for each level are far enough apart so that the effect of your response variable, your Y variable, can be appropriately measured. So you're not going to include every possible value, but you're going to set this up based on high and low levels. Now, it's important to note that with 2-factor levels, because you're only looking at a low value and a high value, you're assuming a linear relationship between these 2 variables. When you explore a design of experiments that has 3-factor levels, you can take into account a middle value. So you would have your low, a middle, and then also a high value, or a high setting. And in this case, you're able to test for a non-linear relationship. So in this example, you have 3 different factors of input: material, time, and temperature. You have 3 levels for each of those variables. So you can have material A, B, and C. You could have a time of 30, 45, or 60 seconds, and a temperature of 100, 125, or 150. Now it's important to note here that again, we've got several continuous variables, including your time or temperature, and then your input material is categorical. So it is possible to have a mix between those two different types of variables. Response is another element of DOE. Now the goal in performing a DOE is to examine your response variable and determine whether you're trying to reduce variability, maximize or minimize that response, or just make your process more robust. So if you want to ensure your response variable is a measurable factor, a measurable variable, because that way you get a true and accurate reading. If it's not measurable, you're going to have a very difficult time understanding the data for your design of experiments. A response variable can be a single variable, or it can be more than one variable, just like you have with your input factors. But again, it's important to make sure that whatever you have as a response variable, it's measurable. That response variable, or your output, is your dependent variable. You want to make sure that as you're selecting a response variable, you're picking a variable that's influenced by your independent variables, or your inputs. So these input factors are independent variables. The other important concept you need to understand with DOE are treatments, or runs. For instance, if you have a DOE where you're studying factors that could affect tensile strength of industrial iron bars during a manufacturing process, you would want to keep it fairly simple. If you have your three factors, input material, time, and temperature, your runs are your set of process conditions. Since you have three factors at two levels, you would have 8 possible runs by looking at all of the possible combinations. For example, in run 3, you might set it up where your input material is at the low level, your time is at the high level, and your temperature is also at the high level. Here's another example. If you run 8, your input material would be at the low level. Your time might also be at the low level, and your temperature might be at the high level. These will be changes that you run at those settings and then measure the output. In this topic, let's examine the purpose and process of design of experiments, or DOE. DOE helps you understand how certain factors, how your inputs or X factors impact your output, your response factors. Let's say that you have a drilling process. For your output, you're trying to get a precision within your depth. You've got multiple input factors, and you need to understand how they impact your output. Now, within design of experiments, you could use this to choose between different alternatives. For example, perhaps you want to look at your drill bits, and you could also look at which of 2 suppliers you should use based on quality and cost. In addition, you could also look at what your key factors are. So you can use design of experiments to determine out of all of these input factors which ones actually impact your drilling precision. You can also look at what you're trying to accomplish within this DOE in terms of achieving a target. You could solve for your design of experiments to make sure that you're hitting a specific target value. You could also reduce the variability within your process and reduce the variability around the precision of your depth. Or you can focus on improving your robustness so that you're getting a consistent output over time. Finally, you can use DOE to simply optimize your process so that you're hitting a target, and you can determine what the most precise settings are for your different factors. The DOE process is conducted using 6 steps. You start with identifying what the goal is for your problem. Next, you determine what your key elements are. You need to make sure that you have a measurable response, that you've identified what your factors are for the design of experiments, and also identified how you're going to measure the output of your process. You also identify the input of your process to make sure that you are setting it up accurately from the beginning. Then, based on your number of factors and your response, and your different levels, you choose the appropriate design. Once we've set up your design, you can actually start running the experiment and collect samples for each of your individual runs. Once you have your data collected, you'll analyze the data to determine what your optimal settings are. Then you perform your verification, in which you confirm your improvements to make sure you're getting what you thought you would get from your design of experiments. Let's explore the DOE process using an example in which you're trying to minimize the porosity in a casting process. So to begin with, your goal would be to set up your design of experiments to minimize the porosity in your casting process. The elements of this experiment would be your response, and you would be able to measure the porosity in your output. And based on what we've done so far in your define, measure, analyze stages, you could identify the factors as pouring temperature, mold hardness, and silicon content. You can measure the porosity using calipers. Next, you select the design for your process. So for your design of experiments, since you have 3 factors for this project, you determined you would have 2 levels for each factor. So your design is a 3-factor design, with 2 levels at each of those stages, with 8 runs for your DOE. The next step of the process then would be to actually start the experiment, collecting samples. So using the 3 factors at 2 levels, the Six Sigma team would make changes to the process, run those samples at that setting, and then make additional changes. And for this example, the team collects 3 samples for each run, and then, using that information, the team would then analyze the data. And you would go back to your goal to make sure that you're analyzing your data correctly. Once you have the optimum setting, you run parts to make sure that you're confirming your improvements. You set your equipment based on the optimal settings for pouring temperature, mold hardness, and silicon content. And you run parts to make sure that you can confirm that you achieve the output that you expected. A key challenge in the design of experiments, or DOE, is experimental error. Experimental errors are observed variations in experimental results, and there are 2 types: systematic errors and random errors. Systematic errors typically come from your measurement instruments themselves. They could be caused because there's something wrong with the measurement instrument itself, or how the data is being handled, or the instrument is being used incorrectly by the experimenter. Now, it's important to note that with systematic error, this occurs when the same error is evident every time an experiment is run. These are the types of errors that you would see often. And this means that the design of experiment has inherent error within it. Random errors, on the other hand, are unknown and are caused by unpredictable changes in the experiment. These could also happen by measurement instruments, but is typically more from environmental conditions. For example, if you're using an electronic instrument, there could be electronic noise within the instrument, or there could be heating and cooling changes within a thermal change chamber or a heat treat oven. Bias is a type of systematic error. Bias is equal to the difference between your known value, so this is where you would have a calibrated standard, versus what you're actually observing. Bias should be a standard difference over time. Bias is also inversely proportional to accuracy. An example of bias is a measuring instrument that's measuring a part, and over time, the weight of the part is 1.446 grams. You know from your true standard it's 1.346, so your bias is 0.1 grams. Another example of bias is scientists unintentionally selecting promising participants for an experimental group, causing the test results to be skewed. Or you could have a majority of patients who may intentionally sign up for a clinical trial because their prognosis is bad, thus making the drug being tested appear less effective than it actually is. Now, there are some random examples that are not considered experimental errors, such as mistakes from people who are carrying out the experiments. If you look at an example of recording the weight for the same part, this could be attributed to limitations of the finite measurement system itself. You may not have enough discretion between your measurement values within this scale, and that finite measurement system in the scale might lead to errors. So how do you control random error? You can control random error by taking the average of those measurements. There are several other factors or causes of errors that are uncontrollable, including noise factors and lurking variables. Think about opening a pizza oven and how it affects cooking times. Every time you open the door, the oven cools down slightly. This is an example of a noise factor. An example of a lurking variable might be an incorrectly calibrated scale. Uncontrollable causes of error impact the experiment by inducing variation and skewing the results. And so you need to make sure that you understand what those causes of error could potentially be as you set up your design of experiments. As you set up your design of experiments, one of the key principles for an effective experimental design is to make sure that you have a balanced design. A balanced design means that all of your treatment combinations have the same number of observations. You set this up by starting to define the levels and the number of factors, and then you calculate your runs required. For example, if you had 2 factors and 2 levels, you would have 4 runs. And then as you set up to have a balanced design, what that means is that each one shows up. And in this case, each letter shows up once in each row. And it also shows up once in each column when you have 4 letters and 4 runs. Let's consider an example of a balanced design where you have 2 factors, factor A and factor B. And again, since you have 2 levels and 2 factors, your full factorial design will have 4 runs. To set this up with your 2 factors, you need to make sure that your high and your low values are appearing equally. So each run must test at either the high or the low level for each of the 2 factors. You set up your experiment at the low level for both factors initially. Running 1 would be A low and B low, and then for run 2 it's A low and B high. For run 3 we'd have A high, B low, and for run 4, A high and B high. What that means for factor A is that you have 2 runs where it's at the low setting and 2 runs at the high setting. Then you would have the same thing for factor B, 2 at the low setting and 2 at the high setting. Based on this design, you're not repeating any experiments, so each of these tests are all the possible options. This is important because you need to make sure that your runs are evenly distributed so that all levels are tested for all factors in different combinations. This ensures that your experiment is considered to be a balanced design. Let's explore an example of unbalanced design. This is what you're trying to avoid in your DOE. In this example, you have 2 runs that are at the same setting where A and B are low in runs 1 and 3. And then you also have a run 2 and run 4 that are also the same. In doing this, you're not getting enough or sufficient information, and you're also not testing all of the possible combinations. With your balanced design, you need to make sure that you're covering all of the possible combinations with your high and low values for factors A and B. Within Design of Experiments, or DOE, one way you can decrease the impact of error in uncontrollable factors is to use randomization. Randomization is a way to organize the order in which you're performing your runs. What you're doing, essentially, is taking an ordered sequence of the factored combinations. You look at each of the possible factor combinations and you randomize that order. You change the running order of the experiments. The goal of randomization is to organize the experiment in such a way that the treatment combinations are performed in a random manner, which improves the statistical validity. This ensures that you and your team are more secure in the conclusion that you reach based on your design of experiments. Randomization helps to reduce those conditions that create bias. For example, when you start your design of experiments, there could be a learning curve, whether it's with using gauges or how you're actually recording the information, that might cause some of the errors in your measurements. In addition, you might have some noise variables that are impacting your system. For example, if you start your design of experiments at the beginning of a shift, your machinery or your equipment might have to warm up, and that might have some impact in your results. So by randomizing your experiment, it would balance those noise effects across all of your different experiments. Let's illustrate randomization in a DOE with an example. Let's say you have a federal health agency that's evaluating 2 different types of messages that were created by an ad agency. So you need your factors. So these ads were about cancer awareness based on the type of message. So the message type could be A or type B. In addition, another factor you have for a design of experiments is a screen resolution. Your 2 levels of screen resolution are 1200 and 2400. And then your third factor is your exposure duration, and you have 2 levels for this factor as well, 120 seconds and 300 seconds. You're conducting your experiment in focus groups, and you're evaluating them and comparing the effectiveness scores. Your focus group members are recording their scores on a scale of 1 to 10. The standard order provides you with information on how you would normally go through and run your experiment. Since you have 3 factors at 2 levels, then you have 8 different runs. For your 8 different runs, if you run them in order, you could be putting bias on your initial runs. So what you want to do is spread that bias out by randomizing your run order. So your run order is where you could use tools such as a random number generator so that you could randomize the values of 1 to 8 and then run them based on the randomized values. So in this example, you would start with the first one, which could technically be your run 6 based on your standard order. But based on your random orders, your first run would be your message type at the low setting, your screen resolution at the high setting, and your exposure duration at the low setting. And then your second run would be all 3 factors at the low setting. Now, while randomization helps to avoid bias, it's not always recommended. If you're setting up a design of experiments, you don't want to randomize if it leads to an undesirable run order, or it's not feasible. For example, if you think about a process where you're casting metal parts, changing a factor such as the heat or pouring temperature of your casting would be very difficult. Typically, you're talking about hundreds of gallons of melted metal, so raising the temperature up and then dropping the temperature down very quickly is not really feasible. So you would want to look at your run order, and you would want to set it up so that you're minimizing the impact on the team, because that would be an undesirable run order. In design of experiments, or DOE, one way to manage variation that's caused by non-experimental factors is blocking. Blocking is a way of setting up blocks for non-experimental factors so that you can take those factors into account and then assign your runs to those blocks. You can organize them in such a way that your study is more uniform than your population as a whole. For example, you can use blocking when you're conducting an experiment around the amount of individual TV viewing in a neighborhood. So you could consider each household as a block, as opposed to all households in the neighborhood or all of the individual people. By doing this, it will help you achieve greater precision by comparing the units within a block, since the main differences between the blocks are assessed separately. You would then need to take care of the randomization run order within the blocks to help avoid experimental error. Blocking is very useful in manufacturing. For example, let's say there are different lots of material being used or introduced within a process. Introducing a new lot during a DOE would introduce additional variation, so blocking can be useful for controlling this variation. Alternatively, in the service sector, you may use blocking to manage different things happening based on different shifts, so you would want to take that into account. You can have within block variation and between block variation, and you want to remove variation between your different types of blocks. In the TV viewing example, you may want to group by household income categories. In the case of manufacturing, we would group by shift in addition to any input material lot. To remove between-group variability, you can assign treatments within blocks to achieve more precise results. You can measure the effectiveness of the blocks and minimize within-block variation by running analysis of variance, or Anova. Let's say that you're conducting a study of the variation in the wear and tear of tires. If you study all car models as one large group and only measure the wear and tear on the left front tire, the results will be skewed. If you select different car models as the block variable and randomize the position of the tire being tested, you can increase the similarities among the blocks. This will create more homogeneous blocks, which leads to more precision results because the variation within blocks has been minimized. You can also block in time or space, instead of by similarities in factors or population. For example, in an experiment conducted over a number of days, the runs made on the same day are most likely to be more similar to each other. Or, in an experiment where a staining process is being tested on wood, areas that are closer together would be expected to be more similar than areas that are further apart. Randomization and blocking are used together to deal with variability by assigning treatments within blocks randomly. With randomization, you can randomize the units in a sample, the order in which samples are tested, and the order of the runs. Blocking helps reduce non-experimental factors. Replication and repetition are two principles for effective, good experimental design. Repetition simply means repeating the same design, but over longer periods of time. For example, if you have two factors, bill amount and experience of staff, and your response is bill processing time, you're running an experiment with 2 factors at 2 levels, and that means you need 4 runs. With replication, you're running your 4 runs, and that first set of experiments for those 4 would be your replicate 1. You're essentially repeating the entire design again. So when you run those 4 runs again, the values that you would get would be for replicate 2. Then, if you run that entire experiment a third time, you have replicate 3. So by using replicates, you're testing all of the combination of the factors, and then you're resetting the experiment so that all of the elements are the same. In this case, you're conducting the experiment 2 or more times, and so that gives you 3 replicates overall. There are several considerations for replication to keep in mind. Replicates are very useful if you want to increase the precision of your output, because you're able to see the change and the variation that's induced over time. And so that really helps with being able to detect different defects over time. Rather than running the experiment just once, you're able to see the experiment multiple times and see the impact over time. Because you're running the complete experiment again, if you have a large number of factors, it's very difficult to run that experiment again, because it might be too timely and costly. And so the number of replicates is very dependent on the cost and the time it would take to do that. Another way you can address this, though, is with repetitions. Repetition differs from replication because you're repeating the same experiment immediately after. For example, in an experiment with 3 factors and 2 levels, you repeat the same treatment twice before moving on to the next. There could be more than 2 factors and levels in an experiment, and you could have repeated each treatment more than twice. Let's take a minute and consider the differences between replication and repetition. With repetition, you're repeating the same measurements taken during the same run, and then you're entering the data across rows, and there's no passage of time between the repeats. And since there's no passage of time, you're immediately running the part or that setting again. You won't catch as much variation as you could, because you won't notice the changes in variation. So this is where repetition is lacking in being able to detect all of that variation. With replication, you're taking the measurements during identical but very distinct runs, and your data is entered then down a single column. Because there is time that passes between the first run and the second run, you're able to capture that variation, which could be from things like different equipment settings or environmental factors. Here's a useful example to illustrate the differences between replication and repetition. Let's assume you have an injection molding company that has a production line with a number of settings that could be modified by your operators. The production manager designs 2 different experiments, one with replication and one with repetition. He wants to evaluate the effect of the settings on the tensile strength of injections. So your response variable that you're testing for is tensile strength. If you look at how this is set up with replication, you have 4 separate runs, because you have 2 factors at 2 levels. In your first set of 4 runs, you're running all of the possible combinations, and in your second set of runs, you're repeating the entire experiment again. If you look at setting up the same experiment using repetition, you're still running 8 experiments, but runs 1 and 2 are running at the same exact settings. Run 3 and 4 are running at the same exact settings, and so over time, you're not seeing as much of a difference with variation. If you want to be able to pick up the variation within your experiments, you want to use replication. And again, this is important because you're trying to hit a specific target with your design of experiments, but you're also trying to reduce your variation. So by using replication, you can pick up that variation that could be occurring. As you start your design of experiments, or DOE, it's important to select your design for your experimentation. To do this effectively, you need to understand the difference between a full and a fractional factorial and the implications of choosing either. Full factorial designs are generally used when you have a small number of factors and levels, resulting in a small number of runs, or where there are more factors and costs and time are not an issue. Fractional factorial designs are typically used when the number of runs is large due to a larger number of factors and levels. You're still able to extract valuable information, but with fewer runs. To calculate the number of required runs in a full factorial design, you use the formula L power of k, where L is the number of levels and k is the number of factors. For example, if you have 2 factors in 2 levels, that's 2 to the power of 2, or 4 runs. If you have 3 factors and 2 levels, that's 2 at the power of 3, or 8 runs. As you set this up as a full factorial design, it's important that you're considering the number of runs in your experiment, and how this affects your budget and your time constraints. If you have a large number of factors, and the levels because of the time and cost restraints, this is where Six Sigma teams might consider conducting a fractional factorial design instead of a full factorial experiment. In fractional factorial designs, you're focusing on the main effects and only a limited number of interactions that are of interest. Typically, interactions of more than 3 factors are not considered significant. So rather than testing every combination, you're testing a subset of combinations. Your number of runs for fractional factorial are calculated by L to the power of k minus. So let's consider an example where you have 4 factors in 2 levels. For a full factorial design, that would mean it's 2 to the power of 4 minus 0, or 16 runs. With a fractional factorial, your p-value represents the number of factorial reductions. So if you're doing 1 factorial reduction, and therefore you're calculating 2 to the power of 4 minus 1, or 2 to the power of 3, which is 8 runs, and essentially you're cutting your number of runs in half from your initial 16. If you do a fractional factorial, your p is now 2, so you're calculating 2 to the power of 4 minus 2, or 2 to the power of 2, which is 4 runs. Now you're doing a quarter fractional factorial design, and you went from 16 runs down to 4 runs. This is where, as a company, you can save time and money. Now, let's go through another example. And this time you're pulling all 3 different types of settings or experiments together. Let's say we've got 6 factors at 2 levels in a full factorial. That would mean that you have to do 64 runs, which would be extremely time-consuming and potentially very costly. So let's consider a half fractional factorial. Now your p-value is equal to 1, so we've reduced your number of runs from 64 to 32. And finally, with a 1/4 fractional experiment, your p-level is now 2, and so that reduces the number of runs even further down to 16. As a general rule of thumb, when you're talking about fractional factorial designs, is that when you have 6 or more factors, you should use a fractional factorial experiment instead of a full factorial experiment to help with saving time and money. Like anything, there are pros and cons of full factorial designs and fractional factorial designs. With a full factorial design, because you're testing every possible combination at every single level, results are more comprehensive, and you also have more data, because you're running every single level. However, if you have a considerable number of factors and levels, it can be very cumbersome and very costly. In a fractional factorial design, because you're reducing the number of runs that are necessary, it can be very economical and easier to run. And it's very useful when you have a large number of factors or levels, say 6 or more factors. Now, as a con, because you're reducing the number of runs, for a design of experiment you could end up with confounded factors, which means 2 factors might look exactly the same, and typically this occurs with a main effect and an interaction. In design of experiments, you have main effects and interaction effects. Main effects are the key factors that you've identified that might impact your output. Interaction effects, or interactions, are the interactions between 2 factors, and the interaction is part of variation. It's a variation among the differences between the means for different levels of one factor over different levels of another factor. For example, if you're examining a process, you might think that the temperature and time are related to each other, so you'd want to be able to calculate the effect of the interaction of those 2 factors on your output. There are several reasons why it's important to calculate effects. When you're calculating effects, what you're really looking for is which of your factors has the biggest impact on a response variable. This is a way of reducing the number of factors to determine which of those factors really has an impact on your output. By calculating effects, you're also able to determine the nature of the factor-level combination, because once you've determined that a factor is important, now you need to look at the levels of those factors to see what the appropriate combination is to make sure you're getting that desired output. If you were to look at this one factor at a time, it might hide the importance or the impact that a factor has on the response. By using a design of experiments, you want to understand what those effects are between your factors. how did those factors work together to create that impact on your response? You can plot main effects graphically to identify the impact of each factor on your output. So typically you're looking at your impact of factor A and factor B and so on. When you plot your main effects, you're looking at your main effects based on the low setting and the high setting. When you change a factor from the high setting and the low setting, if you have a horizontal line, that means that the change in levels has no effect on your output. However, if you change from the low setting to the high setting and you have a difference in your slope, that means you have some sort of effect on your output. So what you're really looking at is the slope of the angle that defines the main effect. The steeper the slope, the greater the main effect. For example, if you change from the low setting to the high setting, and you have a very large difference in the slope, that indicates you have a large effect. So when you have large effects, these are factors that you can change to impact your output. Let's use an example of calculating main effects. Suppose that you're conducting an experiment to select the best wood stain based on absorption percentage. The response variable would be the absorption. You have three different factors: the wood quality, the temperature, and then the stain solvent. And for each of these factors you have a low setting and a high setting. For temperature, you're looking at settings of 70 or 80 degrees, and for solvent, you'd have a low setting and a high setting. Then, for each factor, since you have 2 levels and 3 factors, you would need to do 8 runs. Based on these 8 runs, you would do 5 repetitions for each run. And then using that information, based on those 5 runs, you take the average of those 5 runs. Using this information, you can plot your results. If you look at temperature, you're plotting the average response where the temperature is 70 degrees, which is a value of 6.75. The average response when the temperature was 80 degrees was 4.25, and so the slope of the line tells you that there is a moderate effect. The next factor is the solvent level. When the solvent level was at the low setting, the response was 7.25, but when the solvent level was at the high setting, the value was 3.75. Based on the slope of the line, you can say that it had a large effect. Finally, you look at the wood. When the wood was at the low setting, it had a value of 5.5, and when it was at the high setting, it had a value of 5.5. So you have a horizontal value, which means there is no effect. Now, it's important to note, when you also have no effect, that also gives you good information about your process. Since you have a straight line and there's no effect between the levels of wood quality, then you can look to see which one is less expensive. And in this example, a class 2 of your wood quality is less expensive. So you could use that information to recommend class 2 for your wood, because it's a cost-saving measure. Now you can move on to the interaction plots. Using your interaction plots, you can look at your interactions, which would be the interaction between A and B, A and C, and B and C. With interactions, you're plotting the difference between 2 values based on their low and high settings. For example, if you look at the difference between factor A and factor B, since those lines are horizontal to each other, you say there is no interaction. If you look at factor A versus factor C, since the lines don't necessarily cross, but they will cross outside of this scope, then you would say there is a moderate interaction. And if you look at B versus C, since the lines cross each other, you say that there is a strong interaction. Design of experiments, or DOE, allows you to analyze the impact of key factors and adjust them to optimal levels that will achieve the desired output. In this topic, we'll explore the different techniques and tools you can use to analyze your results, along with the key elements you focus on. Let's go through an example to see this in action. So let's say we've got a glass manufacturer that wants to improve tensile strength. That's the response variable. Based on what the team has done so far, they've identified 2 key factors, material density and molten temperature. Because they have 2 factors, they have one two-way interaction. So to set this up, the team will start by designing and conducting the experiments. In this example, there are 2 factors, and they're going to run this at 2 levels. Once they've conducted the experiments, and as they're conducting the experiments, they're going to record the results for each run. Based on this information, they can calculate the main effects, and they can look at the results to see if the 2 main effects, the two-way interaction, or both of these are statistically significant. Once you've collected your information, you can focus on your main interaction effects plots for the glass manufacturer. This information has been created by Minitab. Typically, you'd analyze the results using statistical software, such as Minitab, because it will automatically calculate and graph your main and interaction effects. It's also useful in helping to determine statistical significance, creating a prediction equation, and identifying the settings for your different factor levels. So when you look initially at your plot of your main effects, you can look at the two factors where you had factor A and factor B, which are the material density and the molten temperature. Based on the main effects plot, you observe the slopes that indicate these two factors are both significant. And that slope is a key indicator of determining whether or not those factors are significant. Now the interaction plot looks at both of the factors. On the x-axis, the molten temperature is plotted, and on the y-axis, the mean of the response. You plot the material density to see the impact or the response of the molten density, where it's 30 and where it's at 40. And in this case, since the interaction effect lines do not cross, then that's telling you that the interaction is not significant. And so, by looking at these two plots, you can state that both of the main effects of material density and molten temperature are significant, but the interaction effect of the two values is not significant. Using statistical software, you can look at the estimated effect and the p-values, and you have the two factors of material density and molten temperature, which are the main effects. Finally, you have the interaction between the material density and the molten temperature. By using the estimated effects and p-value table, you can look at what the effects are. For material density, it's 12.1. For molten temperature, it's minus 12.6. So the main effect of molten temperature is slightly more important than material density. And the value for interaction is very small, and so it's not significant. You can use p-values and compare those with the significance value of 0.05. And since the p-values for material density and molten temperature are both less than 0.05, you can say that these two values are significant. And the interaction value is greater than 0.05, so you would say it's not significant. Graphically, you can also use a Pareto chart to visualize the relative significance of each main effect and the interaction effect. So in this example, you have factor B, which was slightly higher, factor A, and then the interaction of AB as measured against the standardized effect. The 5% significance level is 2.179, so based on this Pareto chart, you can say that the material density and molten temperature are significant, because they extend beyond the 5% significance level of 2.179. And in this case, again, since the interaction is significantly less than 2.179, the interaction effect is not significant. Another way to verify the significance of your effect is using analysis of variance, or Anova. Using statistical software such as Minitab, you can look at data in a tabular format, where you look at the main effects, the two-way interaction, and then compare the p-values based on the significance level of 0.05. Since the p-values for the main effects are less than 0.05, you can say it is significant, and the p-value for the two-way interaction is greater than 0.05, so you say it is insignificant. You can also use the coefficients from the output to develop the model equation based on your statistical software. You can use the partial estimated effects and coefficient table to get the coefficients to determine your prediction equation, also sometimes called your model equation. You can calculate tensile strength by setting it equal to your constant, plus your coefficient for material density was 2.94431 times your factor plus 0.07 times your coefficient for molten temperature. Since the two-way interaction was insignificant, you leave that out of the equation. You can use this model equation to help optimize your output, which is your response variable, by suggesting optimal levels to set the factors so that you can achieve the desired response. During the improved phase of a Six Sigma project, team members use a variety of statistical and non-statistical methods and lean tools to find underlying issues and ways to address them. Root cause analysis is an exception tool that allows you to identify and fix the root cause of a problem, rather than just trying to minimize the effects of a problem. Root cause analysis requires using a root cause analysis process, and applying a set of root cause analysis tools. There are 3 steps in trying to identify and perform root cause analysis. These steps include listing the possible causes, organizing or grouping these causes, and then prioritizing the list. By using these 3 key steps, you can determine the true root cause and actually fix the underlying problem, rather than putting a band-aid over your symptoms. The first step involves generating a list of possible causes. This is typically the most time-consuming step within the entire root cause analysis because it involves collecting data. In this step, you gather the information that's relative to the problem. It's important to note that this step is typically the most time-consuming because you're collecting data. You can't rush it. You need to make sure that you're making data-driven decisions, so you need the data to back up whatever you identify as your potential causes. Some root cause analysis tools you use during this step, as well as the others, include cause and effect diagrams, relational matrices, the 5-why analysis, and fault tree analysis. In the second step, you focus on organizing and grouping the possible causes listed in Step 1. Many of the same tools are also used in this step, including fishbone diagrams and relational matrices. The goal in Step 2 is to identify which causes are linked to each other or influence each other. It could be that they happen in the same process, or by the same people or the same teams. By identifying those common causes or groupings, you can then start to put those into the natural groupings by affinities. Once you've grouped them, now you can move into the third step, which is to prioritize your list of causes. You want to drive it down so you're focusing on those vital few causes, and then you can use your root cause analysis tools on those causes. It's important to note that everything that you move forward with needs to be based on data. So you should be able to back up all of your decisions using solid data. One of the commonly used tools for root cause analysis is the fishbone diagram, which gets its name from the shape of the diagram itself. It's also commonly referred to as the cause and effect diagram, because you're looking for all of the potential causes related to a particular effect. You may also hear it referred to as the Ishikawa diagram, named after the creator of the diagram. With the cause and effect or fishbone diagram, you're trying to identify all the potential causes for one specific effect. Then you use tools such as a brainstorming session to generate all the potential causes that could be leading to that effect. So let's explore how to create a fishbone diagram. The first step in creating the diagram is to develop a problem or an effect statement. And this is where it's important for the team to develop this effect or problem statement together to make sure everybody fully understands what you're trying to solve. The next step is to add the spine that goes out to the left of the diagram. Based on that, you'll have 6 or 7 main ribs along the fishbone theme, branching off from the central line. From there, you add descriptions of the main causes at the end of the branches. Typically, these descriptions are developed based on the brainstorming session. You group your different ideas for those causes by affinity, and then you label the causes based on those headings. Then, as a team develops the different causes in that brainstorming session, they start adding these to the fishbone diagram. Again, you brainstorm and write down each idea based on how it's categorized under a main cause. If you need to go further into causes, you again write down detailed causal factors for each of those main factors, and each causal factor is attached to the branch of the main factor that it's related to. Next, you ensure that all the items are included in the diagram. If anything is left out, the analysis of the diagram won't be valid, which will lead to an ineffective resolution of the problem. Finally, you analyze the diagram. Once the diagram is complete, the team will have a clear picture of what areas are contributing to the problems. Let's build an example of a fishbone diagram. Let's say you're working on a project to improve your retail bank's loan processing time. So as a team, you've identified the effect as consumer loan processing delays, and you're trying to reduce the delays in the process. Based on what you're trying to solve, you've come up with headers for each of the ribs for a fishbone diagram. And those include poor quality infrastructure, varying amounts of loan applied for, customers using paper applications, and loan processing staff's inadequate skills. So exploring the rib for inadequate skills of your staff, for example, some of the causes are lack of experience, inadequate education, inadequate training, and lack of motivation or reward. All of these are linked back to the loan processing staff's inadequate skill, and all of these are potential causes for the effect, which is consumer loan processing delays. There are some important points to keep in mind when creating cause and effect diagrams. First, it's important to reach agreement about the problem statement. Disagreement about the problem statement may indicate that the problem is more diverse than originally perceived. Without agreement from all participants, a disconnect will exist between the information you want and the information you get. You should also fully explore and break down each cause into other detailed causes until you get to the root cause. And finally, your job is to analyze the diagram. Decide which of the causes are most significant contributors to the problem, and then devise your own solutions. The diagram itself does not offer solutions. A relational matrix diagram is a commonly used tool for root cause analysis. It's very useful as a problem-solving tool to help identify the true cause of a problem. The relational matrix diagram shows the relationship between key process input variables and key process output variables in a matrix format. Because it's a matrix, it's very easy to create and use. This tool is used within the Analyze and Improve phases of Six Sigma because it helps to identify the relationships between input variables and what you're trying to narrow down through various tools, such as root cause analysis or design of experiments, and how they relate to your output variables. There are 6 steps in creating a relational matrix. The first step is adding input variables to the first column. Next, you add your output variables to the first row. Then you assign weight to each output variable and assign weight to the effect each input has on its output. Next, you multiply the output weight by the effect weight. Finally, you enter these values in the table and total your results. It's important to understand that the steps here are specific to analyze the relationships between inputs and outputs in a Six Sigma project. But the same relational matrix could be used for understanding the relationship between any 2 variables or 2 sets of different things. So now let's explore an example relational matrix diagram for an axle manufacturing plant. You want to identify what the true root causes are for the less than desired material density of your final outputs. You begin by identifying your big Y's. Your big Y's are your key process output variables, and those include tensile strength, torsional stiffness, and material density. And then for each of those, you've given them a priority score. These priorities are based on feedback or voice of the customer. The next step of the process is to include the key process input variables. You determine the effect of each of these input variables on your output variable. For example, with input density, it's an effect of 6 for tensile strength, 8 for torsional stiffness, and 6 for material density. And then, using the priority score, you multiply the effect times the priority for input density. You get a value of 12 for tensile strength. The priority score is 1 for torsional stiffness, so you have a value of 8. The priority score is a 3 for material density, so you have a value of 18. Finally, you sum up all of the values. If you look at processing temperature, it's 14 plus 4 plus 24, which gives you a ranking of 42. And then using this information, it's clear that the highest priority, or the cause with the greatest effect, is your processing duration because it has the highest value with a score of 53. A common tool that's used to drill down to the root cause is the 5 Whys tool. It's very useful because it's a simple method of continuing to ask why until you drill down to that true root cause. The goal is to eventually reach a cause that's actionable. 5 Whys is typically used in conjunction with other tools such as a fishbone diagram or Pareto diagram to help you fully drill down to the root cause. You start by asking why something happened. For example, you could ask, why did the defect occur? Well, it occurred because you had an inconsistent flow of input material. Then ask, why did you have an inconsistent flow of input material? Well, you had an incorrect measurement. Ask again, why did you have an incorrect measurement? The measuring tool gives inconsistent readings. Next, why did you have a measuring tool that's giving inconsistent readings? Because the measuring tool incorrectly was calibrated. And finally, why was the measuring tool incorrectly calibrated? Because you have no measurement system in place. So it's a process of continuing to ask why until you drill down to the true root cause, which is something that's actionable. In this case, if you have no measurement system in place, then you need to put one in place. The first step in the 5 whys is to select a cause and really ask that initial question. Why does this problem exist? There are a couple of places you can get your cause from. For example, you could look back at your cause and effect diagram, and based what was at the head of your fishbone diagram, you can pull that cause, and start asking the 5 whys to drill down to that root cause. Another place you can get this information is from your Pareto chart. For example, if you're assessing the causes of delays in your receivable cycle, you could use a Pareto chart that reflects data over the past 6 weeks to identify reasons for delays in terms of the customers not paying their invoices on time. And so you could use that tallest bar in your Pareto diagram and ask why that's occurring. And then drill down with your 5 whys based on that highest occurrence. Once you have that initial why, then you start beginning the why does this occur series of whys. For example, if you looked at your late invoices, you could start looking at some of the potential causes. And the potential causes could be that customers are losing their invoices, or the company is sending invoices late, or that the customers are paying their invoices late. At the third why, you're going to start investigating the potential causes, because at this point you have 3 potential causes, and you want to make sure that you have data to support any of these before you move forward. Ideally, you want to narrow your list down to 1 or 2 possible causes. So if you think about the customers losing invoices, you can eliminate this cause because the number of late payments is too large to account for this problem. That would mean that there would be a high percentage of customers that are losing their invoices. A second possible cause was that the company was late sending the invoices, and you decide to keep this as a possible cause because it's actually supported by data and facts. The third possible cause is that customers are late paying their invoices. And you're going to eliminate this possible cause because some of the late payments are coming from customers who have always paid on time in the past. So now you would take this to the next why, and you'd ask why the company is late sending their invoices. At this point, you could discover this is happening because there's a problem with the billing system, there's user error, or there are issues with the customer database. As you continue, you ask more of the why questions, and you want to make sure you're determining what's actionable. So if you look at the problem within your billing system, you find that you have something that is actionable. It turns out that the automated billing system is using legacy software, and it's been due for an update for many years. Because it's using old algorithm sets in the software, it's been producing invoices that are a few days late, rather than sending the invoices immediately once you've shipped your product. So to solve the problem, the team decided to adjust the algorithms as a short-term solution, and then as a long-term solution, they're going to update the entire software. It's important to note that even though you're calling this the 5 whys, you don't necessarily have to ask why 5 times. In this example, the team actually reached an actionable cause after only 4 rounds of why. On the other hand, you might find that it's necessary to continue this process iteratively by asking why 6 or 7 times. The rule of thumb is you stop asking why when you start repeating the same causes or reasons. Fault tree analysis, or FTA, is part of the root cause toolkit used during the Six Sigma Analyze and Improve phase. This tool helps you consider underlying reasons for a specific failure mode or event, and also helps you understand the relationships between them. This is commonly used to search for the causes of an observed or potential failure, so that problems relating to processes, products, service, or quality can be addressed and eliminated. Although fault tree analysis is very useful in manufacturing, that's not its only application. You can also use this tool in administrative, service, transaction-based, and many other contexts. So let's explore the FTA layout and process. You start by determining what is that top event, what are you trying to solve for, and then you start by identifying potential causes. And with your potential causes, you're going to use logic gates. We'll have logic gates such as AND, where the AND means that A plus B plus A plus B plus C plus A plus B plus C must occur. So AND means that all three of the events below it must occur. When there's an OR logic gate, that means that one or the other must occur. Once you've identified your causes, you start drilling down to your root causes, and you will continue creating your fault tree diagram until you reach your true root causes. Once you have your true root causes, you prioritize those causes, and then you identify countermeasures to improve those. So the first step in the process is to identify what the top event is. Let's use an example to go through this. Let's say we're trying to figure out why you have a computer prototype that's not working. So as you drill down to figure out why your computer fails to work, one of your first gates is an OR gate, which means that the computer will fail to work if the hard drive or the CPU or the keyboard or the monitor will not work. When you have the AND gate, your computer will fail to work when the CD-ROM for drive D and the CD-ROM for drive E both fail to work. The next step in the process, then, is to identify those contributing causes until you eventually reach a true root cause. So you would continue to drill down and find those true root causes. As a Six Sigma team, it's important to really pinpoint the highest priority root cause by finding the probability for each cause. So in this step, you also identify what your probabilities are for each of those causes. And if you have an AND gate that's connecting these causes, you would multiply all of those causes that are below it. If you have an OR gate, then you're going to add together all the probabilities below it. The next step in the process, then, is to prioritize your causes. And these would be the values that drill all the way down to your true root causes. That helps you determine the cause that has the greatest impact on your overall top event. For example, if you reduce your probability of your CD-ROM drive D failing down to 0.001, that gives you a probability of 0.036 that your overall computer will fail to work. You could also look at your keyboard, which currently has a failure rate of 0.020. If you reduce that down to 0.01, then it reduces your probability down to 0.024 from your value of 0.036. That tells you that your greatest reduction in the probabilities of failure comes from reducing the probability of your keyboard failing. The final step then in the FTA process is to identify your countermeasures. You want to make sure that you're preventing your critical failures. So if you look at two of your root causes, incorrect panel wiring and not being connected to the motherboard, you could determine a countermeasure, which would be to routinely test your connections. That would help reduce your overall probability for failure. It's also important to really check your results and your tree very carefully. You want to make sure that you're validating the logic of the tree hierarchy. And you also want to compare to all the possible paths that lead to that overall top failure. And finally, you want to quantitatively rank order the paths for system improvement. You will use that information to determine the probability of your overall system failure. In the improve phase, there are several lean concepts, including value-added versus non-value-added activities, that can help to further improve or enhance the process improvement efforts. In this topic, we'll explore how to apply the concepts of value-added and non-value-added activities. Value is always from the customer's perspective, and what they see is the value of the product or service that you're offering. Value added refers to features or services that the customer is willing to pay for. For example, value added could come from home delivery or ease of use. Alternatively, non-value added activities could be transporting components to a factory or inspections. It's important to analyze whether non-value added activities are really necessary. If not, they should be reduced or eliminated from your processes. Keep in mind, however, that not all activities that fail to meet the value-adding criteria should be scrapped. Some non-value-added activities are necessary, even if they don't change a product or service, meet customer preferences, or ensure the task is completed right the first time. Non-value-added activities may be necessary to operate a business, or when you need to meet regulatory or accreditation standards that apply to your organization. These types of activities are known as required non-value-added activities. For example, writing a production report, paying wages, or even implementing a lean initiative are necessary for the efficient running of a business, even though they add no direct value for the customer. So let's examine a few examples. You have a worker that's installing bolts to attach a handle to a product, so they're fulfilling a customer need for a handle on the product. The customer then would expect to pay the cost of assembling the product because they want handles, so this procedure would add value. Similarly, if you're entering data from invoices and receipts into an accounting system, this adds value because customers need to be able to balance their books. Other examples like this might include installing a spark plug in an automobile engine, or cooking a hamburger, because these make physical changes in the item that helps it become a finished product, so these activities add value. Inspections, however, do not add value. They do catch errors that would potentially disappoint your customers. However, customers are rarely aware of these, and they don't know if your product's been inspected a dozen times or not at all. Your customers just expect a product to work to their satisfaction and meet their needs as it was promised to them, so inspections do not add value themselves. And similarly, if you have a program that writes computer instructions or a banker who negotiates the interest on a banking loan, they're acting in a way that makes the change in service, even if the change can't be seen. Six Sigma focuses on eliminating or preventing muda, which means waste in Japanese. The goal is to eliminate and prevent muda to further improve the process. You want to understand where you have waste within your process and reduce the number of non-value-added activities, especially those that are not required at each step within your process. In Lean Six Sigma projects, identifying and removing waste are very useful at the improve stage in the DMAIC cycle. Six Sigma defines 7 ways to try to reduce or eliminate. The first waste is overproduction, which is when you're producing more products than is needed. The next waste is extra processing, where you're doing extra steps in a process, or to your product that the customer is not willing to pay for. The next waste is motion, specifically excessive motion in terms of the people or the operators who are involved within the process, whether this is reaching over too far or having to walk too far to get what they need. The next waste is waiting, and this could be people waiting on equipment waiting on people, or waiting for a step in the process. For example, waiting for someone to sign a form to get an approval. The next waste is transportation, such as moving a product back and forth multiple times. The sixth waste is inventory, which is holding on to too much product in the inventory that might be damaged, or for a customer who may change their mind and not want it anymore. And then the last waste is defects. Defects are any result that does not meet the customer specification. Defects usually result in rework or scrap. In addition to the 7 wastes, there is an 8th waste considered by many, and that is the non-utilized or underutilized skills and talents of employees. This 8th waste is added because people need to understand the importance of the employees and how much they add to the process. By not using their time, their talents, and their skills, you're losing value, so this is another form of waste. All 8 of these types of waste form the acronym downtime. Defects, overproduction, waiting, non-utilized talent, transportation, inventory, motion, and extra processing. There are some strategies you can use for reducing the impact of waste. For example, you can eliminate overproduction and inventory waste by changing from a push system to a pull system. This would help to ensure that you purchase or produce only what the customer or the next process requires. Another way is to implement Poka-yoke, and Poka-yoke devices are mistake-proofing mechanisms that can be used to reduce the waste of overproduction and excessive inventory. Another strategy could be to reduce the batch sizes or eliminate batch production by going to single-piece flow production. And this helps to keep either the batch sizes down or the batch sizes at 1, so you can level out the sales demand. And one way to help this is to reduce the setup and changeover times, and that helps to drive down the smaller batch sizes that make it more economical. Another strategy is to focus on improving communication. When you ensure communication flows between facilities and suppliers, then you're really able to better put together a pull system in which each component or item is supplied only when it's needed. You can reduce motion, transport, and waiting waste with good housekeeping, standardized work, cross-training, and strategies for reducing batches and bottlenecks. For example, a shipbuilding company finds that many of its employees are forced to walk fairly long distances to fetch various tools and components. The company also finds that employees spend considerable amounts of time waiting for components to be finished before assembling them. And the company is spending a large amount of money on forklifts and cranes to transport finished components for assembly. To address these wastes, a team carefully maps workflows and then assembles all equipment used for one component in a single area. Each area is arranged in a U shape to minimize the required motion and transportation. To reduce waiting times, the team balances workloads and redesigns the production process to ensure all employees can work in parallel. The team also reduces the distances between workstations. The company then cross-trains workers so that they can use all the equipment and perform basic maintenance tasks on it. This reduces the need to move machinery, and employees don't need to walk far to complete their tasks. Training also incorporates best practices for completing assigned tasks efficiently. Let's explore some strategies for reducing extra processing and defects. The first strategy is a poka-yoke, which means mistake proofing, and this is where you can implement such things as equipment sensors or software checks, which help to automatically reduce your defects. When employees know what to do, they're less likely to make mistakes. A well-designed and focused training can help better understanding of processes and equipment capacity. Another strategy is the use of Statistical Process Control, or SPC, and this can be used then to monitor and analyze your processes to determine if there is special cause variation. This helps Six Sigma teams because they try to reduce that special cause variation. Another strategy is standard work. This is useful because it helps provide a consistent standard procedure for everyone to use, which also links back to training and cross-training, because it lets operators know exactly what needs to be done to accomplish the job. And finally, Kaizen events are very useful because they give very structured, short improvement initiatives for process improvement. During the improve phase of Six Sigma, there are 4 key tools used to eliminate waste, including 5S, poka-yoke, standard work, and Kanban or pull. In this topic, we'll explore 5S. The 5 S's are based off of 5 Japanese words, and in English they translate to sort, straighten, scrub, standardize, and sustain. They represent a circle, an iterative process of continuous improvement. It's important in terms of quality improvement because you want to have a workplace that's clean and organized and has structure. It's much more difficult to make improvements within your process if it's disorganized, cluttered, or neglected. And this is where 5S provides an excellent methodology for making sure that you only have what you need when it's needed, and it's in the order that you need it when you need it. So you start out the process with sort and straighten. With sort, you're determining what's needed versus what's not needed, and you're discarding or removing what's not needed when you're operating that step of the process. Once you know what you need and what you don't need, you only have what's needed within your process, and then you organize or straighten what you actually need. So if you think about a manufacturing line, you would want to only have the tools that you need for the product that you're running, and anything else that's not needed in that step, in terms of components or supplies or equipment, would be removed from the process. Then what's left needs to be organized in the order it would be used. So a simple example to think about is with an operation. You would only have the medical instruments that you need, in terms of the scalpels and things like that, in the operating room, and they would be organized in the order that they would be used. The next step in the process is to scrub and standardize. That means you only have the tools and the equipment and the components that you need for the process that you're running, and at this point they would be laid out in the order that you would need them. And your third S, scrub, means you clean everything so that you have a nice clean environment where you can operate and you can clearly see what's needed and what's not needed, and if anything is missing. This could involve wiping down machines or setting up procedures so that you can make sure that you have a cleaning routine, which would be your next S, standardize. You could set up your processes where, based on what you're operating in your line or what your role is today, you would have the specific things you need to go and clean up at the end of the day or at the end of the shift, and that would provide a standard operating procedure. And then the final step in the process is to sustain. And when you talk about sustain, you want to make this part of the culture of the organization. So now you build off getting everything organized and clean, and you have the work instructions and procedures to have a standard in place. You want to make sure this is part of your daily organization. And it's part of your ingrained culture of your organization. And you can then set up things to prevent things from happening. You want to prevent things from going back to the old way of doing things. In this topic, we'll explore how you would implement 5S by working through an example. The first step with 5S is to sort. And with sort, you start by red tagging your unneeded items. The key aspect in the sort phase is to understand what's needed and what's not needed. When an item is declared as unneeded for that process, a red tag is placed on it, which gives it an identifier. Then each of those items is moved outside of that main process area to a designated area. And typically these items are held for a week, just to make sure that they're not actually needed. After a week, you have to deal with whatever is left, and those items could be disposed of, donated, or relocated. And it's important to note that the goal is not to throw away as much as possible, but to determine what you actually need and what you don't need, which is why you can hold on to those items for a week, just to make sure there isn't a special instance where you might need something. The next step in the process is to straighten, and with straighten, what you're trying to do is organize things, so that they are arranged in the order that they're going to be used. This helps to maximize comfort and efficiency. You want tools and equipment to be within reach, and your raw materials placed close by so that you can get to them easier. This helps to eliminate any fumbling or hesitating, so that you have exactly what you need when you need it. So let's examine how this would work in a manufacturing environment. Suppose you have a line supervisor that's implementing 5S in his sewing division of a garment manufacturing company. So the supervisor's already talked to the employees about sorting in the area, and they've removed all of the unnecessary items. The supervisor works with the employees to arrange their workstations and those items within their workstations in order to maximize comfort and efficiency. For example, the right-handed employees would have their scissors hooked within reach of the right hands, and the pieces that are awaiting work would be kept on the left-hand side of the sewing machines. That helps them to pick up their fabric and sew or cut threads without fumbling or hesitating, so they have everything right where they need it, when they need it. In addition, they would have the pieces awaiting processing stacked on a common set of shelves, marked and labeled as to where they belong. That way, the employee who prepares the fabric upstream stacks them whenever the designated spaces on the shelf are empty. The next step in the process is to scrub, which is making sure that the workspace is clean and neat and that any machines are clean or free of debris. This could be wiping down machinery or repainting machinery. And for daily maintenance, at the end of the day you would want to make sure that the floors are clean and the tools are clean and hung back where they're supposed to go, and it also involves regular machine maintenance. In the sewing example, you would want to have procedures set up where employees sweep their sewing area and clean their machine of debris after working on each piece. That way, at the end of the day, they just need to hang up their tools, tidy up their area, sweep the floor, and then wipe everything down. You could also set up a schedule where they're oiling their sewing machine on a weekly basis. In the standardize and sustain phases, you want to make sure that you continue to communicate the importance of using 5S. Within these phases, you would establish procedures for all the employees to follow. Now, in addition to just establishing procedures, you also need to make sure that you're providing time and the necessary tools to make sure that employees can do this. Finally, you want to make sure that you're rewarding the behavior so that you can promote it. When you think back to the garment manufacturing example, you would make sure that the supervisor revisits the first 3 S's of the 5S on a frequent basis, and continue to explain why it is important to standardize and use best practices. The supervisor would also make sure to set aside time at the end of every day for regular cleaning and tidying up of the areas. And the supervisor would also work with employees to set up protocols for regular sorting, setting in order, and shining of workstations. To sustain, you would want to set up a procedure where you're educating all of the employees through posters and other communication strategies. And you could set up monthly prizes, where you're awarding cleanliness. One of the key ways to reduce waste in a process is through the use of poka-yoke, the Japanese word for mistake proofing. Mistake proofing involves examining your processes to find places where human errors could occur and finding ways to prevent those errors from occurring. For example, there are connectors or plugs that fit in specific shapes. There are other poka-yokes in everyday life, such as a microwave oven. It doesn't run unless the door is shut. You have spell check on your computer, so it gives you a signal when something is spelled incorrectly. You could design parts so they can't be used incorrectly, and you can also have fail-safe cutoff mechanisms when you have risky procedures. There are 4 key types of poka-yoke devices. The first is a checklist, essentially a list of action items or steps that must be accomplished and checked off as they're completed or accounted for. So it provides a reminder as you perform specific action items. The next type of poka-yoke device is a screening device. Screening devices are design features that prevent processes, equipment, or tools from being used incorrectly. And so the key aspect of the screening device is that they help prevent incorrect use. The options can even be selected based on what's given to you in the options itself. And what's nice is that your screening devices remove the need to correct mistakes, because you can't even make a mistake in the first place. The third type of device is a signaling device. Signaling devices note when something is out of order or they're not conforming. Signaling doesn't stop the production process, but it gives you a visual signal to let you know that something's happened. For example, you could have a warning light that goes off to a machine operator to alert them to a problem, or a beeping sound to signal that the step is due to be performed. The fourth type of poka-yoke device is a control device, which is when the device is actually shut down when the error occurs. It's the most effective type of poka-yoke device because the process cannot be completed until the error or the defect is corrected. An example of this would be a production line that shuts down as soon as a defective part is detected. So let's go through an example of how this applies, given a manufacturing example with a screening poka-yoke. If you have a jacket that requires 10 buttons, rather than relying on the operator to always count the number and to make sure they've got 10 buttons, as part of their standard materials, it's useful to make sure that you already package them ahead of time, so that the 10 parts are the standard materials. That way, if any buttons remain after completing the sewing, the operator can tell that a defect has occurred. Standard work is a useful method that helps reduce waste within the processes. It's a method to document the best practices between operator and machine to make sure that you're running in the most efficient and standard way. Standard work is based on agreed-upon procedures and best practices. They're built from the bottom up, so everyone is involved in creating the standard work guidelines, and they're also involved in improving them. In this way, the operators or the people that are directly involved with the operations are involved in the process. The goal of utilizing standard work is to maximize your performance and also minimize your waste. You also want to make sure that your standard work is operating based on your planned takt time, so you're making sure that you're efficient in terms of what you're producing based on what your customer demand is. Standard work is built upon by the people that are actually performing the work, so that helps to make sure that you have the right documentation of the actual work processes, the action sequence, the quality and safety checks, and any other important work information. There are several key documents in the standard work package. The first one is a standard worksheet. The purpose of the standard work worksheet is to provide information on the overall flow of the process, to make sure there is a high-level documentation that shows the process itself, how efficient it is, and where there might be waste with the process. The 3 key aspects of the worksheet are, first, the work sequence that allows you to look through each step of the process and how the actual work flows through each of those machines throughout the production line. The second aspect is the cycle time that's provided. Based on what your actual production is capable of, you can document your overall cycle time. Then compare that to your takt time to see if you're capable of meeting your customer demands. And third, the standard worksheet provides information on the standard inventory and where those are located within the process. Other key aspects that are involved in the standard worksheet are the quality checks, which are denoted by diamonds, and safety checks denoted by pluses. These are noted at each step of the process where they occur. The second type of documentation in the standard work package is the combination sheet. A combination sheet is useful because it goes through the sequencing of the operation, provides a description of each operation, and then breaks down the time elements for each of those steps based on manual, automatic, or machine time, and the walk time. This is documented to capture the manual time, the auto time, and then any walking time to the next step in the process. This information can be compared to the takt time to see how you can adjust the process to make sure it's the most efficient. The next set of documentation that's useful in standard work are the capacity chart and the standard operating sheet. Capacity charts are used to chart the capacity of the machines that are involved within the process. Each machine number is documented and its process name. Then any manual or automatic time is documented, so you can look at the relationship between the manual and the machine time, and then document the time it takes to complete. Based on that, you know what your operating time is per day. You can look at the capacity and use this information to document or determine where any bottlenecks might be. The standard operating sheet is used to document the interaction of the employee and the operator with the equipment and tools, and communicate the standard timing and procedures. With a standard operating sheet, each activity is documented and includes the standardized work description. You can use this information then to also document information such as the layout of the process, the order of operations that are given, and any safety and quality checks. This gives you information on how to better improve your process. It's important that you make sure you have the appropriate training materials and documentation available, because this operates as your instructions to the operators and how they would implement the process. So, task and training materials must include detailed policies and procedures. In addition to the policies and the procedures, it's useful to have information such as the layouts, and how these policies and procedures, as well as any safety and quality checks, relate to your layouts, so you have an easy reference to document for the operators. And then finally, to make sure that you have information on cycle times, you can use this information then to compare it to the takt time, to see if you are capable of meeting your customers' expectations, and if not, you can use this information from your training manuals to further drive your process improvement efforts. Kanban and pull are two lean concepts that also help to reduce waste, and they're very closely related. Pull is how you pull material through your processes, and the concept behind pull is that you only produce product when you have a demand from your customer. When a customer orders a product, then you start pulling material through your process. And so in this sense, your production is relying on the pull, or your customer demand, rather than on the market forecast. If you focus on market forecast, you might build ahead and end up building product that the customer never orders. That's a form of waste because you might end up having to scrap that product if there's never a customer order for it. Or while you're waiting for a customer order, you're holding it in inventory, and you have associated inventory carrying cost and potential for the product to be damaged while you're moving it around. Pull focuses on the just-in-time philosophy, so there's no wait time throughout your process because you're pulling the material through it. If you think about a chain link, your signal to pull that chain would be from your customer, and as your customer pulls that chain link, then you start pulling products through your processes. By doing this, you're reducing your stock on hand. You want to make sure that you're holding minimal amounts of inventory. Aligned with the concept of pull is the concept of Kanban. Kanban is a Japanese word for signal, and ideally you want to use that customer pull as your signal that you need to produce product. The signal tells your operators when they need to pull materials into the stream. The advantage of using this methodology is that you're avoiding overproduction, because you're regulating how much material is moving through your process at any time. In addition, this step helps with your overall quality, because you're not holding on to products in various queues, and so you don't have the issue of potentially having a defect that might be lost in your inventory somewhere. Since you're reducing your inventory and you're reducing your batches, you have better control of your inventory. The disadvantage, though, is because you're pulling this just in time, you don't have as much of a provision for late deliveries of materials. Kanban and pull blend together. When you have an order from your customer, you're pulling material back through your process, through your product flow, and it's signaling to production that you need to make parts based on how many the customer ordered. This in turn signals a Kanban pull back to the supplier that indicates you need more parts, more supplies. By sending that through, you're moving your material forward only when you have that customer need. Let's explore an example of a Kanban pull. Let's assume you have a workstation that is communicating with the predecessor workstation, and they're signaling that they have a need for more material. They're doing this as soon as they've completed their work, and in that way, Kanban is a signal that says, I need to produce more, and I'm pulling that material from my supplier or my predecessor process. So I'm pulling it back through my process rather than pushing it. There are both opportunities and challenges for Kanban pull. The biggest advantages for the Kanban pull system is that it helps to reduce inventory, work in process, cycle time, turnaround time, and machine downtime. It also helps to really increase the visibility of quality issues because you don't have products sitting in inventory at various spots within your process. The challenges, however, are that for Kanban pull to really work, the material needs to flow at a steady rate in a fixed path. If you have large variations in your product or your volume, that mix interrupts the flow and it can undermine the system's performance. So it may not work well in processes where you have large variation within your products. The other obstacle is when you have unexpected variation in your market needs. These fluctuations hinder the pull system because it causes production to start only when there is a demand for a product. So you need to make sure that as a lean organization, that you can be flexible and really responsive to changes in your customer demand. Kanban cards and containers are a tool within Kanban pull. They can be physical or electronic. With a physical Kanban card, when you use up the material within a container, you have a Kanban card that typically goes back to some sort of a board. The board collects information so that you know when you've reached a certain level of Kanban cards, you need to produce that product again. Electronic Kanban cards capture the information such as the time, the minutes, the seconds, and how many products are used every hour and every day. Electronic signals are being sent back to tell the predecessor operation what parts and what mix of parts need to be produced. In this topic, we'll explore the Kanban pull process. The first step in Kanban pull is calculating safety stock, which is the minimum or safety level of stock required in the process. Essentially, safety stocks is excess inventory. This is material, whether it's finished product or goods from your suppliers, that you're holding on hand to make sure you have enough in place to run your business. You're doing this because you might have variations within your demand, and you want to make sure that you're accommodating those variations. But at the same time, you also want to minimize how much inventory you're holding on hand, and have just enough to make sure if you have a peak in your demand, that you're able to handle that. The more unpredictable your demand is, the larger the safety stock. The second step in the Kanban pull implementation is to calculate your lead time to replenish your materials. There are 4 key factors that affect your anticipated lead time: the time it takes to place an order, the time it takes to process that order, the transport time for those materials, and then the time to receive, unpack, and prepare those materials. Each of those 4 factors goes into your overall lead time, and you need to be able to capture that overall lead time to see how much safety stock you need to hold on hand. The third step in the Kanban pull implementation process is to determine your batch size. To determine your batch size, what you're looking for is how much product you need to produce in one continuous work process. In other words, this is how many pieces of that product you need to produce at once before you change over, and this is used to determine your stock level and your lead time. The fourth step in the process is to check and adjust your levels of requested material, so you need to take into account your current stock, your lead time, your batch size, and then adjust these as needed. Here's an example to illustrate the Kanban pull process. Let's assume you're working for a manufacturer of small electronics, and your company is introducing a new media player. The goal is to have this released by the holiday season. As a Six Sigma team, you're working at the company's manufacturing plant to set up the Kanban pull system. The first step of the process is to calculate the safety stock level of the materials requested. So your team determines that it needs a safety stock of 1 week's worth of production materials to meet variation outside of expected demand. The second step of the process is to calculate the lead time for the replenishment of the materials. Your team calculates that the manufacture and transport time of the components from the supplier to the target workstation is 4 days. The third step is to determine the batch size. In order to meet advanced orders, the team determines that a batch size of 200,000 units will satisfy your customer demand. And then finally, in your fourth step, you check and adjust your levels. So as a team, you do final calculations to check and adjust the levels of materials needed in light of those first three steps. And these final levels determine the appropriate placement of the pull cards within the process. Within the improved phase of the DMAIC methodology, one of the things that you focus on is improving overall lead time. It's important to understand the differences between cycle time and lead time, and how these relate to process improvement. Lead time starts when the request is made by the customer and ends at the delivery. Cycle time starts when the work begins on the request and ends when the item is ready for delivery. Lead time from point to point includes waiting as well as other delays. It's also affected by the actual versus planned speed in cycle time. In addition, cycle time and lead time have different units of measurement. Lead time is measured in time, minutes, hours, and days, but the cycle time is a rate. Cycle time is important because it has a major effect on productivity, and that leads into your organization's competitiveness and market share. So let's examine how you calculate cycle time, using an example with a three-step process for manufacturing a precision tool. Each step is completed by a different operator, and then the tool is handed over for shipping. So for each of these steps, you enter the observed time in your samples column. For this example, you have 6 observed sample times. Now, it's important to note that the norm is typically 10 sample times per task. Then you consider the most frequent value, which value has appeared the most often. For task A, that's 3. Then you're also examining to see which has the highest value, and in task A, this is 3.5. Finally, you're looking for the lowest repeating value, which appears to be task B, and it's 1.5. So this gives you information on what the most frequent value is. In other words, what is it normally taking, that step in the process, in terms of time? The highest value gives you an idea of where you might have peaks that you need to examine. And then your lowest repeat value gives you a good idea on whether there is a consistent lowest reading. So then, using this information, you calculate your total cycle time for the process by summing together the most frequent values for each operator. So in this example, you end up with a total cycle time of 7.6. One thing to keep in mind, you could have multiple operators performing the same work simultaneously, or you could have a single operator performing multiple tasks. So it's important that when you set up your cycle time worksheet, you design it in such a way that it reflects how your actual production process is operating. Now let's move on to calculating your takt time. Takt time is essentially your rate of customer demand. This should be the heartbeat of your process because it tells you how frequently you need to make a product or service to make sure that you are meeting that customer demand. Your takt time is equal to your available time per period divided by your customer demand per period. So continuing your example, let's suppose that you have a shift that lasts 8 hours. This is equal to 480 minutes, and so you're assuming that within 8 hours it's your total available time. So that means there is no break, no lunch that's taken out of that. And then let's assume that your customer demand is 120 products per shift. So to calculate your takt time, you would divide 480 by 120. That tells you that every 4 minutes you need to produce a unit. And so while you have examined this from a very simplistic standpoint, and you have considered 8 hours, it's important to note that your numerator is your actual operating time. So you need to subtract any time, if you have breaks, meetings, or other standard activities, from the net operating time. In this topic, we're going to explore the concept of reducing cycle time, an important element of the lean philosophy. Reducing cycle time offers several key benefits to an organization. First, it really helps to reduce waste within your process. Reducing your waste and cycle time enables a significant cost reduction for an organization. In addition, as you reduce your cycle time, you free up some of your availability and can increase your productivity. As you eliminate some of these waste and reduce your cycle time, you will have an increase in your quality and a decrease in your product time to market. All of these benefits help to improve your level of customer satisfaction. Reducing cycle time translates into quantifiable impact on your entire business. For example, if you reduce cycle time by 30 to 70%, which is not uncommon for Lean Six Sigma projects, there are several key benefits that you can quantify. That translates into a return on your investment of anywhere from 20 to 105%. You can see an increase of revenue of 5 to 20%. Reduce your inventories by 20 to 50%. Reduce your invisible inventories by 20 to 60%. Decrease your delivery lead times by 30 to 70%. And reduce your time to market by 20 to 70%. Besides these direct benefits, the dollar value amount that comes from a 1-month delay or accelerating your projects could mean millions of dollars for large companies. And as your cycle time is shortened, your quality also improves. The main key benefit of reducing your cycle time is that you are improving your customer satisfaction when you're able to get your product and service delivered on time. You can also experience the impact of cycle time reduction through 4 common business cycles: the pre-development cycle, the design and development cycle, the order-to-delivery cycle, and the customer service cycle. When you focus on reducing your cycle time in the improved phase of your Six Sigma projects, that helps to impact your overall business cycles. You can reduce your time to market, and by reducing your time to market, you're decreasing the time that you're actually able to deliver your product to your customer. As you drive through the improvement phase within the DMAIC methodology, part of your improvements should relate to how you could implement lean tools, such as continuous flow. Continuous flow means there's an absence of interruptions, problems, delays, or backlogs within your process. Continuous flow is more of a time-based methodology, where the focus is on reducing defects by improving the logistics. Continuous flow delivers a flow of products to the customer with minimal delay. Consider a product or service moving through a long production line. Any delays early in the process will delay later steps in the process. In a complicated process, upstream delays can cascade through the system, causing multiple time delay problems. Another characteristic of continuous flow manufacturing is the use of units made up of their smallest logical level, either in one piece or a small batch at a time. Right-sizing batches is important because batches that aren't the right size lead to queues, which lead to waiting, which ultimately leads to bottlenecks and delays, poor space and resource utilization, and longer cycle times. In a continuous flow layout, a group of machines or workstations is called a cell. Production steps are arranged in a characteristic tight sequence that flows through a U-shaped cell arranged for optimum operability and maintainability. Inside a cell, each workstation is organized to achieve continuous flow at the desired takt time. And a final key characteristic is that continuous flow uses a team approach throughout the process, which encourages workers to accept and lead the improvement initiative. It's important to provide training and encourage buy-in from employees and other process owners. With continuous flow, you ideally have a just-in-time process, where your material or product flows smoothly through your process without any interruptions. You can focus on setting up your supplies so that you're taking into account any peaks or valleys that might occur in your demand. And by doing this, you can really level load how your process would work and take into account any fluctuations or variability in that demand. Let's examine continuous flow using an example. Say a large manufacturing company that produces stock kitchen cabinets is working with the Six Sigma team to adapt its production facilities to continuous flow manufacturing. In the past, production has been plagued by quality problems, inconsistent work methods, large batch production, excessive inventory, and extensive non-value-added work. Through the Six Sigma initiative, some changes were made. First, the team determined that the old large batch process caused inefficient parts flow because parts are spread over a large area, requiring workers to take unnecessary steps to retrieve what they need. In addition, specialized machinery is located away from the main production line, increasing inefficiency. A new workflow was designed that utilizes smaller batches. Next, the production flow was divided into a series of U-shaped cells, consisting of individual workstations. Each cell was marked with new equipment and inventory locations. Material storage units were built into each cell. Team members also talked to employees about the benefits of continuous flow manufacturing and worked with them to design and implement the new system. Cell layouts were reviewed with process owners, and the employees were given the opportunity to provide additional input on the design of each workstation. Finally, training in new methods was given to each employee. Handbooks and documentation were provided at each workstation. Today's competitive market and customer expectations for diversification lead to more frequent setups and changeovers, which according to Lean is a waste. In this topic, we'll explore setup reduction and single-minute exchange of dies, or SMED, a useful process for reducing setup times. Product diversification means that you need to produce smaller batches and change over more frequently. And it also means that you typically have shorter production life cycles because customers are expecting changes more frequently within their products. Changeover and setup leads to non-value-added activities, so the goal then should be to reduce them. There are several benefits of setup reduction. If you're able to reduce your setup time, you can improve your quality because you can make sure that you are flexible enough to make changes to your products to meet your customers' demands. You're also able to lower your cost because you're not holding so much inventory on hand, because you are not focusing on producing as much as possible before you change over, as your changeover takes so long. By reducing your setup time, you are able to change over more often, which gives you much more flexibility, and you're able to better use and manage your resources. This also helps you increase your capacity, because you can change over more frequently. In addition, it reduces your lead times, because you're able to change over more frequently and produce products in time to ship them or deliver them to your customers. Finally, by standardizing and reducing your setup times, you're able to reduce your process variability. One of the most common methods for reducing setup time is single-minute exchange of dies, or SMED. With SMED, you're trying to reduce the time it takes from running one product to the time you start running another product. So essentially, when you finish running product A and you have the last good unit of production for product A, you then have all of the activity required to change over from running product A to running product B. Your changeover time is the time from when you make your last good unit of product A until you make the first good unit of product B. So this involves changing out fixtures, tooling, cleaning down the machine, doing any quality checks, making adjustments, and then checking the product again. And your overall objective is to get this time down to 0. One fun little thing to keep in mind, when you talk about single minute, it actually means that it's under 10 minutes. Another thing to note is that even though this concept came out of changing over dies, where the name of the methodology came from, this changeover time applies to any type of changeover that's necessary. For example, if you consider the healthcare industry, when you are changing from the operating room for one patient until it's ready for the next patient. That's changeover time. Implementing SMED has several advantages over traditional production line manufacturing setups, where it's common practice to produce large lots of a particular type of product and then switch over to another product. First, because you're able to change over more frequently, you can reduce your lot size. In addition, because you're making each type of product more frequently, you are not holding as much inventory on hand, so you can reduce your inventory. Because you can change over more quickly and you have a systematic procedure to do this, you will be able to reduce your labor cost and reduce any bottlenecks within your process. In addition, you can increase your usefulness and capacity of your equipment because you are reducing the amount of time it is down for a changeover. Finally, as you standardize your processes, you're reducing the scrap that's created while you change over your process, and you're putting in place tools and techniques to make your changeover efficient and effective. In this topic, you're going to explore the 6 core steps of the single-minute exchange of dies, or SMED, process. The first step of the process is to organize your setup operations. You want to go through and outline each step that's required for a setup, and you want to note whether each of those activities falls into a waste category, which is something that you can remove, if it's an internal setup or it's an external setup. An internal setup is something that's done internal to that operation, and so the process has to stop for that to be conducted. If you think about a piece of equipment, this would be changing out anything internal to the machinery. So the machine has to be stopped while you are inside, for example, taking out a fixture. Anything that's external can be done while the machine is still running. Now that you have organized your setup operations and know where the waste is within your process, you want to go through and eliminate that waste, which is step 2. And then the third step in the process is to convert your internal to your external. Again, internal operations are things that are done inside the machine, so your machine has to be stopped. It can't be running when you perform these activities. You could also think about this in terms of a hospital room, where you're changing over from one patient to the next. Nothing can be performed while you are cleaning and changing over that room. When it's external, these are things that still can be done. So you can still be performing activities. Or if you think about this with your manufacturing setting, your machinery can still be running. And so you want to convert as much from internal to external as feasible within your turnover tasks and processes, because anytime you're performing those internal operations, you are not producing parts. Okay, so now what do you do about those internal processes that you can't convert to external? That's where step 4 comes in, improving internal setups. You want to organize the workspace and decrease movement as much as possible, so that you can get in and do the necessary steps as quickly as possible, and then move back to running your operations. Next, you want to move on to improving your external setups. You want to provide checklists, for example, so that you can make sure that you have everything ready. When you shut down your piece of equipment, you have all of the tools, inspections, the next fixture, all of that ready to run your next product. It's also important because you want to make sure that it's organized, that you use such tools as 5S to have everything clearly located where you need it for the changeover. You could also use color coding to make sure that you've got the right components and parts for your next product, so it makes it easy to make sure you have exactly what you need. Finally, the last step of the SMED process, now that you have all of your operations in order, is to develop a standard operating procedure, or SOP, so you have documentation on how to go about performing your changeover. SOPs and standard work are related in SMED and often include visual aids and mistake-proofing measures to ensure we get it right the first time when setting up. A huge goal of any Six Sigma initiative is to reduce waste in processes, and an especially effective tool to use for that is Kaizen. Kaizen is a Japanese term, and it roughly translates to small incremental improvements. You can use Kaizen as part of your Lean Six Sigma improvement events to drive continuous improvements, using small incremental steps based on specific projects. Typically, Six Sigma projects result in improvements based on what you're implementing. However, there can also be a little bit of backsliding or degradation before you move forward with your next project. By driving and implementing your Kaizen events into your process, you can have further improvements before you start your next project, and you can start noticing that further improvement. Kaizen events are particularly useful when you're dealing with capacity constraints, setup reductions, acute quality issues, or safety issues. Building Kaizen events into your Lean Six Sigma projects helps to improve the company's bottom line, and helps to ensure that you're improving upon those original improvement solutions. Kaizen, like other tools, is implemented in steps or stages. In the first step, you state your problem and solution. So you would start by developing your problem statement, determining what your required goals, objectives, and deliverables are, and communicating these with your stakeholders. A common Lean Six Sigma tool you'll use in this phase is a Kaizen event worksheet. The second stage is to gather and train your team. In this stage, you're choosing your project team. It's in this stage that the project team members are chosen based on their individual talents and their collective ability to work cohesively. Team members receive training for the specific tools and tasks needed during the project. Finally, a schedule is developed to ensure that the key project milestones are implemented in a timely manner. In the third stage of Kaizen, team members collect data on which to base decisions that will allow them to manage the actual Kaizen event. Based on the gathered data, metrics are formed, and the current process is mapped through the use of various Lean and Six Sigma techniques and tools, such as flowcharts, time study sheets, control charts, process capability ratios, and Anova. In the fourth stage, the team analyzes the data gathered in Stage 3 to identify areas for improvement, formulate ideas, determine the root causes of problems, and evaluate proposed improvements. Tools typically used in this stage include fishbone diagrams, 5S, capacity charts, and standard operating sheets. During the fifth stage of Kaizen, the team makes improvement recommendations and ranks priorities based on the analysis of data completed in Stage 4. Recommendations are prioritized based on estimated financial savings and the amount of waste eliminated. It's now that roles, responsibilities, requested resources, metrics, and measurements are revised for each process improvement. Common tools used include project plans, action plans, flow diagrams, and Gantt charts. The sixth and final stage is the action stage. This is where the team communicates the plan and implements and monitors changes. Other stakeholders, such as suppliers or functional employees, are often involved in making these improvements. Regular update meetings are held, and progress is measured using metrics. Documentation is completed. A Kaizen storyboard is created, and the process improvements are assessed to determine if they can be migrated to other areas. In this stage, you'll typically use a rollout plan, stakeholder training, and the Kaizen storyboard. It's important to note when you should use Kaizen. It's best used when the problem is clearly understood. If you don't understand your problem, then you really need to drive down and understand the problem before you move forward with it. Kaizen is also very useful when the team is resistant to change, because you're going to go through and map the process, and through each of those 6 stages, you're going to have the team involved. Kaizen also provides a quick turnaround. Therefore, it's very useful when you require immediate results. It's also very useful when you go after low-hanging fruit. In other words, Kaizen is useful when your solution requires fairly minimal effort. And because Kaizen provides those immediate benefits, it's useful when you have projects where your resources are too limited for long-term process improvements. There are 3 types of Kaizen events, and each has its own duration. A Kaizen project is typically 2 to 4 weeks. A Kaizen blitz typically occurs over 3 to 5 days. And a Kaizen super blitz typically occurs over 1 to 8 hours. Each of these types of event has a significant difference in duration. Which one you use will really depend on the goals of the project and what you're trying to accomplish. You could use a 2x2 grid to determine the type of Kaizen event that's appropriate for your project, or if Kaizen is not appropriate and a long-term continuous improvement approach would be best. You consider the effort that's required in terms of time and cost on the x-axis, and then the impact on performance on your y-axis. The impact of performance refers to efficiency, cost, and customer satisfaction. So if the effort and the impact are low, then you will have a fair project. If your effort is high and the impact on your performance is the worst, then this is something you want to try and avoid. If your effort is high and your impact is high, you would need to consider how you would separate these out into smaller projects. Using this type of grid, you can identify if Kaizen is appropriate and which type to use. Kaizen events are ideal when your effort is low, but the impact on your performance is high. Kaizen projects are events that focus on improving the value stream. Typically, these projects unfold over weeks, but the Lean methodology also uses a technique called the Kaizen Blitz. A Kaizen Blitz is a planned Kaizen event that's conducted over a very short period of time, typically 3 to 5 days. And within that short time period, you're trying to enhance your process improvement efforts by eliminating non-value-adding activities. A Kaizen Blitz differs from a Kaizen event because it's much more focused and has a considerably shorter duration, but you're still searching for a tangible outcome. In contrast, Kaizen events are focused on improving the entire value stream, meaning these projects typically occur over several weeks. Now it's time to explore the difference between a Kaizen event and a Kaizen Blitz, and how that differs from Lean and Six Sigma. In a Kaizen Blitz, you're trying to do these events over a very short period of time, again, typically over 3 to 5 days. So you really want to go out after those low-hanging fruit with very specific goals. Lean projects are typically occurring over several weeks. You can still go after some of the low-hanging fruit, but you are going after things that are a little higher up from those smaller Kaizen Blitzes. In Six Sigma projects, you're typically going after what's considered those best or sweetest picks at the top of the tree. Six Sigma focuses on the problems in which you don't specifically know the answer or the root causes of your variation within your process. You spend much more time and effort on trying to understand the problem and the true root causes. Even though a Kaizen Blitz focuses on the low-hanging fruit and not the higher goals in a wide-scale Six Sigma initiative, a Kaizen Blitz still fits in very nicely with Lean Six Sigma efforts. You would still have the same need for management and sponsor support from the top of your management chain. And you would also need to have that clear foundation with your Six Sigma team and your workforce engagement. In a Kaizen Blitz, you'll use tools such as 5S, waste reductions, cycle time reductions, SMED, and flow, and pull. You'll also have 5 phases of planning, measuring and analyzing, brainstorming, implementing, and fine-tuning and confirming. Sounds very similar to the DMAIC methodology, right? So your Kaizen tools and process integrate very nicely into your Six Sigma methodology and tools. So how does a typical Kaizen Blitz flow? Well, on day 1, the project kickoff meeting communicates the purpose of the project to the team. The problem statement is created and the scope is narrowed and defined. Project ground rules are established for roles, responsibilities, workload, resources, and boundaries. A work plan is created to document project activities, estimate time and resources, and identify measures of progress. You and your team will decide which tools will be used to gather and analyze data. On day 2, team members begin to collect data and conduct interviews with workers. They directly observe the current processes, take measurements, and identify items from the 7 categories of waste. A process map of the current work area or process is developed. Your team will continue to analyze data as it's gathered, and will begin developing metrics for workspace use, distance traveled, throughput rates, and lead times for each step in the process. Ideas for waste elimination are prepared for presentation the next day. On day 3, you'll meet with your team to brainstorm improvement ideas for fixing the constraints and eliminating the waste identified on day 2. Each idea is evaluated in light of the collected data and the resources required to implement it. Tools such as affinity diagrams and checklists help the team reach consensus about which improvements to implement. Once the improvements have been determined, the team establishes what will be needed in terms of equipment, tools, templates, documentation, and work standards to carry out the improvement. On day 4, you'll incorporate the collected data and approved recommendations for process improvement into the project's action plan. Team members are assigned responsibilities, and the project work plan is expanded and updated. You'll also create a timeline that sequentially offers improvement actions. During the day, you and your team members will meet with operators and the process owners to explain and demonstrate process changes and new procedures. The improvements are implemented, and then throughout the day, you will observe, evaluate, adjust, reobserve, reevaluate, and readjust processes in a refinement cycle. And then on day 5, you and your team refine, approve, and document process changes. Standard operating procedures are drafted and then tested to confirm that measurable improvement has been accomplished. Final refinements are made, and the process is documented as standard work. Changes that require time to implement are incorporated into a future action plan. Finally, the project is documented into a Kaizen storyboard for presentation to everyone impacted by the new processes. In this topic, we're going to explore the process of applying Kaizen using an example. The first step in the process is to state the problem. When you are stating the problem and selecting the problem for your event, you need to make sure that you are linking this to the organization's strategic goals. You also want to consider which projects could eliminate the most waste or cost, and what benefits accomplished in this project would have on the organization's profits. In most organizations, you have multiple projects that you're trying to select from, so you could set up a rating table to prioritize your various projects. Say your large manufacturing company has identified 2 potential projects. The first is a die-cast process, and the second is the assemble and pack process. In order to rate each of these projects, you would have to set up several key business drivers. Based on those key business drivers, you rate each project using a rating scale where 1 equals no impact, 2 is equal to a smaller impact, 3 is a moderate impact, and 4 is a high impact. Each of the project's business drivers are rated, and you would sum up each of the individual ratings to get a total value. Then you would take an average based on the number of business drivers. In this example, the assemble and pack process has the highest average, so this would be the project that would have the biggest benefit for the organization. Once you've selected a target process to improve, you need to gather and train your team. Usually, event leaders are the first ones to be chosen. They then provide leadership to the Kaizen events. The team should also include a lean facilitator, as well as an executive sponsor, a value stream champion, a team lead, and an event coordinator. These leaders should meet regularly during the planning process to monitor progress and provide necessary resources. The facilitator will direct the selection of members for a cross-functional team. An important part of team building is developing an event charter. This document is updated and goes through several reviews before the planning process ends and the event can begin. It outlines the scope of the event, the team's membership, and the schedule for the event. After gathering and training the team, you collect and analyze data. For your example, using videos or photos, you observe and record the current process. Your aim is to gain a full understanding of the process and to gather data such as cycle time, defect rate, and number of operators, so that you can develop current maps of the process. The team may need a selection of tools to gather data and use it to create visual maps. Useful tools for creating baseline data include cycle time flowcharts, operator cycle time charts, time observation sheets, Pareto charts, and analysis of variance tools. In the manufacturing example, the team uses time observation sheets and operator cycle time charts to gather baseline data. Once the data is gathered, you can create current state value stream maps, 5S maps, workflow analysis maps, and cycle time flowcharts. Using the data gathered, the manufacturing Kaizen team creates a current state value stream map of the process. It also creates a 5S map of the assembly and packing area. Once the baseline data has been gathered, team members identify waste in the process, along with its causes. To do this, they can categorize steps as value-adding or non-value-adding, and check for issues such as waiting and unnecessary motion. You can use different tools to analyze the root causes of the waste you identify. These tools include the 5 Whys process, cause and effect diagrams, Pareto charts, and check sheets. For example, the 5 Whys tools requires you question why waste occurs, and keep questioning until you find the root cause of the problem. The Kaizen team at an electronics manufacturer notices that operators spend a lot of time waiting for components to arrive, and that some of them have to wait while the first operator completes a task. The team also notices that operators make unnecessary movements, bending, and searching for tools and packing materials. To analyze what is causing these wastes, the team questions why the operators need to wait and why they have to move around so much. They determine that the operators receive components on a push system, that the cycle times for the respective tasks are different, with the result that the line is unbalanced, and that the layout of their work area is inefficient. Once data is collected and analyzed, you move to the final 2 stages, making improvement recommendations and implementing and monitoring changes. At this stage, waste and its root causes have been identified. The team needs to brainstorm ideas for improvement and then find a way to implement those improvements. During brainstorming, the team reviews the current state map and searches for ways to improve it. All ideas are welcome during an initial, non-judgmental process. The Kaizen team for the electronics manufacturer is targeting a specific electronic product and the final assembly process for that product. The team identified waiting, motion, and unbalanced lines as key wastes. They propose a Kanban system, 5S, line balancing, and the use of standardized work to improve the process. Other ideas include using taller work tables to minimize bending and use inventory trolleys on wheels so that operators don't have to walk to the stores to gather materials as frequently. The team must then evaluate and prioritize the improvement ideas they have generated. They create drafts, samples, maps, or prototypes of the planned improvements for testing. This process is similar in both service and manufacturing environments. The Kaizen team for the electronics manufacturer prioritized the use of 5S, line balancing, and Kanban to improve the assemble and pack process. The team tests the potential layout for the area using sticky notes for each piece of furniture in the area. This is part of their 5S strategy. Once you've tested the proposed changes and determined which you want to use, you move to the implementation step. you now need to develop a schedule for going live with the improvement. You may also need to consider a specific implementation training for your team. When assessing what to cover in staff training of the electronics manufacturer, the team might realize that operators need to know where everything is located after the 5S initiative. The operators must also know what they need to do in terms of assembly and packaging tasks in the new balanced line. Finally, the operators supplying components for this process need to know what to do when the Kanban is triggered. Once everyone is prepared, the team rolls out the new process and a planned start date. The team also needs to monitor the Kaizen event. This includes following up regularly on results and improvements, creating standards, and communicating results and process audits. This helps to solidify the new process and may highlight further improvement needs. In the Analyze phase of the Six Sigma Define, Measure, Analyze, Improve, and Control methodology, the focus is on determining the factors or those key inputs that impact the variation and the mean of the output. And in the Analyze phase, you determine what the optimal setting should be based on different factors to help control and reduce that variation. But there's always going to be variation within a process. It simply cannot completely be eliminated. And even though you can't eliminate variation, you can certainly take steps to identify and control it. And that's where Statistical Process Control, or SPC, comes into play. Statistical Process Control, or SPC, helps you identify where there is variation within a process and helps you find ways to control the impact of that variation. Statistical Process Control was developed in the mid-1920s by Dr. Walter Shewhart. He also developed the associated tools, one of which is the control chart, the most commonly used of the statistical process control tools. Using the DMAIC methodology, you begin by defining the problem, and then as a team, you decide what the desired state should be. In the Measure phase, you create the baseline for your data. In the Analyze phase, you begin to identify what your key factors are. Then, in the Improve phase, you optimize those key factors. So now that the process has been improved, you can begin the Control phase, where you want to make sure you're maintaining the gains that you've achieved by considering ways to control the process over time. Typically, the Control phase is in place for 3 to 6 months to ensure that there's no backsliding within the improved process and that the gains are being sustained. During the Control phase, you determine if and when a process is out of control. In order to do that, you need to understand what an in-control process looks like. When processes are in control, the mean and standard deviation are consistent over time, meaning there is a consistent output from the process. When a process is unstable, there are points outside of the control limits. A stable process has all of its points consistently within the control limits, and it forms a stable distribution of the mean and standard deviation over time. Let's consider two terms used in relation to process control: process stability and process capability. The key difference is what you're comparing your process to. Process stability is a stable process, which may be referred to as the voice of the process, that falls within your control limits, which are based on the variation within the process. A capable process is compared to the customer's specification limits. Process capability, then, is the comparison of the voice of your process to the voice of your customer. There are 3 key objectives for statistical process control. The first objective is monitoring the performance of your process. The second is to identify the variation within your process and its causes. This helps tell you when you need to take action and when you should not take action. Once you understand the cause or causes of the variation, you focus on the third objective, controlling and improving your process performance based on how your process is currently operating. In order to monitor process performance, you need to examine it from various perspectives. These various perspectives include simple graphics, like Pareto and run charts that show process data and trends, standard control charts that show variation compared to statistical limits, and specification control charts that show variation compared to customer requirements. Control charts help you to determine if a process is stable. A stable process is predictable and allows further improvement in process capabilities, which tells you how your process operates and how the natural ranges within your process compare to your control limits. Remember that this looks at the voice of your process because the control limits are based on the process itself and not based on the specification limits. The control chart can be developed into a histogram that looks at the variation within your process. This information monitors process performance that helps you see how the process is operating and whether there are specific trends within the data that are signaling an out-of-control condition. You can also create a specification control chart, which compares process variation to customer specifications. Examining process performance from multiple perspectives using control charts, run charts, and histograms give you information about the centering of the data and the variation within your data. Based on this information, you can make management decisions based on when a process needs to change, or if it can just keep running. When variation is detected, it's important to determine the cause. There are two types of variation: common cause variation and special cause variation. Let's explore each one. First is common cause variation. Processes are always going to have natural variation that occur within them. That natural variation comes from basic changes within a process, such as tool wear. For example, if the process involves printing receipts, there will be changes within the variation of printing quality due to changes in the printer ink or toner. That natural variation is normal and expected, and acts as a signal that you need to change the ink or toner. However, the variation that's more concerning is special cause variation, which indicates a process may be out of control. Special cause variation is something that can be quickly identified. It can be identified by data points outside of the upper and/or lower control limits, or by upward or downward trends of data points in a row. Special cause variation is also known as assignable cause, because when it happens, you can quickly assign a cause to it. It's up to the person directly involved within the process to fix it. For example, if you're running a piece of equipment and a tool breaks, the reading from your tool break might cause an out-of-control data point, but it would not require the action to get management involved. The person directly involved with the machinery would be able to change the tool. It's important to understand the difference between these two types of variation as a Six Sigma professional. Knowing the cause of the variation determines whether action needs to be taken to correct it, and if so, what action is needed. In other words, adjusting a process in response to common cause variation, also known as natural variation, could actually introduce more variations into the process because of over-control. Failing to adjust a process in response to special cause variation could lead to more process variation due to under-control, which could lead to more potential scrap for the customer. Therefore, it's important to use statistical process control to identify the difference between special cause variation and common cause variation by looking at the different types of runs of data and tracking trends. The main objective of statistical process control is to control and improve process performance by focusing on reducing variation. The Taguchi loss function was developed to look at the loss created from variation in a process. The essence of the Taguchi loss function is that anytime you have a process that's not running on target, there's a loss. That loss and its impact on the customer or the organization and society can be quantified. What this function does is to help you get away from the goalpost mentality, which implies that anything within the specification limits is equally good, which, according to Taguchi, makes anything within the specification limits acceptable to the customer, but any variation from the target still has a cost to society. That's not true. As a customer, there's a loss associated with the product when it does not hit the target. The difference in a loss from even a minor change shows that customers would probably be equally dissatisfied. But just because there's that small difference between being on either side of the specification limit, it makes a difference with the goalpost mentality of whether the product is good or it's bad. Chances are that slight difference would still make the customer dissatisfied. There are a number of benefits to ongoing statistical process control. Because you're monitoring trends in a process, you can detect and give immediate attention to any special cause or assignable variation very quickly. Effective monitoring also helps reduce the need for inspection. This leads to shorter and more consistent cycle times, and it increases predictability and reliability as processes improve. Finally, better monitoring of improved processes ensures that the improvement is sustained, and avoids potential backsliding from the gains achieved. As you implement statistical process control, there are several key considerations to take into account. The first one is the buy-in from every member of the team. This means everyone from the processors who are using the process to make sure they actually use the statistical process control methods in place to the managers who approve the costs. The cost for statistical process control is in the initial development of the control limits, as well as whether the method of tracking is a paper and pencil process or an automated process, where the data is automatically uploaded. They both have costs associated with them, whether it's the time of the operator to plot each data point, or if it's the cost of buying equipment to handle it automatically. The second buy-in is that everyone involved must understand the need to investigate the process defects and then correct them. The second key consideration is to avoid over-analysis. Over-analyzing limits what you can accomplish. For example, there's no need to create a control chart for every single process, product, or service, or every aspect of the selected processes, products, or services. Start by focusing on the key process aspects. The third key consideration for SPC is that you need to understand that you're not focusing on the team member performance. The focus should be on the actual process issues to understand where the process variations come from. The goal of SPC is not to intimidate and reprimand operators. You want to make sure that the people working on the process are empowered to make decisions based on how the process is operating. Process owners should have control over the process so that they can record its behavior and have the authority to change the process as needed. SPC is a toolkit, and therefore it does have certain limitations. SPC is very useful because it provides immediate, quantitative feedback on process behavior, enabling process owners to make changes as needed. But it's important to note that SPC is simply an indicator of process performance. It's not a complete quality assurance program, and so does not actually fix process problems. It just provides an indicator that something is happening within a process that needs to be investigated. The final consideration is to remember that control charts are the primary tool and the backbone of SPC, and represents the voice of the process. The center line represents the mean of all the data. The upper and lower control limits represent the variation in the process being controlled. These values are calculated based on the data collected as part of SPC. The main purpose of using a control chart is to determine process stability. In other words, whether the mean and standard deviation are consistent over time. There are 4 key reasons for using a control chart. The first is to monitor the process to determine whether it's stable. The second is to find root causes of special cause variation. Process control charts make it easy to see variations in the process, and based on that, to determine the root causes of the variation to make further process improvements. Using control charts to help you improve a process so it's stable enables you to predict a range of your process outcomes. And finally, control charts are used to analyze process variation patterns over time to identify any patterns in the process that can be further improved. Let's examine the key parts of a process control chart and how they link to some of the assumptions you'll use them for. The first aspect is the mean, or the center line derived from the statistical average of the collected data. This represents the mean of the process, whether it's x bar or mu. The control limits are based on the voice of your process and come specifically from the data to calculate the upper control limit, or UCL, and the lower control limit, or LCL. The control chart itself then gives you information about the central tendency, dispersion, and spread of the process. That enables you to relate the spread of the data to the actual control limits. It's important to note again that the control limits are not equivalent to specification limits. The control limits are based on the data itself, but the specification limits come from customers or regulatory agencies. The point is that specification limits are given to you by someone else, whereas the control limits are actually calculated based on the process data itself. A key assumption about control charts is that they follow a normal distribution. So when you calculate the upper and lower control limit, they're essentially equal to the mean plus 3 standard deviations for the upper control limit, or the mean minus 3 standard deviations for the lower control limit. This is how you're able to account for about 99.7% of all of the data points within the control limits. Anything that falls outside of that is considered special cause variation. Let's examine how a control chart is created. In the first step of the process, you plot the process or product data of interest itself. For example, this could be the average weight of a bag of chips or the number of escalated calls in a help desk shift. The second step is to draw a line to connect those dots. This gives you time-ordered series information. And essentially at this point, you've created a run chart. To take this into a control chart, the third step is to draw the center line, which represents the mean of the data. The fourth step is to add the upper and lower control limits. Any values within your UCL and LCL represent the normal amount of variation that would provide a consistent process over time. These are calculated by taking plus or minus 3 standard deviations from the center line. Any value that falls outside of the UCL and LCL are considered excessive variation, which is attributed to something other than normal causes of variation that you expect to see within your process. As a Six Sigma professional, it's important to know when to use each type of control chart. There are several types. The first consideration is the type of data you're working with: variable data or attribute data. Variable or continuous data is based on the quality characteristic that involves data that is measured and expressed numerically. For example, length, volume, temperature, or time. This type of data lends itself to variables charts. If you're charting only one sample at a time, you would use the IMR, or the individual moving range chart. If you have multiple samples, then you'd use the X by R chart, or the X bar S chart. Attributes charts, on the other hand, are used for discrete data, such as data associated with product characteristics, that can be evaluated with a discrete response. For example, it could be pass or fail, yes or no, good or bad. In that case, you're typically plotting the number of defects or the number of defectives. If the data is count data, you'd use a C chart or a U chart. If it's classification data, then you'd use an MP chart or a P chart. Let's examine each of these charts in more detail. The first chart is the X bar and R chart, which is a variables chart, used with variable or continuous data. It actually includes two different charts: the X bar chart to track the sample mean and the R chart to track the sample range. They're typically represented with the X bar chart on the top and the R chart on the bottom. These charts are typically used with samples of less than or equal to 9. For example, let's say you're monitoring a process where every hour you pull 5 parts. In the first hour, you pull 5 parts and take the average of those 5 parts and plot it on the sample mean chart, or the X bar chart. You'd also determine the range of those 5 sample parts and plot that on the R chart. Then, in the second hour, you pull a new sample of 5 parts and plot the mean of that sample on the X bar chart and the range of the sample on the R chart. You continue doing this for a given time frame and plot each sample in both charts. The next variables chart is the X bar and S chart. This chart is typically used when the sample size is greater than 9. As with the X bar-R chart, the X bar chart is on the top and the S chart, which represents the standard deviation, is on the bottom. You use the S chart because when you have a sample size greater than 9, the standard deviation is a better representation of the variation in the sample than the range is. So, for example, let's say you pulled a sample of 15 parts. You take the average of those 15 samples and plot it on the X bar chart. And then for the S chart, you determine the standard deviation of those 15 samples and plot that on the S chart. So X bar S equals sample mean over sample standard deviation chart, whereas X bar R equals sample mean over sample range chart. Now, let's move on to the third type of variables chart, the IMR. The IMR, or individual moving range chart, is used when you're only pulling one sample at a time. As with the previous two charts, this chart is also represented by two charts, with the mean plotted on the top chart similar to the X bar chart and the range on the bottom chart. However, because you're only pulling one sample at a time, there's only one individual mean plotted for each interval. So for the range chart, you're determining the range from one sample to the next sample. This is called a moving range. When the mean is plotted for the first sample interval, the moving range would be blank. But when the second sample is taken, you would then plot the range from the first part to the second part. So the moving range is the difference between each of those subsequent readings. The third sample interval would be plotted as the difference between the second and third sample, etc. So these are the variables charts. X bar-R for samples less than or equal to 9, X bar-S for samples larger than 9, and IMR for samples of 1. Next, let's explore attributes charts. There are 4 different types of attribute charts: the C, U, NP, and P. The C and U charts follow a Poisson distribution. These charts contain the raw count of the total number of defects, without categorizing them as defective or non-defective. A C chart is used when the sample size is constant. On a C chart, you plot the number of defectives per subgroup or sample. For example, you might measure defects by day, batch, or machine. A U chart is used to plot the average number of defects per unit, and because of this, the sample size is not constant. The key difference here is that a part could have multiple defects per part, so this chart takes that into account. Notice that the control limits on the U chart are not straight as they were in the C chart. This is because the sample sizes are varying. So, a C chart is used to plot the number of defects in a sample, and the U chart plots the number of defects per defective unit in the sample. The NP and P charts are used to plot data for subgroups of a sample. The NP chart is used to plot the number of defective or non-conforming units when the subgroup size is constant. Because the subgroups are equal in size, converting defective counts into proportion isn't really necessary. This is where the P chart comes into play. The P chart is used to plot the proportion or ratio of defective units within the subgroup. You use this when the subgroups are not of equal size, so the subgroups are not constant. As with the U chart, the control limits on the P chart also do have straight lines because each plot represents varying sample sizes. The P chart is useful when you have a sample size of 50 or more. So, C and U charts are used with samples, and P charts are used for subgroupings within a sample. Now, let's dig a bit deeper into the different types of variation on a control chart. Common cause variation is a natural variation that occurs within a process. These are things that affect the entire process and aren't specific to one type of machinery or one step within the process. Special cause variation occurs when something specific happens within a process. It's often referred to as assignable causes because you can typically pinpoint what happened within the process. There's something specific that happens which immediately creates a difference in your output. As mentioned, common causes are normal wear and tear on your machines. They're natural changes that occur in the process over time. The data points fall within the UCL and LCL and don't show specific trends in terms of changes in the mean and standard deviation. Common causes include such things as normal wear and maintenance on machine, poorly written standard operating procedures, or poor work environments, including issues with things like lighting, temperature, and ventilation. Special cause variation is a specific change that happens within a process. You can pinpoint when it occurred or assign a cause that happened within the process. For example, you could have a conflict with existing software, or the process might have slowed down because of a change in the software program. Or you could have a lack of operator training and skills needed for the process. Special cause variation, in and of itself, doesn't necessarily make the product or service defective. Special cause variation causes the process to be unstable or out of control, and you must compare the process to the specification limits to know if you actually have a bad product, or if there are economic issues by not meeting the target. To do that, you need to compare the overall process width to the specification width. That being said, it's important to note that if you have an out-of-control process with assignable causes or excessive variation, you have a greater chance of producing defects. It's that unpredictability from special causes that leads to lower quality goods and services and more rework and scrap and waste in a process. One of the goals in a Six Sigma project is to control the special cause variation. You want to make sure that the process is stable over time, as this helps to minimize the potential of quality costs. Let's examine more closely some of these patterns that show you when you have special cause variation within your process. One example is when you have an upward or downward trend in a process. This is a sign that you have a lack of randomness within your data. You would expect, based on natural variation within the process, that the process would have points where it goes up and then down. Another example of a sign of special cause variation in a process is when you have a spike within your data. These spikes could be outside of your control limits. A third sign is when you've got cyclical type data. You would expect some sort of randomness within a process, but you would not expect a cycle where the process goes up and down, up and down, up and down. A fourth sign is when you have a shift within your data. You'd expect to have points within certain ranges of the control limits, but you wouldn't expect over time that you'd have a shift in your data, where your data points fall within a narrow range around your center line. This could be caused by a change to the process. If that's the case, you need to go through and recalculate the control limits. However, with a normal process, you'd expect variation right around the center line. It's important that you choose the right number of variables for your statistical process control efforts. There are several ways you go about this. You could choose variables that are part of your domain process improvement project, or you could choose variables that need to be monitored as part of an SPC activity that's done independently for a project, to monitor and analyze those variables because those processes are currently not control. It's important to make sure you select the right variables, because if you select too many variables, that leads to wasted time and effort, which you want to avoid as much as possible. If you select too many variables, you can't focus on the ones that are really critical, so the benefits decrease and costs increase. There are some caveats that go along with choosing the right variables. It's important when you're doing the Six Sigma project that those variables you're trying to improve typically and naturally come into the control phase, where you can perform statistical process control. However, when you're running other process improvement efforts, you want to be careful that you select the right variables, based on what your customers' needs and expectations are. Also, if you're running a long-term Six Sigma project or continuing activities, you might want to actually broaden the net on those long-term projects, to make sure that you're looking at the number of potential variables that are important as part of the specific DMAIC methodology, as well as to control your overall process. There are 4 key categories of variables that are important to take into account when you're selecting the right variables. The first category are variables that are difficult to control. For example, if you have a variable that's associated with a high defect rate, you want to focus your efforts on reducing those defect areas by controlling your process through statistical process control. Another example of a process that would be difficult to hold is a process that has considerable variation. You want to be able to examine a process and understand the variation from that process in terms of special cause and common cause variation. The second category includes variables that are tied to customers and their key imperatives. You want to make sure you're taking into account those variables tied to customer, organizational, or regulatory imperatives. Customer complaints are things that your customer would be unhappy about with your product or service. That's a variable you might want to consider using for a control chart. Also, you might want to choose variables tied to a specific customer request. If the customer is requesting a key aspect of your product, then that means it's something that they are particularly interested in, and so that should be an area of focus. For example, a cellular phone manufacturer might know that their customers don't really care about multiple ringtones, but they do care about battery life. So the battery life might be something that you should focus on for a control chart. The third aspect is standards. If your organization needs to adhere to applicable organizational or regulatory standards, you might want to use control charts to make sure that your process is stable. For example, if you have a company that wants to expand their organization and build on a new premises, they need to make sure that the new building meets environmental standards, which is probably important to the company. Another aspect to take into account when selecting variables for statistical process control is to look at the critical dimensions of the product or process that's under consideration. Critical dimensions could be things that affect human safety or the environment, and since there could be adverse risks, you want to make sure that you're closely monitoring these. Customers typically buy products for a specific use. and if that use degrades for any reason, the customer is going to be unhappy with the product. So you could conduct a statistical process control on those key aspects that tie to the product's use. In terms of reducing risks, anything associated with processing failures or aspect of the product or service that cause high internal cost could be important. That is something you'd want to tie into to help control your process. Variables that help control processes are those factors proven to have a high impact on ability to meet specifications consistently. For example, if temperature is known to be critical to the customer in processing, it would be a key variable to help control the process. The fourth category of variables are those salient or known variables. These are the variables that you know, based on past historical data, usually exhibit special cause variation. You could also monitor root causes for which you know what the true root causes are, because then you could conduct statistical process control on those root causes. As you do this, the variables will be measured by the person that's actually doing the charting. They would have insight into how the processes are operating. Another good variable to track would be variables that are leading indicators. Leading indicators are important because they give you information about what the output of the process will be. Let's explore a scenario to illustrate how to select variables for statistical process control according to certain criteria. Assume for this example that you're part of a Lean Six Sigma project team at a toy manufacturer. Over the past few weeks, you've received several complaints from customers about the brittleness of certain motorized toys and their inability to maintain shape after only a few weeks. This is concerning to the company and management in particular. Their concern centers mainly around the customer complaints and the excessive variation within the products. Within the organization, cost control and customer satisfaction are key. Your team finds that the variations mostly occur in the toy's base structure as it goes to the molding and stamping process. And you've determined that the customer complaints about brittleness and shape also relate to the base structure. Using this information, the team is able to identify 15 probable input and output causes and variables in the process. Each of these could be related to variation. As a team, you were able to eliminate 7 of these variables at the primary stage because they aren't critical to product quality or customer requirements. The 8 remaining variables are the quality of liquid plastic that's poured into the die temperature, the liquid plastic temperature, the liquid plastic density, the injection pressure, cooling time, material elasticity, and the tensile strength of the base structure. Because there are 8 variables, it would be too time-consuming and expensive to conduct statistical process control. The team needs to narrow down the variables to focus on those variables that are critical to cost, variability, and customer satisfaction. They start digging into each of these characteristics more deeply and determine that the brittleness is directly associated with the liquid plastic temperature. The base structure is brittle as it comes off the mold when standards aren't followed. The team is unable to prove that the liquid plastic density could also be directly related to the base structure having low tensile strength. However, considering its significance to customer satisfaction, the team decides to monitor this variable separately. As part of the process of narrowing down the variables, the team talks to the production manager, who reports that the material is often discarded due to the liquid plastic overheating, or because the liquid plastic density strays away from the technical standards. Next, you note that the quality of liquid plastic poured in the die is controlled manually, causing lots of rework and waste in the process. Finally, you conduct a factor analysis with a large sample. This reveals that other variables, such as cooling time, die temperature, and injecting pressure, aren't major causes of variation. Based on this analysis, you decide to use control charts to monitor 4 key variables out of the original 8. Quantity of liquid plastic poured in the die, liquid plastic temperature, liquid plastic density, and tensile strength of the base structure. So now let's examine why each of these variables were actually chosen. The quantity of liquid plastic that's poured in the die was chosen because it contributes to high internal cost, and this is a process that runs at a high defective rate. Liquid plastic temperature was chosen because it's a key process variable that impacts the products, and the items must adhere to applicable organizational or regulatory standards. Liquid plastic density was chosen because it's a key process variable that impacts the product and is also one of the major sources of customer complaints. And then finally, the fourth characteristic is the tensile strength of the base structure. It was chosen because it's a variable that's known to exhibit a lot of variation, and because it's also a major source of customer complaints. A key aspect of statistical process control is to determine what your subgroups are. This is where rational subgrouping comes together. Rational subgroups help you make sure that you identify special cause variation in your data using your control chart. In order to do this, you need to have data that's as representative as possible to identify where the variation is coming from. You can do this by collecting a set of subgroup samples. For example, subgroups A, B, C, and D. Each of these individual subgroups are collected under similar conditions, providing you with rational subgroups of small homogeneous samples. The samples are taken in a short space of time, which makes sure that the data is collected under the same or very similar conditions. What you're trying to do is contain the within subgroup variation, which is called rational subgrouping. It's also useful within statistical process control because it helps to limit the variability that's inherent to a particular subgroup of samples within that subgroup. And so by doing this, you're able to observe the special cause variation that's happening within a process. If you collect your subgroups properly, you're only getting the variation that comes naturally within the process, and that helps to identify any unusual or your special cause variation. In SPC, subgroups enable you to separate the within group and between group variation within a process. Within group variation is determined by calculating the variation between the individual samples from within that subgroup. To minimize that uncommon or unnatural variability that comes within the same subgroup, it's important to make sure that you're collecting information as consistently as possible under the same set of conditions within each of those subgroups. For example, consider a die-cut manufacturing operation that produces 50 parts per hour. The operator would measure 4 randomly selected parts at the beginning of every hour, and then each sample of those 4 parts is a subgroup. Once you have your subgroups, you can consider the variation both within and between each subgroup, based on the variation coming from each hour of the process. We've already examined how control charts rely on rational subgrouping of process data. The upper and lower control limits for control charts are calculated using the process variability that comes from within subgroups. So it's important to make sure that you're selecting subgroups in a way that you're only getting a common cause variation within that process. Once you have the upper and lower control limits identified, you can plot the average for each subgroup to understand between subgroup variability. That's essentially the line that connects each data point on the control chart. Then you can use that information to see if the variation corresponds to the same level of variation as within the subgroups. If they do not, then you've got a process that's out of control. The goal of statistical process control is to reduce excessive variation. You can do this by eliminating between subgroup variation, which is special cause variation, and by reducing the within subgroup variation, which is a common cause variation. Let's explore why sampling is needed in statistical process control. Now remember, the goal of statistical process control is to identify special cause variation. And to do that, you need to make sure that your subgroups are free of your special cause variation. Once you've identified the special cause variation, then you want to compare the within group variation to the between group variation. There are 3 key elements for collecting subgroup samples. The first one is that your observations must be comprised of data points that are independent. Second, your observations that are within group are from a single stable process. And then finally, subgroups are formed from observations that are taken in a time-ordered sequence. One of the primary rules about choosing subgroups is to make sure that you're taking subgroups from different times, different locations, different suppliers, and different operators. Doing this helps to show the differences between these types of variables. Another key rule is that in order to create meaningful control charts, you need to make sure that your subgroup samples are produced under similar conditions. This helps as you set up your process control chart, because what you're trying to do is ensure that while variation between subgroup samples is attributable, it's typically related to natural or common causes only. When you look at between subgroups, you're capturing all the possible variabilities within your system. Let's explore an example of how you could apply rational subgrouping within the service industry. In this example, you have a car rental company that wants to improve the turnaround time for getting cars ready for the next customer. The Six Sigma team has gathered 4 data points from each of 3 different rental car locations. A, B, and C are all within one city, and the data was all collected on a specific day. So each rental location would form a subgroup, which helps show the team the variation between locations. Now let's explore another example, a cereal manufacturer that wants to reduce variation in their box filling process. This process involves the use of 3 different filling machines. You have an operator who's taken some initial data on the process, and they're trying to decide how to organize it into a process control chart. The operator has collected data using 15 different samples, and the characteristic under consideration is the weight of each box. The operator wants to control rational subgroups for an X bar and R control chart, but they're not really sure what that is. So the operator works with the Six Sigma team, and they have several suggestions that emerge from this process. The first option is to consider all 15 data points as one subgroup, and collect more subgroup data the next day. You wouldn't want to do that because it goes against the rational subgrouping practices that we've discussed so far. The second option would be to organize the data into subgroups of 3 taken each half hour. The problem with this approach would be that you wouldn't be taking into consideration the variation from all 3 machines. The last option would be to treat each of the machines as a rational subgroup of 5. This is the best option because you're able to take into account the 3 machines separately, and you're also able to get information over the time the sample was taken. Let's examine some of the benefits of using smaller subgroups. Large subgroups may contain dependent data or special cause variation. What you want to do is make sure you're collecting information under similar conditions, which may be difficult with large subgroups. In addition, using smaller subgroups is much more economical than collecting multiple parts and having large subgroup sizes, which require inspection of each of those. Also, small subgroups can be assumed to be rational. With small subgroup sizes, you can detect small shifts, which might be more difficult to detect in larger subgroups. An issue with small groups is that you may not be able to detect large shifts within your data. Typically, when you're monitoring service processes, you're typically looking at a sample of 1, because you're able to gather information on that one service encounter. The last consideration you need to take into account with subgroup size is that you need to make sure that you have sufficient history of the process in order to create the control chart. The control chart calculates the upper control limit, lower control limit, and the center line based on current data. So you need to have enough data observations in order to be able to calculate reliable estimates of the average and the variation before you start your control chart. In addition, you won't be able to distinguish between special causes and common causes if you don't have enough subgroups to define the common cause within the operating level of your process. Control plans are a common methodology used in the control phase of the domainic methodology. Control plans ensure that you're monitoring and controlling your processes through your measurements and inspections, and that you have reaction plans in place. A control plan can be used for either a single process or a family of processes, and they're owned and updated by the process owner. There are several key pieces of information that are included within the control plan. The first is information about the characteristics of the process. The control plan also captures the process history and all the process improvements that have occurred. It also specifies the frequency and methods by which the process would be measured and evaluated, including the key indicators for monitoring control of the process. And then, if something does go wrong, there are reaction plans or contingency plans that outline how you would need to handle that situation when one of your critical characteristics do not meet your specifications. In addition, the control plan includes information on the roles and responsibilities of your team members. There are 4 key factors that affect the complexity of your control plan. The first is your type of business. This determines in a large part how a control plan will be designed. Now, while there are standard templates that can be used, this really ties into the complexity of your product and your process and your business. For example, if you're controlling a tangible manufactured product that will involve entirely different measurement tools and techniques, as opposed to measuring customer service results at a call center, or determining the speed of transactions for a retail provider at a point of sale. Another factor that affects your control plan is the nature of your process. If you have a simple process, it might require fewer control elements than your more complex operations. Controlling the final measurement for a single part, for example, probably requires a different level of complexity than controlling a fully assembled jet engine, and so that would need to be taken into account. The third factor is the voice of the customer. Even if you have the same product and the same process, you may have different customers that require different needs and expectations, and that might lead to a different control plan. For example, wholesale customers might place a different emphasis on shipping and packing items than what retail customers would place on the same product. The fourth factor would be the feasibility of implementation. Because you have different levels of complexity, you might have some situations that require hard quantitative data and rigid controls and highly detailed documentation. And in other situations, you might have more subjective evaluations. And so your process scope and the financial and physical resources available to the Six Sigma team may affect how your plan is structured. There may not be time and money available for more complex, detailed measurement systems to be used more frequently. Control plans are created in 3 phases. The first phase is identifying your process scope. This is where you define the purpose of the process, its boundaries, and its intended use. You would also translate the voice of the customer into quantifiable, measurable objectives. The second phase is determining the indicators and responsibilities. This is where the team would be involved in designing the control process to make sure you're meeting their critical customer requirements, commonly referred to as CCRs. In the third phase, the team reviews the completed control plan. This is where you define the rest of the elements that would be included in your control plan, keeping in mind that each control plan has its particular needs. You evaluate the finished control plan, perform a potential problem analysis, and then document any lessons learned in this final phase. Because the control plan contains a considerable amount of information, the team would need to pull together various sources of information to complete the process control plans. Some other sources of information would include process flow diagrams, a system-level failure mode and effects analysis, a design FMEA or a process FMEA, historical data on the process, team knowledge about the process, design experiments, design reviews, multivariate studies, and lessons learned. Let's explore each of the sections of a control plan more closely and how you would complete those. It's important to note that even though you have a basic template that would be used, control plans are going to vary greatly from project to project, depending on the type of a situation, the nature of your business, the voice of your customer, and the feasibility of implementation. So while you go through each of the main elements, it's important to remember that they might vary greatly. Typically, the top portion of a control chart is where you include administrative information. That gives you information about what the product is and what you're trying to accomplish. The first part is the title of your control plan to help you distinguish this control plan from other documents, such as the operating instructions or the Six Sigma database. Next is the unique reference number for this plan. It's sometimes called a control number, and it might be supplied by the responsible party. It's also important that your plan contain page numbers. Pagination ensures that you have all the documentation necessary and none of the pages get out of order. The next piece of administrative information is the list of team members who participated in creating the control plan. Following that are the original date and revision date. The original date is the date on which you first developed the control plan. All subsequent revisions would be included with the revision date. Having a revision date ensures that everyone is working off the latest and most current control plan. Other information in the header of the document is the process owner's name. The process owner is the person that's ultimately responsible for monitoring and overseeing the execution of the control plan. You also need to include a description of the process you're controlling. Here, you provide an overall description of what the process is for this control plan and what you're documenting. And then finally, you identify the process customer. This is where you would list who the recipients are of this process output, because the objective of this process is to make sure you're meeting their input requirements. The next step in the process is to include information about the specific control indicators. This includes what the critical customer requirements are. These are the specifications of the process that influence how the process operates. You would also include information about the outcome indicators. This is where you would be able to demonstrate the degree to which your process improvements have resulted in lasting change. In other words, this is how you evaluate how well the process meets your customer requirements. And now, that information and the header of the document is completed. You start filling out information within the body of the control plan. The first step is to list each process step. Then you complete the information on either the key process input variables or the key process output variables. It's important to note here that you would only have one of those. Next, you identify your process specification information, which include the target and upper and lower specification limits. These would be provided by your customer. The next piece of information is the process capability. Based on historical data, you could determine what your process capability is. You could calculate information such as the initial CPK, the date it was taken, and the sample size for that CPK value. And then next, you would consider the measurement system. The technique field is used to capture what the specific gauge was for the measuring technique. Then you would include information on your gauge R&R. This will tell you how much the total variability is introduced by the measurement system. The final 6 fields within this table start with the method. The method describes the variables that will be controlled, whether you're using control charts, checklists, visual inspections, or automated measurements. The who provides information on who is responsible for taking and recording the measurements. The where and the what document where in the process this information is being collected and what you're measuring. The when specifies the sampling frequency. The reaction plan provides instructions for the action to be taken if the process is out of control, or if you have a product that begins to fail inspections. And then finally, there's a place on the control chart to include miscellaneous information, or notes. And this could be anything that you need to take into consideration as you're monitoring your process. There are 2 key categories of additional information that are often included with your control plans: graphical elements and lessons learned. It's useful to include graphical elements along with your control plans because it helps provide more detail about the specification limits and capability figures that were recorded in your control plan. Providing these images gives more in-depth visual performance history about the process by including summary statistics. And to make sure you don't lose your quality improvement gains, the control plan should also document what went right and what went wrong based on the lessons learned. That's very useful information to take into your next process improvement project. Once you've created your control plan, it's important to make sure you have an effective handoff of the control plan over to the process owner. You hand over the control plan when you've completed your project, and it's time to transition the process to the process owner, because they're the ones that will have ownership of the process from this point forward. In addition, there's going to be personnel changes from the Six Sigma team members back to the new process owner to take over. It's important to make sure that this is a smooth transition. If the control plan isn't adequately maintained during the transition, the improvements that were achieved during the Six Sigma project are going to deteriorate, and the process will revert back to the old way of doing things. There are several requirements for the handoff. The first is to make sure that the control plan is integrated. Your Six Sigma team must re-examine the control plan in light of its integration with other related processes. An order fulfillment process, for example, must interface with the order taking process on one hand and the shipping department on the other. The control plan must allow smooth interaction between both of those processes. The second aspect is securing understanding and agreement. The process owner and their employees must understand what's involved and accept accountability for controlling the process. Most likely, these people will have been consulted and involved in the improvement process, as well as in the development of the control plan. The Six Sigma team will need to train all involved personnel in their responsibilities, verify that the training is effective, and get the team members and process owner on board with the program. The third requirement is establishing the documentation processes. The documentation methods involved in the control plan must be well designed, clear, and easy to use. This will allow the people doing the monitoring to effectively document the control process in both written and graphic forms. And then the fourth aspect is to update the work instructions with clear directions. The team needs to ensure that all of the work instructions, including the documents that are inside and outside of the area, have been updated with adequate and clear reaction plan instructions. This helps to ensure that everyone's on the same page with what they need to do when a nonconformance or instability is identified in the process. At this point in your Six Sigma journey, you'd be in the control phase. Up to this point, you would have analyzed and improved your processes and should have achieved the desired level of improvement. The purpose of the control phase is to monitor and control the improved processes over an extended period of time to make sure that you can sustain those gains. One of the main tools used to do that is control charts, which use the normal distribution to look at the difference from the mean in terms of standard deviation. They're essentially based on 6 different groups. In normal distribution, if you're running at the mean plus or minus 1 standard deviation, you're including data for 68% of the population. If you're running at plus or minus 2 standard deviations, you're including 95% of the population. And at plus or minus 3 standard deviations, you're including 99.7% of the population data. Using the normal distribution and control charts, plus or minus 2 standard deviations are typically considered warning limits that something might be happening within the process. Plus or minus 3 standard deviations is where you're capturing the upper control limit and lower control limit. Anything outside of the upper and lower control limits represents an out-of-control symptom. Control charts represent data you're capturing from samples. Rarely will you have enough time and money and effort that you can capture information about the entire population. So you make multiple observations from a subgroup, your sample, to make inferences about the total population. You use different control charts depending on the size of the subgroups, and even within that, you may also use a specific control chart if you've got subgroup sizes that vary. For example, if you have a Six Sigma greenbelt examining the quantity of chipped windshields in an automobile assembly process, and the greenbelt samples the output of the assembly line 5 times daily for 30 days, then the subgroup size is 30, and you're getting 5 observations per subgroup. Another important thing to note is that you need to make sure you select subgroups so the chance for detecting the differences between subgroups is maximized. While you're trying to balance that with the chance of finding differences within the subgroup, you want to minimize that. In this course, you'll also get a recap of rational subgrouping. You use control charts to try to understand the difference between the common cause variation and special cause variation, which is also known as assigned variation. Common cause variation has a stable and predictable distribution over time, relative to the mean and standard deviation. However, special cause or assignable cause variation is when there are points outside of the control limits, or when there are various trends that show within the data. You need to be able to examine a control chart and understand what the causes of that type of variation might be. There are 6 main causes of variation. Materials include issues such as using new materials or materials provided by a new supplier, too much waste in your facility, or parts or batches being mixed together. Machines include issues such as frequent machine breakdowns, poorly designed equipment, broken or worn tools, general deterioration, or lack of preventative maintenance. Manpower includes issues such as sloppy or careless operators, worker fatigue, poor attitudes toward work, lack of proper supervision, or ignorance about how to perform the tasks. Methods include issues such as failure to follow standards or guidelines, new or poor production methods, or machinery being frequently adjusted. Measures include issues such as using different or unsuitable testing methods, ineffective measurement methods, or lacking effective measurement methods. Mother Nature include issues such as changes in temperature or humidity in a facility, level of noise, whether inside or outside, or dirt or dust in the air. These are all potential sources of variation that can affect processes. Control charts can help point out where the variations exist, what kinds they might be, and how they impact the process. During the control phase, you need to understand and monitor for these causes of variation to reduce their impact on your output. Chart selection is a critical element of creating a control chart. Each chart is used for different types of data. If the wrong chart is selected, the control limits won't be correct for the data. There are several key factors to consider when determining which control charts you should use in certain situations. One of the first factors is knowing whether the data is variable data or attribute data. You also need to know what size your subgroup is and whether its size varies. And finally, you need to know what type of distribution you're using. For attribute data, you need to know whether it's binomial, either 0 or 1, or Poisson, for example 0, 1, 2, 3, or any other integer. Once you know that, you can make sure you're selecting the correct control chart. The control chart flowchart helps you select the correct chart according to several factors, based on the type of data you have, whether it's variable or continuous data, or attribute, also called discrete data. Let's examine variable or continuous data first. Once you've determined that the data is variable or continuous data, you need to know the size of the subgroup. If you have a subgroup of 1, then you'd use an individual moving range, or IMR chart. For a subgroup size greater than 1, you have to know the size of the subgroup to determine whether you use an X-bar and R or an X-bar and S chart. If the subgroup size is between 2 and 10, you'd use the X-bar and R chart. For subgroup sizes greater than 10, you'd use the X-bar and S chart. Charts for variable data are constructed in pairs, as you're considering the mean and standard deviation. With attribute data, you're considering single data points. Because of the differences between variable and attribute data, the decision flow is similar, but slightly different. For attribute or discrete data, the first thing you consider is whether you're looking at defects or defectives. Once you know that, you consider whether the subgroups are equally sized or not, to determine which distribution chart to use. So if you're counting defects, you'd use either a C chart for equal subgroups or a U chart for unequal subgroups. If you're considering defectives and classification information, which essentially means you could have more than one defective aspect of the part, then you consider whether or not the subgroup sizes are equally sized. If they are, you can use the MP chart. If the subgroup sizes are not equal, then you use the P chart. Now let's explore some of the control charts for variable data. Notice that all of the charts are in pairs, where one chart shows the mean and the other chart shows the range of the mean. First, consider the IMR chart. If the subgroup size is 1, you use your IMR or individual moving range. The first chart of the IMR is the actual individual value you're plotting. Similar to a run chart, you're plotting the individual values, and then plotting the range between each individual value. With the X-bar and R chart, you're plotting the means of each subgroup, and the range is the range within each individual subgroup. As you just learned, this is the chart you use if the subgroup size is between 2 and 10. The X-bar and S chart captures the same information. The mean chart plots the mean of each subgroup, but because the subgroup size is greater than 10, the S chart plots the standard deviation from the mean rather than the range. With subgroup sizes greater than 10, standard deviation is a better indicator of the variation within the process. There are two types of control charts for attribute data: control charts for number of defects, called count data, and control charts for number of defectives, or classification data. When you're using count data, you can use a C or U chart, depending on whether the subgroup or sample size is always the same or if it varies. The C chart looks at how many defects are within a subgroup where the size doesn't vary. When the sample size varies, resulting in unequal sample sizes, you use the U-chart. When you're considering defectives, where you could have more than one aspect wrong with the product, you'd use the MP chart. And when the subgroup size samples are unequal, you would use the P-chart, which is the proportion chart. So now, let's review a couple of examples to show how you would select the appropriate control chart. Let's assume that you're part of a Six Sigma project team, working in an electronics manufacturing facility. You've determined that the temperature of the soldering equipment is essential for the product's quality, but due to the cost and technical constraints, you can only measure the temperature once every hour in degrees Celsius. This involves measuring temperature, which is a continuous variable. Since you know the data is continuous, you then determine which variable's chart to use. In this case, the subgroup size is 1, so you'd select the individual moving range, or IMR chart. Now let's explore another example. Suppose you're monitoring a process for an invoicing process improvement project. You want to know the stability of the invoicing process by counting the number of errors that occur in it. Since you're going to determine if the process is in control by counting the number of errors in each invoice, you would use an attribute chart because it's discrete data. You're going to randomly select 200 invoices from your subgroup, which is a subgroup of equal size. You'll select these from the invoices generated over 15 weeks. Because you're counting the number of errors in the invoices, you're monitoring defects. And because the subgroup size is equal, you'd select the C chart. Now we'll consider data trends and some decision rules for interpreting the charts. There are several decision rules that help you interpret what your control chart and data are saying to you. It's important to recognize these trends because they essentially set off warning bells that indicate an out-of-control process. For example, if you have a point that's outside of the control limits, it's pretty easy to see that something is off. Now let's explore some of the different trends that indicate an out-of-control process. There are 6 commonly used trends that indicate that. The first 2 we'll examine are freaks and systemic variation. A freak is a control chart data trend where the points are more than plus or minus 3 standard deviations away from the center line. In other words, they're outside of the upper and lower control limit. The second type of control chart data trend is systemic variation. This is a trend of 14 or more data points that are alternating up and down. With natural variation, a process wouldn't normally have 14 data points or more that alternate up, down, up, down. So this kind of pattern is a sign that something is happening within the process, and that the Six Sigma team needs to go in and further investigate the process. The next 2 trends to look for are process drift and process shift. Process drift occurs when you have a run of 6 or more data points that are either steadily increasing or steadily decreasing. Process shift occurs when you have a run of 9 or more data points in a row, all on the same side of the mean. And again, if you think about natural variation and normal distribution within a process, you'd expect points to alternate on either side of the process mean. Process shift can be described as a process shift up or down. For example, process shift up is where it's above the center line. The next 2 types of trends are stratification and recurring cycles. Stratification occurs when a control chart has patterns of 15 or more data points in a row that are clustered around the center line, plus or minus 1 standard deviation on either side. So again, if you think about natural variation within a process and the normal distribution, plus or minus 1 standard deviation within your process includes 68% of your data. With 15 or more data points, you would expect with natural variation that some of these points would be outside of that 1 sigma limit. The other type of trend is recurring cycles. With a recurring cycle, you have a control chart trend that's demonstrating any other visible recurring pattern or cycle. This is where a Six Sigma team needs to go back and analyze what might be causing the patterns or cycles within the data that they expect to see. For example, there might be something that changes within the hour of the day of the week, or the month of the year, and it may also not be the things you would expect to see. When you analyze the data as a Six Sigma team, searching for those patterns or these cycles within your data helps you identify where there might be variation occurring. Recurring cycle trends are often caused when you modify the process inputs or methods based on a regular schedule. Those are the 6 most common trends to look for, but there are also early warning signs. Based on those previous methods, searching for 15 data points in a row could take some time, and during this time, your process might be running out of control. So you also want to watch out for other indicators that act as early warning signs. For example, if you have 2 out of 3 data points that are beyond 2 sigma from the center line on the same side, or 4 out of 5 points that are more than 1 sigma from the center line that are on the same side. These are early warning signs that can help react a little bit more quickly than waiting for having 15 data points that are showing a trend. There is a caveat to this. Some trends don't appear to violate the rules that we've discussed here, but they still need to be considered as alarm signals. There are visible signs that don't map to any of the broad rules used to classify the trends themselves, but still indicate these visible signs of shift, drift, repetition, patterns, and stratification early in the monitoring of the data. As a Six Sigma professional, you need to be able to dig deeper to find the possible causes, and then identify the appropriate corrective measures. One other thing to consider is that the individual moving range, or IMR chart, is interpreted a bit differently from the other types of charts, because it only plots a subgroup size of 1. So the subgroup sizes are not independent, and the moving averages are smooth. You need to take that into consideration when interpreting an IMR chart. Each of the signs can indicate specific problems, and you need to take the proper corrective action to address them. The corrective actions you apply when you discover trends and patterns will be very specific to the business or production context that you're in. Different situations will require different actions, and it's impossible to cover all the possibilities, but having a general sense of what causes each trend and how to respond will help you make better decisions in your own situation. As a starting point, each trend gives a sign that indicates some sort of specific problem. Freaks are points outside of the control limits, which puts them beyond plus or minus 3 standard deviations. Some potential causes of freaks are factors such as over-control, using different methods for testing, or using materials from various suppliers that are mixed up or of different quality levels. In order to take the appropriate corrective action to respond to these types of data points, you'll need to consider a variety of things. You could start by preventing operators from over-adjusting the process. Sometimes operators over-tweaking the process causes over-control. You can also make sure that the variability in the machines and the operators is reduced to a minimum. And then consider the variation in your incoming materials, because you could be getting that different level of quality from your different suppliers. As a reminder, in this course, we'll review some of the general corrective actions that you could apply when you discover these trends and patterns, but these are very specific to the type of business or production that you're actually working in. You need to tailor your handling to the appropriate context for your environment. Different situations will require different actions. Let's now explore how you would respond to drifts within your data. Remember that drifts are about 6 or more data points that are either increasing or decreasing. Some potential causes of drifts are material deterioration, operator fatigue, worn tools, operator skill improving or deteriorating, or a change in the quality of materials. One way to respond to this change in the output is to maintain the machine being used, to make sure that it isn't due to parts wearing down. A regular maintenance schedule is a good way to prevent this cause. If you can pinpoint a specific operator, do a root cause analysis to determine why that operator might be having problems, and then take the appropriate action to train the operator. If it's occurring because of a broken tool, then you need to repair the broken tool and look at the tool life. This next type of trend is a shift trend. You may recall this as when you have 9 or more data points on one side of the mean. This could occur when you're obtaining more or less material from different sources. You may have new machinery or operators. There's been a change in your production process, or in the way that you're inspecting the process, or changes in materials, methods, operators, or inspections. To take corrective action when you have a shift that's occurring up or down, there are at least 3 key aspects you could address. The first is to work with your suppliers to ensure the material supply is consistent. Next, make sure your operators use the same methods and instructions over a reasonable period of time. And then third, check the calibration of the devices being used for the measurements. The next trend is systemic variation. This is evident when you have 14 data points that alternate up and down. There are several possible causes for this type of systematic variation. The first is over-control, so you could be over-tweaking your process. There could also be differences in the methods that are used for testing, as well as differences in the material quality, and using materials that are mixed or from different qualities. There are 4 key ways you could take corrective actions. You could make sure the control limits are actually set at the appropriate or correct levels. So you might need to go back and recalculate your upper and lower control limits. You also need to check your testing procedures. You should also determine if the inspection should be performed differently or occur more frequently. And then finally, you need to make sure you standardize the materials that are used. The next trend is stratification. This is where you have 15 data points around the center line. There are several possible causes of stratification. Stratification is most commonly associated with variables control charts, so you want to check that information as well. Maybe the control limits have been incorrectly calculated, or you've actually improved the process to a point where you need to go back and recalculate the control limits because you've reduced the variation within the process. In addition, there could be the presence of 2 or more cause systems at play. And finally, if you have samples that contain many measurements from different lots, the average value could cause it to be centered more around the mean. There are 2 key ways that you could respond to stratification variation. The first is to ensure the checking procedure is being followed, working with your operators to make sure you're using a consistent process. Then second, make sure that your employees are taking the measurements properly and they're following procedures for rational subgrouping to make sure they're getting a representative sample. Next is how you could respond to recurring cycles. Recurring cycles are other visible patterns that may occur within your data. This is where the Six Sigma team needs to dive into understanding what's happening, where you have a consistent pattern that's occurring over time, that's repeating itself. Some of the possible causes for recurring cycles could be physical factors such as temperature or humidity. For example, it might be more humid during the day than it is at night. Another factor might be operator fatigue. For example, you might find changes in the morning versus the afternoon. You could also find differences if you have machines or operators that are being regularly rotated. In addition, scheduled maintenance and worn tools could affect those recurring cycles. There are 4 key ways you could respond to the trend of recurring cycles. The first is to adjust the environmental factors, if you can relate the cycle back to something physical such as temperature or humidity. Next, if you find issues with your machine maintenance or worn tools, make sure you're regularly maintaining your equipment. If you could associate this with operator fatigue, then you should consider how you are rotating your operators, and how you could change your operators when you see the signs of fatigue. And then, if you're finding issues with worn tools, consider the tool life of your equipment to determine how you should better schedule replacing the worn-out tools. Once you've determined the type of control chart you're going to use based on the control chart flowchart, there are 5 key steps that are used to create your control chart. The first step is to plot the data points. Then you connect the data points as a time-ordered series. The third step is to determine and draw the center line. The fourth step is to determine and draw the upper and lower control limits. And the fifth and final step is to analyze and interpret the chart. Each step will be explained more in the remainder of this topic. The first 2 steps involve plotting the data points and connecting them as a time-ordered series. The first step is completed using the information that's being collected over time. You plot each data point as you're collecting the information. The second step is to connect each of the plotted data points so you can consider your data as a time-ordered series, which is important because you'll use this information to find trends and patterns within your data. Let's explore how this would apply in a scenario. Let's say you're working with a Six Sigma team in a manufacturing company, examining the diameters of bearings in their operations process. The team has the machine operator pull a sample subgroup of 7 cylinders every hour for 8 days, capturing the data daily on a worksheet. This data will be used to calculate the center line for the chart. Before the team can begin the control charting process, they need to first determine what type of control chart is best for this situation. The data being collected, which is the diameter of the bearings, is continuous data. And you know the subgroup size. You're pulling 7 bearings every hour for 8 days. Based on this information, the team determines they should use an X-bar and R chart. Because the data is variable, and because you're using this with a subgroup size of less than 10, the subgroup size is 7, you use the X-bar and R chart. And then using this information, the team calculates the average value for each subgroup on the mean chart, the X-bar chart, and then plot the range for each subgroup on the R chart. The team labels the data on the X and Y axes, plots the data points, and then connects the data points as a time-ordered series as you consider the samples over time. The next step in the process is to determine the center line, which represents the mean value for the process and helps to show how far the process is deviating from the mean. Determining the center line might be slightly different for each process depending on the type of chart you choose. The centered line shows the Six Sigma team how far the data points are from the mean, the variation, and potentially how serious this could be if you have process fluctuations. X-bar and R charts are one of the types of paired charts used for variables data. You need to look at both the X-bar and R charts to analyze the information. The X-bar chart shows the average as the mean for all the observations within each individual subgroup. This determines the within subgroup average. Then you calculate the average of each of these X-bars for each subgroup to get the grand average or X double bar. That gives you the between subgroup average, which is also known as the grand average or grand mean. It's represented by the X double bar symbol. This is the center line in the X-bar chart. Similarly, you consider the average of the subgroup ranges to get your R-bar, which gives you the center line for your R chart. The fourth step is to determine and draw the upper and lower control limits. To determine your upper and lower control limits, you need to make sure you're selecting the appropriate constant from a table. Typically, the upper and lower control limits are 3 sigma above and below the center line. The UCL and LCL help you to easily determine whether your process is in control, and helps you to take the appropriate corrective actions. You're looking for points outside of the upper and lower control limits to determine if there are any trends within your data that might suggest that you have an out-of-control process that needs to be investigated. The placement of the UCL and LCL are based on the results of the plus or minus 3 standard deviations calculations. You use the A2, D3, and D4 values from a constants table to calculate those. These are the constant values used in the upper and lower control limit formulas. The team looks up these values in a table and uses the formulas as follows. UCL equals X double bar plus A2 times R bar. LCL equals X double bar minus A2 times R bar for the X bar chart, and UCL equals R bar times D4, and LCL equals R bar times D3 for the R chart. Once the chart is completed, then the team can perform the final step, which is to analyze and interpret the chart based on the trends within your control charts. In this example, the team observes that the X-bar-R chart does not show any evidence of special cause variation. There are no points outside the control limits and no non-random trend or pattern, and so determines that the process is in control. Now, let's examine the control charts for variable or continuous data. It's important to note that control charts for variables data are paired. The average of the data is captured on the X-bar chart, and then the second chart is either the R for range or S for standard deviation chart. The second chart shows the range or width of the data and how much distribution there is within the process. Together, these charts graphically illustrate the presence of special cause variation. In this topic, you'll learn about the X-bar and R chart, which looks at the average and range, and the X-bar and S chart, that looks at the average and standard deviation. These are the 2 most commonly used variable control charts in the domainic methodology. As you start to consider the X-bar and R and X-bar and S charts, it's important to understand the key differences between them. The range chart, or R chart, is used when there are 10 or less data points within each subgroup. The standard deviation chart, or S chart, is used when your subgroups are greater than 10. This is because when a subgroup has more than 10 data points, standard deviation is a better indicator of the variation or the distribution of your data. Additionally, when using the R chart, you need to make sure that you have a fixed subgroup size. However, with the standard deviation chart, the subgroups can vary in size because it's how it's calculated. So let's discuss two examples to find out when you would use each chart. First, consider the X-bar and R chart. Suppose you have a situation where you want to find the average range of variation in the machines that are making glass cylinders. If your team pulls the subgroup sample of 5 cylinders at 1-hour intervals, and then they measure the cylinders, they could then chart the average value for each subgroup on the X-bar chart. And then they would use the range of each subgroup with the R chart, because they're pulling a subgroup sample size of 5. Now suppose you have a team that's using the X-bar and S chart to check the control of an improved process. The team checks the inside diameter measurements of tempered glass beakers. Each subgroup consists of 5 beakers, and then the team lead calculates the sample and sample standard deviation for each of the 25 samples. So the Six Sigma Greenbelt can now use these charts to determine if the process is out of control or not, and if the limits could be used to monitor the process. Another chart that could be used is the median chart. The median chart differs from the X-bar chart because you're plotting the median of the value versus the mean of the data. And the difference in the chart is that you plot each of the data points pulled within the subgroup, and then the main point that's plotted is the median of those points. On a median chart, the data points are arranged from high to low, and the midpoint is the point where 50% are above it and 50% are below it. This chart plots all the individual readings, which gives a clear picture of how some of the points might actually fall outside of the control limits, even though some of the points might have the median within the control limits. It's important to understand when you should use the median chart. You use it when your process is not completely normal. The other key aspect of the median chart is that it plots all of the measured data, not just a single plot per subgroup. That's important because it shows the actual spread of the data in addition to the median value. It's particularly helpful when you have subgroup ranges that vary greatly, because it helps to show the dispersion of the data. In this topic, we'll explore how to create an X-bar and R chart using a scenario to illustrate the process. When creating control charts, you're going to plot the data points, connect them as you add them to the chart, calculate and draw the center line, calculate and draw the control limits, and then analyze the chart. For example, say you're working at a major airline, and you have a Six Sigma team that's examining the time it takes to process passenger data check-in. The team conducts one random observation each hour at each of the airline's 9 processing counters during a 5-hour time frame. So there are 9 subgroups, 9 different processing counters, and you're doing this over 5 hours, so you have 5 observations. So in this example, the subgroup size is 5, and the number of subgroups is 9. This study is suited to the X-bar and R chart because you're capturing variable data for a fixed subgroup size of less than 10. Now that the team has the data, they can move forward with plotting the data points and connecting them in an ordered time series. The next step in the process is to calculate the center line for the X-bar chart and the R chart. The X-bar center line is the average of all of the X-bars, or the X double bar. To determine that, first calculate X-bar for each subgroup. This is known as the average within each subgroup. In this example, there are 9 X-bars, 1 per subgroup. Then calculate the between subgroup average, also called the grand average. To get the X double bar value is where your center line should be. In this example, that point is 8.81. To determine the center line on the R chart, add up all of the ranges from each subgroup, and then divide by the number of subgroups. In this example, the subgroup range from each subgroup was added together to get 9.8. Then it was divided by the number of subgroups, which in this case was 9. For this example, the R bar value is 1.09. Using that information, the next step is to draw the upper and lower control limits on each chart. The formulas for the X-bar and R-chart are shown in the columns, and the rows show the formulas for calculating the upper and lower control limits for each chart. Start by calculating the upper and lower control limits for the X-bar chart. To calculate the upper control limit, or UCL, for the X-bar chart, use the grand average of the process, or X double bar, and then add the value of A2, which is a constant, times R bar, which is your average range. Using the constants chart, in this case, the A2 value is 0.577 because the subgroup size is 5. This formula results in a UCL of 9.44. To calculate the lower limit, or LCL, of the X-bar chart, you subtract the value of A2 times R bar. Since the subgroup size in this example is 5, you still use the same A2 value of 0.577, and your lower control limit for your X-bar chart is 8.18. Next, you need to calculate the limits for the R-chart. The upper control limit, or UCL, of the R-chart is equal to your R bar times D4. The value of D4 is retrieved from a standard statistical table or constants chart. In this case, the value of D4 is 2.114. Therefore, your upper control limit for your R-chart is 2.3. To calculate the lower limit for the R-chart, the calculation is R bar times D3. For this example, the statistical value is 0 for D3, so your lower control limit is 0. Now, using this information, the team can analyze and interpret the chart. Your team has plotted both components of the airline data on the X-bar and R-chart, and you're able to interpret the data to see if you need to take any corrective action. In this example, the X-bar chart doesn't reveal any special cause variation, as there are no patterns present within the data and no out-of-control data point. Next, you review the R-chart. As with the X-bar chart, there are no points outside of the control limits and no non-random patterns, such as the 4 test patterns that are appearing. Considering both charts, there are no patterns in either, so you can say that your process is in control. Now, it's important to note with this scenario that if you're showing the output from statistical software like Minitab, there might be minor differences between statistical software and the values you get from manual calculation, values that are typically attributable to rounding, if you're using 2 decimal points, for example, in your manual calculations. And that's one of the disadvantages of manually calculating and constructing control charts. However, the differences are typically very minor and rarely affect the result or how you would interpret these charts. Now let's explore how you would create an X-bar and S-chart. The same general process is used to create the X-bar and S-chart as is used for the X-bar and R-chart. The key difference here is that the formulas, with the S-chart, you're using standard deviation to look at the variation, because the sample size is greater than 10. So to calculate the center line for the X-bar chart, you use the X-bar values within each subgroup to calculate the average of all of the X-bars. Then you calculate the grand average, known as the X double bar, and that's the center line. For the S-chart center line, you calculate S bar, which is the average standard deviation value, and then you plot this value. To calculate the upper control limit, or UCL, for the X-bar chart, you multiply the S bar by the appropriate A3 constant, and this again is based on the subgroup size from a standard statistical table, and this is added to X double bar. To calculate the upper control limit for the S chart, select the appropriate B4 constant and multiply that times the S bar. And in this case, the B4 value is a function of n, which is the subgroup size. To calculate the lower control limits for the X-bar chart, you multiply the S bar value by the appropriate A3 constant, and then subtract this value from the X double bar value. And to calculate the LCL for the S chart, select the appropriate B3 constant from the standard statistical chart, and multiply this times your S bar value. In this case, the value of B3 is a function of your sample size. So let's consider a scenario to illustrate how you would calculate the center line and upper and lower control limits for your X-bar and S chart. In this example, you're considering patient satisfaction scores and using 10 subgroups with 13 in each subgroup. For this sample, you'd use the standard deviation rather than the range, because you have more than 10 samples within each subgroup. You have 13, which is a better indicator. To calculate the center line for the X-bar chart, you'd use the X-bar values from each of the subgroups, and then calculate the overall average of your X-bar groups. In this case, it gives us an X double bar of 8.339, which will become the center line for the X-bar chart. To calculate the center line of the S-chart, calculate the average standard deviation, or S-bar, and plot that value. In this case, it's 0.6707. Then to calculate the UCL of the X-bar chart, multiply the S-bar by the appropriate A3 constant based on your subgroup size, which is 13 for this example. So in this case, the upper control limit of the X-bar is 8.887. The upper control limit for the S-chart also uses a constant value, so you need to select the appropriate B4 from your constants table, and multiply that times the S-bar value. This gives you a value of 1.0690 for the UCL of the S-chart of patient satisfaction. To calculate the LCL for the X-bar chart, multiply the S-bar by the appropriate A3 constant, and subtract this from the X double bar. In this case, you get a value of 7.790. Then, for the LCL of the S-chart, multiply the S-bar value by the appropriate B3 constant. That gives you a value of 0.27725 for the LCL on the S-chart. The next step in the process is to interpret the X-bar and S-chart. When you do this, start with the S-chart first, because if the chart is not in control, then the control limits on the X-bar chart really don't have any meaning. So starting with the S-chart, interpret any trends or patterns in the data points on this chart. You have no patterns or anything out of control on this S-chart. The next step then is to review the X-bar chart. Here there's one point that's out of control on November 12th. This signals that you need to analyze the results by digging deeper into what happened on November 12th. You consider what happened on that date because it indicates the customer satisfaction is higher than expected, which isn't necessarily a bad thing, but it is very different than every other day. So as a team, you would want to take action on this issue and investigate the reasons. Then you could determine whether the data is valid, or if there's a measurement error, or find out if higher satisfaction was achieved to additional services, or something that could be emulated as a strategy to achieve higher patient satisfaction across the board. In this topic, we'll examine the IMR chart, or Individual Moving Range Chart, also sometimes called the XMR chart, in greater detail. This chart is called a moving range chart because of the calculation constant that changes range between two of your successive values. Typically, you use the IMR chart when you only have one data point. You don't have subgroups that you can take advantage of. You're using one sample and you're plotting that one sample over time. The IMR chart is used when your sampling opportunities are fairly limited, perhaps because you have a low production volume, or you just may not be able to get the sample size that's larger than one. Another instance where you might use the IMR chart is when you have homogeneous batches, because pulling more than one will still get you the same value. You might also use the IMR chart when your sample data is not in subgroups but in individual data observations. As with the X-bar and R and X-bar and S charts, the IMR is also a paired chart which contains the individual values chart and the moving range chart. When you're analyzing the data, you'd want to start with the moving range chart first, because it shows the variation between the data points. This enables you to evaluate the stability of the moving range before you make decisions about your individual chart. So now let's examine the calculations for the IMR chart. We'll start with the calculations for the I chart because they provide values that you will need for the MR chart, starting with the center line. To determine the center line, calculate the mean of all of the observations, which will give you the X-bar value, and plot this on the I chart. Then to calculate the upper control limit for the I chart, multiply the E2 constant by the average moving range of your MR bar. The E2 constant is read from the constants table. The value you use depends on how many consecutive observations you're including in the moving range chart, typically 2. Therefore, you're using the constant value of 2.659, which can be rounded up to 2.66. And then you calculate the lower control limit for the I chart by multiplying the MR bar by the appropriate E2 value factor, and then subtracting that from the X bar value. Now let's examine the MR chart formulas. The first step in the process is to calculate the centered line of the MR chart, or MR bar, by taking the average of the moving ranges and dividing that by the number of moving ranges minus 1. The next step is to calculate the lower control limit by first multiplying the MR bar you just calculated by the constant for D3. As you learned for the IR chart, the most commonly used sample size for the moving range is 2, and for the MR chart, while it's commonly 2, it's almost always less than 6. And because the value for D3 for subgroup sizes of 6 or less are 0, the lower control limit formula typically results in a value of 0. However, if the subgroup size is greater than 6, then you'd select the appropriate D3 value, and you would multiply that times your MR bar value. The next step then is to calculate the upper control limit. The UCL calculation uses the constant value of D4 multiplied by the subgroup size. And again, typically the subgroup size is 2 for a moving range, so you would multiply the D4 value, which is typically 3.267, times the MR bar value. Let's consider an example to find how these calculations work using some data. Suppose you're working on a project for a bank that wants to determine if the time taken for prospecting, that is, from the first contact with a potential home mortgage buyer to actually signing the mortgage contract, is in statistical control for all cases, irrespective of the bank branch or location. To do this, the team decides they'll create an iChart component for the IMR chart. They collect the data over 50 observations. It's important to note that for illustration purposes, the chart has been truncated between the 11th and 45th observations to make the full chart more visible. First, they calculated the center line, or X-bar, and the moving range, or M-bar, to plot the data for the individual and moving range charts. The 50 observations took 233.93 business days. The mean is the average number of business days it took for the 50 observations. So you divide 233.93 by 50, and that results in an X-bar value of 4.697, or 4.68 when it's rounded up. The moving ranges are also totaled and yield a result of 33.4. That's divided by k minus 1, or 49, resulting in a moving range average of 0.682. The next step is to construct the iChart. Now that you know the value of X-bar, you can plot the center line and use that to calculate the upper control limit. To do that, add the X-bar value of 4.68 to the product of the moving range, times the value of constant E2. This results in a value of 6.49 for the UCL. Next is the lower control limit for the iChart. The LCL calculation for the iChart uses the same mean value, X-bar of 4.68. But this time you subtract the M-bar value multiplied times E2 to determine the lower control limit, which in this case is 2.87. The Six Sigma team at the bank is now ready to create the moving range chart. Earlier, the moving range was calculated as 0.68. To determine the upper control limit of the moving range chart, the MR bar value calculated for the iChart, or 0.68, is multiplied by the value of constant D4, which is 3.27, resulting in an upper control limit of 2.229. And to determine the lower control limit, the M-bar value is multiplied by D3. In this case, D3 is 0, and because you're multiplying by 0, the LCL will be 0. At this point, the Six Sigma team at the bank is ready to analyze the results from the IMR charts they constructed. First, they look at the moving range chart and note there are 4 points above the upper control limits, at observations 22, 23, 28, and 29. These indicate you have part of the process that's out of control. In addition to that, they notice that the test 1 has also failed for this chart. Also, there are more than 9 points in a row on the same side of the center line, at observations 6 through 17, and again at 33 through 43, which indicates that test 2 has failed. Taking all of these things into account, the chart shows the team that statistically the process is out of control. Next, the team reviews the iChart. On the iChart, there is just 1 point that's above the upper control limit at observation 26, and there's 1 point below the lower control limit at observation 28, which means that test 1 has failed. There are also 9 points in a row on the same side of the center line at observations 3 through 11, and again at 32 through 40. These indicate a process shift, so it fails test 2. And there are more than 6 points in a row that are all increasing at observations 38 through 44, which indicates an upward shift. There are decreasing points at observations 4 through 17, indicating a downward shift, all of which failed test 3. By analyzing the IMR chart they created, the Six Sigma team learns that the process is statistically out of control and needs more process improvements. Now let's explore control charts for attributes data. Attributes data is information about whether the product, part, service, or whatever you're monitoring is good or bad. It's different from a continuous variable that can be measured, such as time, length, weight, etc. Attributes data focuses on whether something has defects or doesn't, is defective or isn't. Defects are any characteristics of a product or service that do not conform to specifications. Defectives are units that contain one or more defective aspects. It's important to note the difference between defects and defectives, because when you talk about a defect, you're talking about the product as a whole being good or bad. But when you're talking about defectives, you're talking about the number of defects an individual product has. There are different charts used for each. A P-chart is used to track the proportion of defectives. An MP-chart is used to track the number of defectives. The easiest way to understand this is to consider an example. What do you think is the first thing you need to do? If you said, calculate the center line, you are correct. In this example, you're on a Six Sigma Greenbelt team working at an electronics equipment manufacturer. The team wants to make sure the process they're monitoring is in a state of statistical control. They want to determine the proportion of defects on a DVD player that's being produced. So the team collects data for 20 days and captures information on how many observations they made each day and how many defectives they found during those observations. So because they're considering the proportion of defects, they select a P-chart. The proportion of defectives is calculated by dividing the number of defectives, in this case 5,120, by the total number of observations, 20. For the first day, there were 9 defectives out of 320 parts or observations, resulting in the proportion of defectives being 0.028125. This information is collected and stored in a worksheet each day, so you can plot the control chart at the end of the observation period. To calculate the mean, or P-bar, of the DVD player data, divide the total number of defectives, 226, by the total number of observations, 5,120. This results in a P-bar value of 0.044, which is where the center line would be placed on the chart. Before you can calculate the upper and lower control limits, you need to calculate another statistic, called N-bar. N-bar is the average number of observations per subgroup. In this case, N-bar is 256, or 5,100 in total observations divided by 20 days. Now that you've calculated the P-bar and N-bar, you can determine the upper and lower control limits. The formula for the upper control limit on a P-chart is P-bar plus 3 times the square root of the following: P-bar multiplied by 1 minus P-bar divided by N-bar. So for the DVD player example, the upper control limit is 0.044 plus 3 times the square root of 0.44 multiplied by the results of 0.956 divided by 256. Following the calculation from top to bottom, you get a value of 0.083 for the upper control limit. The formula for the lower control limit is very similar to that for the upper control limit, but now you're subtracting the value of 3 times the square root of the result of the P-bar multiplied by the result of 1 minus P-bar, divided by N-bar. Because you subtract to get the LCL, it's possible to get a negative value as a result. If that happens, the lower control limit would be set to 0 on the control chart, because you can't have a control limit less than 0. However, that isn't the case here. The result of this calculation, which can be followed as each expression is simplified from top to bottom, is a lower control limit of 0.005. At this point, the team has the center line, the upper control limit, and the lower control limit. The next step in the process is to analyze the P-chart. The team has drawn the points on the P-chart and connected them in a time sequence. Note the jagged lines for the control limits. The reason for the jagged lines is the sample sizes vary from day to day. When the sample size stays the same, the control lines are even. This chart was created using statistical software that was able to calculate the UCL and LCL on a daily basis. As you may recall, we just explored the manual calculation of the UCL and LCL for all the data to come up with just one value for the whole time frame. You could certainly do that, and if those values had been used, the UCL and LCL lines would be even. But when you're dealing with sample sizes that vary, it's useful to use statistical software to draw these lines for your charts, as was done here. Having accurate control lines is helpful when later analyzing a given plot in relation to another. Now, the resulting p-chart can be analyzed to look for any special cause variation. In this example, there is no special cause variation present, because there are no data points outside the control limits, and no evidence of any non-random trend patterns appearing. This p-chart shows that the process is under statistical control during the time period where we've collected these samples. Let's explore how to create an MP chart. It's basically the same as a p-chart, but there are some slight differences in the calculations. The Six Sigma team is examining the new process for manufacturing the DVD player. But this time, instead of considering the proportion of defects, the team decides they should examine the number of defective players produced by the process. To do this, they decide to use a constant number of observations of 100 DVD players per day, collected over 20 days. So each day they're going to examine 100 DVD players and decide if they're good or not. This type of data they're collecting is about the defective units as a whole, which is binomial, yes or no attributes data. So they need to use the attributes flowchart to decide which chart to use. And because the subgroup sizes are constant at 100 observations per day, the team determines they should use an NP chart. This is the data they collected. Using this information, the team sums up the total number of defectives at 83 defects. This chart still provides the team with information on the proportion of defects, but this time the observations, which are in the denominator of the mean calculations, are constant at 100. So, for example, on the first day, the team finds 8 defectives out of the constant of 100 observations. So the proportion of defectives is 0.08. On the second day, they found only 1. So the proportion on that day is 0.01, and so on. The team then sums all the proportion of defects to get a total proportion of defects of 0.83. The average proportion is the 0.83 divided by 20, which gives a value of 0.0415. The third step in creating the NP control chart is to calculate the center line, or mean, of the distribution. On an NP chart, the center line is called the NP bar. The NP bar is equal to the number of defectives divided by the number of subgroups, which in this case is 83 divided by 20, which gives a value of 4.15. Because you're using the NP chart, it's important that when you do this calculation, you use the sum of actual counts, and not the sum of the proportion of defects before dividing by the subgroup number. The sum of proportion of defects is used to calculate P bar, which is needed to calculate the control limits. The formula for P bar is NP bar divided by N, which is the total number of observations per subgroup. In this case, the total would be 0.0415, which can be rounded to 0.042. Now that the team knows N bar and P bar, they're ready to calculate the upper and lower control limits for the chart. In the manufacturing example, NP bar is 4.15, and since the subgroup size is 100, P bar is 0.0415, which the team rounded up to 0.042. The upper control limit formula is NP bar plus 3 times the square root of the following: NP bar divided by 1 minus P bar. Substituting the data ranges into the formula and simplifying each expression in stages, the team calculates an upper control limit of 10.132. The formula is essentially the same for the lower control limit, except now you subtract the value of 3 times the square root of NP bar, multiplied by the result of 1 minus P bar. Substituting the data values into the formula and simplifying each expression in stages, the team calculates a lower control limit of minus 1.832. Do you remember what happens when you have a calculated negative value for a lower control limit? Since you can't have a negative number of defects, the lower control limit will be set to 0 on the control chart. And then the final step in the process is to build the NP chart from the data so it can be interpreted and analyzed. This enables the team to determine what's happening within their process and determine whether appropriate corrective action is needed. Reviewing the NP chart of the defective DVD players, the team determines that no data points exceed the UCL or the LCL, even though 2 points are on the LCL. As a practical matter, having 0 defects is a good thing, so having points on the LCL is not the same concern as finding them on the UCL. Taking all of this into consideration, they conclude that the process is in control. There is also no evidence of special cause variation in the NP chart, so no action is required at this time. The other two types of attributes control charts are the U-chart and the C-chart. Both are used when counting individual defects in a unit, instead of broadly categorizing a unit itself as being either good or bad, defective or not defective. Because the type of data being collected deals with defects and defectives, which aren't continuous measures, they're considered attributes data. The C-chart is used for defect counts in an unvarying sample size. In other words, when the subgroup size remains constant. The U-chart is used when your subgroup sizes are not the same, because it plots counts per subgroup. One of the questions that you should ask when you're trying to decide whether to use a C or U chart over a P or MP chart is to ask, can an event happen more than once in this area of opportunity? If so, depending on whether you're counting defects or classifying defectives, you'd use a U or P chart. If not, then you'd use a C or MP chart. In this topic, we'll be discussing how to create and use a U chart following an example. This time, you're working with a Six Sigma team for an online shopping company that's launched an invoicing process improvement project. In the final phase of the project, the team wants to monitor if the suggested measures have resulted in a process that's in control. The process involves sending customer invoices for their purchases. In the last 6 months, there were several instances of incorrect invoices being sent to customers, the timing of which coincided with the company's introduction of online sales. There are 6 possible opportunities for errors in an invoice. This is where it's useful to make sure that you're reviewing the C or U chart, because you have multiple opportunities for an incorrect invoice. Incorrect entries may be made for the type, name, and price of the item or items purchased, as well as the customer's name, the customer's address, and the total billing amount. Each of the invoice errors at the retailer is counted as one defect, even if a single defect results in a defective invoice. So the Six Sigma team collected samples over 15 weeks, based on the invoices that were generated and sent to the customers, and they've collected information on how many invoices were sampled and how many defects were found in those invoices. From that, they can determine the total number of invoices they've sampled and the total number of defects on those invoices. Because there are more than 2 opportunities for defects in a unit, there are 6 opportunities in each invoice. The distribution follows a Poisson distribution, not binomial. The subgroup size varies, ranging from 173 to 224 observations in a week. Given these variables, you can confirm that the U-chart is the appropriate control chart for the data. Let's continue with the calculations needed to create the chart. As with all the charts we've explored so far, you start by calculating the center line. To do this, calculate the mean of all the observations, or U-bar, and then plot this value on the chart. In this case, the count of the number of errors found, or C, was 404, divided by the number of observations, or N, which was 2,948, which makes the center line 0.137. The next step would be to calculate the upper control limit. The UCL is equal to the U-bar plus 3 times the square root of the result of the U-bar, divided by N-bar, where N-bar is the average number of observations per subgroup. M-bar is the total number of observations, or N, which was 2,948, divided by the number of subgroups, or K, which in this example is 15, because the information was collected over 15 weeks. That results in an n-bar value of 196.53. Back to calculating the UCL. U-bar is the center line, which you have solved for, which is 0.137. When you plug those values into your formula and simplify the expression in stages, you end up with a UCL of 0.216. Then you calculate the LCL. As for the other charts, instead of adding to U-bar, you subtract from U-bar. And in this case, the LCL is calculated to be 0.058. Again, if the value had been negative, the LCL will be set to 0, since you can't have negative defects. The final step is to analyze and interpret the control chart. The team has plotted the center line and both the upper and lower control limits. Do you remember why the control limit lines are jagged? If you said because the subgroup size varies, you're correct. The chart was created using statistical software that was able to calculate the UCL and LCL on a daily basis. As you may recall, we just worked through the manual calculation of the UCL and LCL for all of the data, and then came up with just one value for each representing all of the data. You could certainly do that, and if those values had been used, the UCL and LCL lines would be even. But when you're dealing with sample sizes that vary, it's useful to use statistical software to draw those lines for your charts, as was done here. With the UCL and LCL lines adjusted for each plot, that plot can then be better evaluated against other plots. Reviewing the chart, there are visible signs of special cause variation within this process. There are 4 points during weeks 9, 10, 11, and 12 that are above the upper control limits. And there are also 5 points during weeks 3, 4, 5, 6, and 7 that are on or below the lower control limit. Both of these situations indicate special cause variation. There are also 6 points that occur between weeks 1 through 7 that are all in a descending order, indicating a downward process shift. The team needs to investigate the causes of variability within these weeks. Note that while fewer defects found was inherently good, the team must still react to understanding the root causes for the drift for many reasons. Let's quickly review the differences between the U-chart and C-chart. This is important because they differ in 2 broad categories. The first difference is with the number of defects, and the second is the number of observations. In relation to the number of defects, a U-chart plots the number of defects per unit in a subgroup, versus a C-chart which plots the number of defects in a subgroup. In relation to the number of observations, in a U-chart the subgroup sizes can be equal or unequal, but for C-charts the subgroup sizes must be equal or constant. So let's explore how you would create and develop a C-chart. The Six Sigma team is still working on an improvement project at the online shopping company. At this point, the team has decided to change how they're collecting their data. They decide to collect the data in 200 subgroups of equal size. They're collecting random samples from invoices generated over a period of 15 weeks. For each week, they're determining how many defects there are in the 200 samples. During the 15 weeks, they found 406 defects in the 3,000 invoices they sampled. Next, they calculated C-bar to come up with the average number of subgroup defects. C-bar is calculated by dividing the total number of defects by the total number of subgroups. In this case, the number of subgroups is 15, because the information was collected over 15 weeks. For this example, C-bar has a value of 27.06667. It's important to note that based on the properties of the data, a C-chart is perfect, because the project uses defect data in subgroups of equal size. The next step in the process is to calculate the center line and control limits. As you've learned, the center line is equal to the mean, or C-bar. C-bar has already been determined to be 27.067 by taking the total number of defects, 406, and dividing it by the number of subgroups, 15, to get the C-bar value of 27.067. The next step in the process is to calculate the upper control limit, which is equal to C-bar plus the result of 3 times the square root of C-bar. You know what C-bar is, so you can plug it into the formula, and as you simplify the expressions as you progress through the calculation, you can find that the upper control limit is 42.675. The lower control limit is calculated similarly to the upper control limit. But for LCL, subtract from C bar the result of 3 times the square root of C bar. In this example, the lower control limit is 11.459. Again, as you learned with other control charts, if the lower control limit is negative, you would set it to 0 on a chart. But in this case, the result is positive, so it is set as calculated. Now that you know C bar, the UCL, and the LCL, you can plot the information on the control chart. Now you're ready to analyze the completed chart and determine what actions need to be taken, if any. There are visible signs of special cause variation in this C chart, similar to those you found in the U chart. First, there are 4 points that are above the UCL during weeks 9, 10, 11, and 12. And there are 4 points below the LCL during weeks 4, 5, 6, and 7. The points fall below the LCL indicate that you had expected defects in invoices that were less than expected. Each of these points are freaks because they are outside of the control limits, meaning they are plus or minus more than 3 standard deviations from the mean or center line. These 4 points are part of a run of 7 points that show a decreasing order, indicating a downward process shift during weeks 1 through 7. This meets the criteria for a downward process drift, which occurs when there is a run of 6 or more data points that are either steadily increasing or steadily decreasing. The Six Sigma team needs to investigate these occurrences to determine the causes of the variability during these weeks. There are several lean tools that are very useful to help you control and maintain your processes during the control phase of the Six Sigma DMAIC methodology. One of the first tools is Total Productive Maintenance, and as its name implies, it helps you maintain the gains in improved processes. The goal of Total Productive Maintenance, which also is known by the abbreviation TPM, is to maintain your processes. It's used more as a proactive maintenance program. The overall goal of TPM is to maximize the effectiveness of the processes in your equipment because you're trying to keep emergency and unscheduled maintenance to a minimum. As you do this, you also want to make sure you're boosting your operators and other employees' job satisfaction and morale, so they're taking ownership and pride in the equipment and their roles within the organization. As you maximize effectiveness, you're also removing deficiencies by working together to improve the maintenance of your operations, which in turn helps to eliminate defects and downtime. There are 6 key elements of TPM. The first is preventative maintenance. This is a time-based maintenance where maintenance is performed on a schedule that's designed to prevent breakdowns before they can occur. The second element is predictive maintenance. This is condition-based maintenance conducted using instruments and sensors, so you can anticipate when a failure or breakdown is about to occur, so it can be fixed before the machine fails. The third element is breakdown maintenance. This is when equipment is repaired after a breakdown occurs. This is when equipment is repaired after a breakdown occurs. It's more reactive versus predictive and preventative, which are both proactive. The next element is corrective maintenance. This refers to ongoing modifications to equipment that help reduce the frequency of breakdowns and make repairs easier when equipment does break down. The fifth element is maintenance prevention. This refers to how organizations can work to design equipment so that it rarely breaks down. And when it does break down or when it fails, it's easy to repair. And the sixth element is autonomous maintenance. This is team-based maintenance that's done primarily by plant floor or shop floor operators. When working to implement maintenance regimens and improve the reliability of equipment through tools like TPM, organizations face challenges as they try to change the status quo. In many organizations, there's an attitude that you fix things only if they're broken, so maintenance is reactive rather than proactive. This just-in-case mentality means storing a lot of spare parts and large inventories of backup pieces of equipment. Because of this, operators may ignore signs that could potentially warn them of malfunctions. TPM can help you move the culture of your organization from a reactive approach to more of a proactive approach. Many industries take a zero-tolerance approach to malfunctions. Take the aircraft industry, for example. Equipment maintenance is vital to that industry due to safety and regulatory compliance requirements. There's a lot at stake if their equipment malfunctions, so they have to be proactive to prevent downtime and accidents. The rigors of TPM require a high degree of discipline and certification. TPM also ensures that every process and every step is documented, so there's no question about what or how to do things. There are double and triple verifications for each and every critical process, as well as regular audits by regulatory bodies and third parties to ensure compliance. TPM aims to prevent deterioration of equipment and reduce the amount of maintenance. It's not just about fixing equipment, it's about being more proactive. TPM extends beyond simple preventative maintenance and includes comprehensive management of people, processes, system, and the environment. TPM is a coordinated group of activities that involves operators sharing responsibility for routine equipment inspection, cleaning, maintenance, and minor repairs. It also includes daily scheduled downtime for maintenance. So let's examine the total in total productive maintenance. It's made up of three parts. The first is total efficiency. The goal of total efficiency and effectiveness of equipment is the elimination of failures, defect, rework, waste, and any losses for equipment-related operations. The second part is the total package. TPM is a total package for both downtime prevention and maintainability. The goal is zero breakdowns and zero defects. Organizations are implementing TPM as part of a 2% goal in reducing original breakdowns, which has resulted in a 90% reduction of rework. Organizations are seeing significant returns on implementing programs like TPM. And the third part of total is total participation. This means involving all employees in the TPM program, from leaders to operators. Having a TPM program doesn't mean there's no professional maintenance staff. They still perform major maintenance activities and coach operators in the routine and minor activities. It means it extends beyond the professional maintenance staff to getting everyone in the organization involved in the maintenance program. A Japanese plant engineering study found that even in clean plants, more than half of machine breakdowns are caused by dirt and looseness. Management decided that cleanliness and tightness would be key in any system to reduce breakdowns. But how can maintenance workers stay on top of such a huge task? This is where TPM comes in. TPM focuses on that guiding principle of shared responsibility for maintenance. The operators are the key players, and they're supported technically by skilled maintenance workers. So in effect, maintenance workers can be everywhere at once. There are three key characteristics of TPM that come from the principle of shared responsibility. The first is that TPM has the involvement of employees at every level and across all departments. Without leadership, even the best maintenance, operators, and reliability engineers can't achieve total plant reliability. TPM requires the involvement of employees at every level and across departments, from top management all the way to frontline employees. Cross-functional teams from all departments are included, from production, product, and process development, across the board to marketing and administration. Of course, the professional maintenance staff still has responsibilities, but employee participation in the enterprise is comprehensive. This employee involvement is a key characteristic of TPM that makes it unique. The second aspect of TPM is the integration of autonomous maintenance into daily routines. Autonomous maintenance includes any activities operators perform that have maintenance functions and are intended to keep the plant operating efficiently. Operators perform certain equipment maintenance activities, which are closely linked to the daily operation of equipment. The focus of the operating team is on cleaning, inspecting, lubricating, monitoring, and other essential daily tasks traditionally within the domain of the maintenance department. In a TPM system, operators should have a sense of ownership, protecting and caring for the machines. And maintenance personnel then spend more time on value-added activity and technical repairs instead of constantly fighting fires. And the third aspect of TPM is that it incorporates company-led monitoring activities carried out by small groups throughout the organization. These small groups consist of employees who continually control and improve quality of their work, products, and services. They operate autonomously, tap members' creativity, and promote mutual development through training. They facilitate a top-down promotion of company TPM activities, as well as bottom-up ideas for the production floor's activities. The way to achieve zero losses is by overlapping small group activities to identify causes of failure or possible plant and equipment modifications. Let's explore how this might work using an example. A manufacturer of plastic injection and rubber moldings for the home appliance industry had neglected preventative maintenance. The company was in a classic maintain it when it fails situation. To improve plant availability, product quality, and resource utilization, management decided to implement TPM. The TPM committee emphasized the most important change of all, that the new plan was to be carried out through the positive participation of all concerned, across departments at every level. A suggestion from a small group for reducing part replacement time on molding machines was implemented as a joint project by engineers from the parts, maintenance, and production departments. Over a period of 3 years, this effort reduced the replacement time from 59 minutes to 50 seconds. Operators now carry out mandatory daily and weekly inspections. Without interrupting production work, operators can easily prevent breakdowns, predict failures, and prolong equipment life as they become more familiar with the machinery they use. Operators know what to do to keep the machines in normal operating condition by lubricating them regularly, monitoring vital signs, and recording abnormalities. They also know what to do to get a machine back online when something goes wrong. The company expended considerable effort on improving the plant for ease of machine condition monitoring, including creating small groups within and between departments. Group activities are overlapped to promote a closer working relationship between maintenance workers and plant operators, encouraging operators to become more equipment conscious through focused training. The small groups successfully helped in this training, as operators learned what constituted normal and abnormal operation, and what to listen for to detect potential problems before they occurred. Total Productive Maintenance, or TPM, focuses on the zero loss concept, which has 4 objectives. The first objective involves trying to get to a point where you have 0 equipment breakdowns. This will happen if your organization is being proactive enough that your machines don't break down and you're doing regular maintenance as it's needed. The second objective is 0 defects. As you reduce breakdowns and the variation from machines by helping them to operate more consistently, your output also becomes more consistent. Reducing the number of defects helps eliminate equipment-related failures and waste, which is the third objective of 0 defects, and it also minimizes the need for emergency maintenance events, the fourth objective, because you're performing predictive maintenance when it's needed and your machines aren't going down as frequently. There are 6 big losses that negatively impact an organization's equipment efficiency. The first one is equipment failure, which results in downtime for repairs. Breakdowns cause a loss of time, resulting in lower productivity, and cause quality losses from defective products. Costs associated with equipment failure include downtime and its resulting lost production opportunities and yields, as well as straightforward costs for labor and spare parts, so it can be fairly expensive. The second loss is setup and adjustment losses that come from equipment changes. They result in lost production yields that occur during product changeovers, shift changes, or other changes in operating conditions. The third type is idling and minor stoppages. These can be caused by defective sensors, conveyors that jam, and other things like this that result in slowdowns and losses. Frequent production downtimes, which can range from 0 to 10 minutes in length, add up over time. Minor idling stoppages are typically 10 minutes or less, and are often difficult to record manually. As such, they're typically hidden from efficiency reports, and they can cause substantial equipment downtime and lost production opportunities that add up over time. The fourth big loss is reduced speed. The differences between designed and actual operating speeds results in losses from reduced speed. Productivity losses occur when equipment has to be slowed down to prevent quality defects or minor stoppages. In most cases, these losses aren't recorded since the equipment continues to operate, though they may directly impact overall equipment effectiveness, or OEE. The fifth loss involves process defects. Process defects produce scrap, and quality defects causing off-spec production and defects due to equipment malfunction or poor performance. This can lead to reduced output that has to be reworked or scrapped as waste. The sixth big loss is reduced yield. This is typically reflected in wasted raw materials associated with rejects and scraps. They're typically linked to machine startups, changeovers, equipment limitations, and poor product design. Organizations need to start eliminating or minimizing these 6 losses because they impact overall equipment efficiency and productivity. Let's explore how the goals of TPM address each of these losses. The loss due to equipment failure is addressed by the goal of 0 losses due to breakdowns. For the setup and adjustment loss, the goal is to keep the changes under 10 minutes. With idling and minor stoppages, you should be trying to achieve 0 losses. The goal associated with the reduced speed loss is to have 0 speed losses. To address the losses due to process defects, the goal is to have 0 quality defect losses. And the goal associated with losses from reduced yields is to minimize yield losses. Equipment downtime can bring a lean manufacturing operation to a complete standstill, so you want to address equipment failures because of their impact on your ability to carry out your organization's processes and the flow of your entire operation. If implemented properly, TPM provides several key benefits. The first benefit is that it increases productivity and efficiency due to downtime reductions. Another benefit is reduced cost and inventory because you're not holding additional product just in case the equipment breaks down. And you're also not holding additional inventory and parts for spare parts in case equipment goes down and you need to perform maintenance. You can also reduce accidents and pollution because when machines break down, safety is vital, and accidents can occur because you're not operating under the standard procedures. Circumstances are slightly different than what you're typically operating under. Additionally, when you're using TPM, you're not doing much firefighting, and this really helps to increase employee morale. Finally, as operators are being trained to better understand and take care of their equipment, you're enhancing their skills and the skills of other employees. The visual factory is a concept used in lean manufacturing during the control phase of the DMAIC methodology. In a lean manufacturing environment, the time and resources dedicated to conveying information, although necessary, are considered a form of waste. Using a combination of signs, charts, and other visual representations of information, the visual factory efficiently disseminates information at the point of need within a lean manufacturing process. In short, the visual factory is a way to make sure that everything is clear, to save time, to improve the effectiveness of processes, and to enable organizations to quickly understand how its operations are functioning. Now, while the name visual factory seems to make it relate more to manufacturing, this tool is increasingly being used in service industries and healthcare, hospitality, airlines, and other types of customer service operations. In that context, it's referred to as the visual workplace. Later in this topic, we'll explore an example of how this concept was used in a hospital. The key characteristic of a visual factory is visual cues such as warning signs, process flowcharts, status maps, maps of the building, indicator lights, use of color coding, or even simple arrows. All of these are very useful in helping to make sure things are simple, succinct, and effective. At a quick glance, these visual clues help workers see exactly what's going on and what needs to be done. Visual cues are efficient because they can convey information very quickly and reduce the need for repeated verbal messages or costly demonstrations. But this happens only if they're easily understandable and consistent across the board. For example, if you think about a stoplight, red always means stop, green means go, and yellow means slow down, no matter where you go. It's simple, effective, and consistent. This same thinking applies to the creation of visual cues in an organization. Keeping things consistent and as basic and as clear as possible helps make sure that the visual cues are easily understood. There are 3 basic goals that these visual management tools fulfill. First, you want to make sure that when problems arise, they're visible to people who need to know about them. This enables quick reaction to take care of the problem, thereby reducing downtime. For example, if a light flashes when something goes wrong in a process, it's very easy to see there's a problem, which helps people keep direct contact with what's going on in the workplace. A supervisor can look across the shop floor and see where disruptions are occurring and what's going on at any given time. Additionally, visual cues can be used to clarify the organization's targets for improvement. For example, if you have some processes that need to be improved, You can apply visual cues to help people become aware of the problems within the process and keep them informed of progress made or not made toward improvement. There are two main components of a visual factory: visual displays and visual controls. Visual displays impart information and data to employees in the area. Such displays make working areas user-friendly by answering questions, identifying equipment, materials, and locations, describing actions and procedures, and providing safety warnings. Labels and signs are displays that communicate needed information at the point where it's needed. Visual controls actually control or guide actions. They give management and workers a visible manifestation of what's happening at any moment, allowing for immediate feedback about the workplace's condition. Visual controls include production boards, schedule boards, tool boards, Jidoka devices, and Kanban cards. They can illuminate the condition of workplace safety, production throughput, material flow, quality metrics, or other information. Let's examine how a hospital could use visual factory components. Visual displays that could be used in a hospital might include information on large whiteboard charts that show operating room schedules or attendance, making it clear at a glance who is on duty, who is incoming, and when a substitute has to be called in. Visual controls might include color-coded painted arrows and signs on the floors, which could guide workers and patients to the correct exits and departments in the hospital, providing information at a quick glance when needed. Visual displays and controls can also be combined. For example, in grocery stores, they turn checkout aisle lights on to indicate when registers are open to take customers. This provides useful information not only to customers in the store, but also to management and workers to help them understand how the checkout process flow is currently operating. Another example is any ticket system, where the number being served is displayed on an LED screen, such as in a bank or a delicatessen. Now let's explore some of the key tools of the visual factory, and how to use them to make problems more apparent. As you may recall, there are three key goals of a visual factory, and each goal is associated with tools that can be used to help organize and achieve those goals. A key tool used to make problems visible is Jidoka, automation with a human touch, which empowers employees to stop the line when a problem is detected. The second goal is to make direct contact with the workplace, and tools that are used toward that goal are visual information systems, Kanban systems, audio signals, or visual production controls. These all provide information to provide employees, supervisors, and managers with information to keep them in contact with how the workplace is operating. The tools used to clarify targets for improvement are visual performance measurement and periodic reporting displays. Both provide visual displays of information that make sure the organization's targets are clear and everyone is well informed. Next, we'll examine the first tool, Jidoka, in more detail. The main concept behind Jidoka is automation, which may also be described as intelligent automation or automation with a human touch. It describes a feature of machine design that enables employees to stop the line when a problem is detected. This type of automation implements some supervisory functions rather than production functions by empowering employees as thinkers and giving them the right to stop the production line if necessary. Some of the common Jidoka devices include signaling solutions, panel mount alarms, LED round beacons, hazardous location signaling, and safety relays. Let's explore how a shutdown device could be used in a Jidoka system. In a metal manufacturing plant, if the temperature drops below acceptable levels in a machine that heats up aluminum, a red light comes on above the machine. When the operator or maintenance personnel see the light, they stop the machine so it can be fixed. Visual information systems are used in the visual factory to help people keep contact with what's going on in the work environment. These are helpful because they provide simple information about the performance of a process at a glance. For example, they could be signs, labels, or marking on a floor that point out where aisles or emergency exits are. A visual information system could consist of toolboards or indicator lights that provide information about how a process is running. It could also include things such as Kanban cards or the information on the product itself, so you know exactly where things are. And it could include process flow diagrams that give you a quick understanding of what needs to happen next within the process. So let's consider an example where visual boards have been used. An air compressor company has implemented a visual management system. They created tool boards to hold or mark the places of tools that are required for each workstation. The tool boards visually convey two types of information: where each tool goes and which tools are missing. You know exactly where the tool needs to go based on the shape of it, and you know whether the tool is there or it's missing. This saves the operators a considerable amount of time and eliminates the need to search for the tool in other boxes or work areas. Another visual type of information is the Kanban system. As you may recall, Kanban means a signal. In lean manufacturing, a Kanban signals the need for materials, acting as a pull system. Let's explore an example. A Kanban system was implemented in a factory that manufactures lounge suites. One of the components needed to produce a particular type of armchair is a 10-inch bolt. These bolts are designed specifically for use in assembling a particular type of chair manufactured in the factory. The bolts are manufactured in a separate area of the factory and arrive at the chair assembly station in boxes of 100. When a box of bolts is empty, the worker assembling chairs at the station takes the card that was attached to the box of bolts to the bolt manufacturing area. This action triggers the production of more bolts, which are sent to the chair assembly station. The Kanban card is a signal that provides information back to each operation on what's happening. In addition to visual signals, audio signals are also an important tool to keep workers in contact with what's going on in the workplace. Even though they're not visual, these audio signals still communicate information, indicating malfunctioning equipment, or sounding warnings that will alert people prior to the start of a machine operation, or when transport vehicles are backing up, among other things. They're another way to provide information about what's going on in a process or on the production floor. Another way to help employees stay in contact with the workplace is through the use of visual production controls. These generally include the posting of daily production data, maintenance items, or quality problems for everyone to see and understand. Before the start of a shift, a department supervisor might use the boards to discuss the daily planned activities and any specific problems. Visual control boards are a specific type of visual production control used to estimate progress in various departments. They can take many forms and might indicate where there are quality issues, if there's any machine downtime, cost reduction, trends, total productive maintenance, or 5S activities. And they may provide information about production or delivery information, or provide checklists and work instructions for processes. Visual controls can give quite a bit of information. For example, each week, the company might create a visual control board that lists each department and tracks, on a daily basis, the defects each department has, or which processes are running above or below control limits, providing important information to management and department employees about how well their process is running. Visual control boards provide good information about how the processes are trending, if there are too many defects in one area, and where the company needs to focus its efforts. And finally, let's explore an example of a visual control board in use. A parts manufacturer is simplifying its production scheduling using visual signals. Instead of generating paperwork, the supervisors are using signs to trigger indicators during their production processes. They're using this as more of a scheduling board, so they can look at their processes and see what's coming down the line to schedule their production. On this chart, they're using a simple system with X's that indicate the product has been consumed. When the filled-in areas of the chart reach a certain height, the operators are authorized to produce more parts. The chart tells the viewer exactly where the production point is, and then when it's reached, they need to produce more of that specific part. Using something as simple as this, everyone in the area can quickly visualize part consumption and the production status. Visual performance measurement tools are a group of tools used in a visual factory to clarify performance targets for employees. If an organization wants to make its targets, they need to make sure their workers, operators, and employees in general have performance information. If they don't have access to information related to their performance and where they are in relation to performance targets, then they can't help the organization reach those goals. Visual performance measurement tools help organizations meet the third goal of a visual factory. which is to provide goals versus actual performance information. There are several tools that can be used to summarize performance measurement information. For example, you could use status boards, indicators, quality control charts, or check sheets. Let's explore an example of how one factory keeps employees in touch with their targets. At a paint factory, managers have set up performance boards to display information about where each workstation is actually running and what their targets are. In this organization, the floor supervisors are responsible for recording the quantity that's been completed at the end of each hour, as well as the cumulative quantity that's completed at the end of each day. These performance boards show the current status of operations by looking at what the work in progress is and when it's due, helping the team meet the goals. You can use boards like this or any other type that may include information such as hourly production goals against actual production, days of inventory, cross-training data, or the number of improvement projects that have been completed. The boards can also be color-coded to indicate various statuses. For example, the board might show which lines are on schedule using green dots. Yellow dots might indicate lines that are slightly behind schedule, and red when a line has actually missed a deadline. It's important to make sure that consistent rules are used for color coding, so that the same coding is used in all departments. If you have employees that are cross-trained and move across different departments, they don't have to relearn a new system. Consistent mechanisms reduce wasted time, which is important in lean manufacturing. Other types of visual information used to clarify targets include periodic reporting displays that visually display performance over a specific time period. For example, you can use weekly data or monthly trend lines and improvement plan information. Color coding is an important mechanism to help employees focus on the key information you want them to focus on. Consider this example of how color coding can be used as a simple display to clarify progress toward targets. This dashboard-type display looks at division performance in 4 areas: quality, schedule, cost, and people. The pointer shows where the division stands in meeting its goals. From this chart, you discover that first pass yield isn't meeting the quality goals that have been set because the pointer is in the red zone. The division is also not meeting its goals in relation to cost or people metrics either. However, they're running in the blue in relation to schedule goals, which means they're running where they need to be. Using simple displays of information such as this dashboard enables employees to quickly see that the division is behind in 3 out of 4 targets. Knowing where the division stands helps employees identify what they can do to help the division meet performance expectations. Dashboards such as this provide information in multiple areas with a quick glance. Let's examine how total productive maintenance can be used in service organizations, which are typically characterized by intangible processes. They deal with perishable outputs that are commonly driven by the customers themselves, so they aren't always able to provide a consistent or the same type of output. It's more of a heterogeneous type of output. Service environments are also characterized by having simultaneous production and consumption. The TPM principles and tools can be applied in service industries as well as manufacturing settings. For example, the hospitality industry includes hotels, fast food chains, and restaurants. There's plenty of equipment in each of these environments that needs to be maintained in order to provide services. If the equipment breaks down or doesn't work, you'll have unsatisfied customers. Other service organizations that rely on equipment to deliver their services are good candidates for TPM, including airlines and customer service operations such as call centers, help desk, and contact centers, and also functions within an organization such as finance and human resources, product development, purchasing, and engineering. These all use equipment that need to be maintained and, when it breaks down, may lead to consequences with their customers, whether they're internal or external. It's important to think about what equipment is used in these organizations and how to make sure it's being maintained to continue to provide consistent service. In service industries, the TPM metric changes slightly to look more at overall performance efficiency, referred to as OPE. This commonly used metric measures the effectiveness of people versus the process. What you're really doing in service industries is targeting value and non-value added factors to try and reduce the waste in the processes used. The OPE metric helps to identify and uncover waste such as waiting waste, changeover waste, retrieving waste, delivering waste, cell motion waste, and rework waste, amongst others. That helps organizations to determine what some of the contributing factors to waste are in their systems or processes, which could include scheduling and other abnormalities, operator performance, or process performance. Consider how TPM works in the healthcare environment. TPM has considerable opportunities for applications in hospitals because there's equipment everywhere. There's sterile processing, which has washers and sterilizers. Radiology has X-ray equipment. Surgery has C-arms and anesthesia equipment. And the floor nurses use medication storage machines and machines at bedsides that monitor vitals. All of this equipment needs to be maintained, so this ties in directly with the TPM goals of making sure equipment is available. In hospitals, TPM goals are to eliminate unplanned machine downtime, increase machine capacity, have fewer errors or failure rates, allow for minimum inventory, and increase equipment operator safety, among other things. What you're really trying to do in healthcare, then, is shift the maintenance department from focusing on the use of medical devices to how to maintain those medical devices so the hospital can reduce its operating costs, have better uptime and availability of needed equipment, and in doing so, create a better working environment. Using TPM in service organizations has a number of potential benefits. It can lead to a better use of work areas, reduced administrative cost, a reduction in the number of files, increased productivity in support functions because they don't have downtime waiting for equipment to get back up and running, and reductions in office equipment breakdowns and customer complaints. All of these benefits result in a clean and pleasant work environment. Depending on the type of industry you're working in, you might either be working in a visual office or a visual factory. Visual factory is typically used to refer to manufacturing environments, while a visual office is based on the extended notion of the visual factory, but encompasses other types of organizations, such as the service industry and office environments. The visual office is similar to the visual factory, but in service organizations, the kinds of information being tracked is about employees seeing at a glance what their role is, how the office is organized, and whether the company or department is achieving its goals. For example, you could have a call center that uses visual cues such as pie charts or bar charts to indicate how it's achieving customer service metrics. Let's consider how that might work at a small bank that guarantees its customers they'll answer their customer phone calls promptly. The flow of customer queries at the bank's call center is fairly unpredictable. For example, the bank receives a lot of phone calls during the last hour of business, and employees find it difficult to cope with the volume of calls, because they might have to work overtime to catch up on other tasks. In order to handle this problem, the manager decides to monitor the calls more closely. She uses a chart to post the hourly updates, which helps track what the customer calls are and gives everyone an idea of what the average customer wait time is. If the wait times are getting too long, the manager could use this information to transfer more employees, to concentrate on clearing out the call log. Having this information in a prominent place in the office helps employees and managers manage their time better. When you're putting charts or any other information out in the workplace, it's important to make sure that you use large text and clear graphics, so that all employees can see at a quick glance what's going on, as in this case, where they're able to see quickly what the average customer wait times were. Now let's explore another scenario of how visual control tools can be used in service organizations to reduce the amount of time wasted on tasks that could easily be performed with some type of visual cues. In this example, you've got employees at a busy travel agency who have to fax many documents throughout the day. Some of the employees are unsure how to operate the fax machines. Faxes sometimes don't get transmitted, causing employees to waste time trying to figure out how to do it, then having to ask a coworker who knows how to do it to help out, and then they're wasting their time showing others how to use the machine correctly. So as a quick fix, the manager puts together simple work instructions that outline the steps for how to send a fax. The manager posts this on the wall beside the fax machine. He also puts a note on the fax machine that lets employees know that if they're unsure how to send a fax, they should refer to the posted work instructions. This simple reminder helps to make sure that faxes are getting sent without any mistakes. In another example, a graphic design department has been receiving a lot of customer complaints about the quality of their graphics. After investigating the problem, the manager determines that some of the designers are submitting graphics to production without having them checked by the quality department first. The solution to this is to standardize the graphic design production process. The manager meets with the team leads to come up with some best practices. They develop the best practices into a workflow diagram so that everyone follows the same process. Let's consider one final scenario. This situation involves temporary employees at a doctor's office who are finding it difficult to locate files. This causes confusion for the contract workers. Since they aren't familiar with where to return the files after they've used them, they don't know where things go. This has created confusion in the office and started to lead to conflicts. Patients are starting to complain about the wait times created by the lack of organization. To solve the problem, the manager invests in new storage shelves and filing cabinets. She then completes an inventory of all of the information the office has on file, including patient details, employee details, and financial results. Each filing cabinet is then clearly labeled according to the information it contains. The cabinet drawers of each filing cabinet are also clearly labeled. For example, one cabinet is labeled Patient Details, and the 4 drawers are labeled A through G, H through N, O through S, and T through Z, so that files can be easily organized alphabetically. This is a simple visual control that helps employees see at a glance where files should be returned or filed.